Good morning, everyone. I want to welcome you to the 2023 NETL workshop on multiphase flow science. It's almost 9:20, and I am Marianne Clark, and I will be the moderator for this morning session. My colleague, Arthur Conan, will be helping me along, and he will be monitoring the chat for questions. And I understand from our WebEx leader that if attendees have questions of the presenters or panelists, to engage with the chat, that it's going to be a little bit difficult to take voice questions. So that would be great if you will use the chat. And Meredad, when you're ready, could you put up the first slide of your presentation? And then when you're ready to start, please do.
Great, thank you, Marianne. Let me, okay. All right. So hopefully you can see my desktop.
We can.
Okay, great. Well, good morning, everyone. Good afternoon, good evening, good night, depending on your time zone. Thank you for attending the 2023 NETL Multiphase Flow Sciences Workshop. My name is Mehrdad Shanam. I'm the team supervisor for the computational device engineering team. And if I can, why can't I go to the next slide? There we go. All right. Our mission, the Multiphase Flow Sciences team mission at NETL is to support, obviously, the DOE mission. And the tools that we develop are cross-cutting, and it's used across many departments and offices. Our tools are all, the physics-based modeling tools. We use a lot of AI/ML application these days. We do have a small experimental facility that we use for small-scale data generation for model validation. And we also have our own HPC system, Joule, at NETL that we use to, do all of our simulations. The programs in FECM that we heavily support are hydrogen production, in gasification, carbon capture, and among some of the other programs. And of course, as I mentioned, the work we do is crossing. We reach across other offices as well, ERE, Office of Science, the Environmental Management, among many other offices. There is a snapshot of the folks involved in the Multiphase Flow Sciences team. This is not a complete picture here. There are a few colleagues that recently joined that I don't have their picture yet. My apology to them. The MFS team, as I mentioned, we develop modeling tools. MFIX, of course, is our workhorse. We've been developing that for about 30 plus years. There are other tools such as Nodeworks and trackers that we use. We have been developed and we use for our activities. As I mentioned, we have the Multiphase Flow Analysis Laboratory that we run experiments in support of the model development that we do. And of course, the application, all of these activities are in support of the various applications that we are engaged with, from point source capture and carbon conversion to gasification, hydrogen production. And I should also mention that aside from MFIX, we also do use other commercial and open source code, depending on the application and the need, of course. Just a quickly I go over some of the recent releases of MFIX. In MFIX 22.3, that was released, and in October 2022, aside from the typical bug fixes that every version will have, I think there were some improvement made in the display and display panels. As you can see here, I believe this is showing, for instance, the force between particles in DEM. In December 2022, the Super DEM was released in version 22.4. This is where the super quadratic shapes are used to model non-spherical particles. And then in version 23.1, some improvement was made to the geometry cleanup and geometry formation in MFIX. And of course, in this latest version released 23.2 in July of 23. There was some improvement made in the chemistry, setup. We are not able to directly support ChemCan thermodynamic data set, and of course, improvement also were made in dealing with different numerous reactions and species. MFIX outreach, there is a model, a VNV manual that was finalized within that past year, and is actually on the MFIX website for those who are interested. And of course, this past year was another successful year for MFIX. We have about 658 new registration, just under 7,000 downloads, and right now we are at 8,300 plus all-time users, and you can see the breakup of the MFIX community. Majority is in universities, academia, and then these are the breakup between industry, national labs, and others, mainly the different industries, smaller players. I should mention that MFIX EXA, which I'm sure some of you are familiar with, was a very successful program. I believe it's coming to an end at the end of the 3-year funded activity through Office of Science. The goal was to port CFD-DEM and PIC, from the start, a clean implementation in GPU and CPU. As I mentioned, that is completed and it's actually available for download. The link is up on top. Those who are interested, you can certainly download it and give it a try. It is MFIX for, at exascale, basically. Some of the very recent developments are listed here. Multi-grid neighbor search algorithm, and of course documentation is available, and the PIC to DEM application, which is actually very unique and a very smart way of initializing your simulation. Those who do run multiphase simulations know that initialization is always a major time-consuming part of the process. With this PIC to DEM, you can actually initialize your solution and let it develop using the PIC, and then at some point in time, once you feel confident that the initial transient have sort of left the system, then you can switch to DEM and then bring in that high level of fidelity that DEM simulation provides you. We are certainly very excited about that feature. And some of the applications that team has been involved with, some of you may remember this from previous years. This is the oxygen solvent technology. We've been involved with other colleagues here at NETL who've designed actually this particular prof's guide that is showing up here. And our team has been working closely with them to develop the appropriate modeling tool to obviously simulate at lab scale and then help take this to a much larger scale. To date, kinetic rates have been developed for oxygen absorption and desorption using data from TGA and bench scale experiments. Model have been validated, and as you can see here, in this case, the hope is to use this oxygen carrier potentially for use in gasification, for instance. And you can see the actual prof's guide material itself, and these are some of the absorption, desorption, the curves that you see during the process of absorbing the oxygen and obviously then releasing it. And this is a conceptual design that my colleagues were working on and testing. Basically, you're looking at 3 geometries here. One is a packed bed cylinder, and these other 2 are the this kind of a multi-tube arrangement and stack arrangement. They alternate between absorption and desorption of the material. Oops, I didn't mean to move. And as you can see here, you can see how this multi-tube bundle or plate stack works as you go through numerous absorption and desorption cycle. When, for instance, tube 135, it could be 135 here when they're absorbing oxygen. The other three tubes are desorbing, and of course, this is a temperature is very important here, managing the temperature, because as you can see in these other plots, the absorption and desorption is really a function of temperature. And we can see here for the different configuration that was tested here between 500 and 550 C operating temperature, you can see the difference between the amount of oxygen that's been produced or deserved. So this has been a successful activity, and currently the goal is to take this sorbent and of course the model to a much larger scale, potentially at a pilot scale. And another activity that we are heavily involved is DAC, the direct air capture. NETL is putting together what we call a center, and we've been asked to help with some of the initial design here, and some of my colleagues have been involved with this activity, and this is basically showing some of the design concerns that folks have in terms of flow uniformity in the system, gas mixing, steam concentration inside the piping. And of course, we've been using our modeling tool to help them with some of the design aspects of this DAC center. Aside from that, we're also heavily involved in developing absorption desorption modeling capability for a porous fiber. It's a polymer fiber, again designed by our colleague at NETL. And we've been collaborating with them and developing modeling tools to capture the absorption and desorption process. For this activity, we are using a second-order linear driving force model. And here, in conjunction with the experiment that were done at NETL, we can see the capacity, the absorption capacity of the fiber. And of course, we have been carrying out, as this animation shows, this is a simulation of an actual experiment, a pack-packed experiment that we are doing in our MFAL lab to look at the breakthrough curve, as is shown here, compare the different breakthrough as a function of temperature. And the goal here is to calibrate the K, which is kind of the transfer sort of coefficient there. And this is a successful program, and again the goal here is to move this now. These animations that I'm showing, they are I don't believe they're necessarily at DAC level capture, CO2 capture, the 400 or so ppm, but currently the goal is to push and move to that level of low ppm CO2 and test the model. One of the other issues here is, since in DAC pressure drop in the system is quite important, we are also helping, and this is just a proof of concept. We are helping the design team to come up with what they call a shape factor. This is the different arrangement, fiber arrangement, that will give you the least amount of pressure drop for the obviously most performance, the optimized performance. And we are helping with that activity as well. Another activity that you may recall from previous year is the kick detection work that we are doing. One of my colleagues is leading that activity, and the goal here is to produce data through experiment and also simulation to help the knowledge gap that exists for kick detection. This is quite important to gas and oil drilling folks. And We've all seen what happens. Some years back, we all remember Deepwater Horizon, and we can. So it is the potential for something going wrong and leading to some disastrous outcome is great. So here the goal has been to use CFD to come up with acoustic sensor, essentially, to simulate an acoustic sensor, the performance of acoustic sensor that can be used in wellbore for detecting these pressure pulses or that are created when you have fluid during the drilling leaking into the system. I believe there will be a talk on this actually tomorrow. And that's quite an interesting topic. Another activity that we're heavily involved is gasification. We've been at that for a number of years now, and here the goal is to look at gasification of biomass and plastic and municipal solid waste with multiple goals. One is for hydrogen production, and the other goal is for sustainable aviation fuel. And we are using, we have a research agreement with one of our collaborators in Italy, Sodocarbo Sustainable Energy Research Center in Italy, and they provide us with a large-scale, pilot-scale experiments that we use for our model validation. Here we are looking at a gasification of eucalyptus biomass, and test was carried out at Sodocarbo for a 300 kilowatt thermal fluidized bed gasifier. There is the picture here, and of course this is the unit itself. And it was a quite a successful as a model. We can see that some of the species are captured actually reasonably and well, and the temperature profile inside the system is captured, even though there is only 2 data points. But we can actually see that how the temperature in the mixing zone is right on, and the temperature actually in the freeboard is pretty close to what's been measured. And what you see in the animation is just a gas temperature and solid temperature. And I mentioned that we are also heavily involved in plastic pyrolysis and ultimately moving towards municipal solid waste. We are collaborating with our colleagues in our Pittsburgh campus, looking at pyrolysis of high-density polyethylene, and they have a drop tube that it's shown here in this picture. And we are looking at pyrolysis of a couple of pellets. It's 25 milligram each. In this drop tube, we are looking at multiple temperatures here from 500 to 900 degrees C. And one of my colleagues is involved in this activity, and this is the model that he's using. The model is from open literature, and it actually is doing a reasonably nice job. We can compare it with the TGA data and some of the gas that's being produced. But we feel that obviously this can be done better. So we are now moving more towards a lot more detailed kinetic model, as opposed to this very global model. And we are actually have started a collaboration with Polytechnic University of Milan. The goal is to develop very detailed kinetic model for different plastic type for pyrolysis. And the goal here is that to look at this at the polymer essentially in plastic, and lump them into functional groups. And as we're saying here, to look at it as to sort of break it into mid-chain and end-chain polymers, and then break it further down into high molecular weight chain that decomposes to further decomposes to sort of smaller fragments, and then ultimately to low molecular weight species. This is the kind of mechanism that we've come up with. Oops, I need to go back. Plastic, which is represented by C20H40 in solid phase. And of course, after it heats up, it goes into liquid phase. So everything here is all in liquid phase. And so we have 40 liquid species and 31 gas species that describes the pyrolysis of polyethylene, for instance. And 9 of them are these heavier polymers, as they're shown here in liquid phase. There are 11 low molecular weight species. Now, these are real gases up to C5, as it's been shown here, from CH4 all the way to C5H12. And then, since this is a lumped approach, the heavier materials, anywhere the carbons from C5 up to C40, they're lumped into two groups, C15 and C39, and then we represent them in terms of olefin, diolefin, and paraffin, and that's what you see here. For instance, we have the olefin here for C15, then we have our the diolefin, and then the paraffin here for C15. Same thing for C39. And this is in liquid phase, it decomposes to gas phase. So this is basically the mechanism, the number of species that we have to deal with. Now the goal is to make this suitable for CFD. We started our baseline number of reactions, as I'm showing here. There are 71 species and 1,377 reactions. This is obviously, there are too many reactions here for using CFD. This reaction set has been further reduced to 969 and 737, and the smallest set right now is 489. So this one is 51 reactions and 51 species, 489 reactions. And this is how some of the reaction model is going to look like. We have number of these heavier hydrocarbons, and plastic, for instance. This is like 3 of them I'm just showing here, breaking down into other components and some light gases, for instance. So the goal here is to go further down from 489 to something much more manageable, perhaps in the order of 30, 40, 50 reactions that can be used in CFD. And just showing here some result. This is a single particle sort of model. We're just testing the accuracy of the model with respect to some TGA work that was done at heating rate of 5 centimeter, 10 centimeter, and Celsius, 5 Celsius per minute, 10 Celsius per minute, and 20 Celsius per minute. And we can see that the 4 reaction set that I was just showing, they agree reasonably well with the data. So that's good. And what I'm showing here is actually the number of carbon. C1 through C5, these are all real species, and C15, C39, these are the lump species. And we can see that, for instance, there isn't that much difference between the 489 reaction set and 1,377 reaction set. Clearly, we have more C15 when we are using a larger reaction set, but altogether, we are not losing that huge of an accuracy when we go to this sort of a low number of species. But again, as I said, the goal is to take this even further down. And let me, in the interest of time, quickly, I can probably skip over this. This is just showing, again, the same thing, that molten plastic, shown here by red, that dotted line. As we increase the temperature, obviously, the mass loss goes all the way to 100%. And these are the liquid species that are being formed during the pyrolysis. You see some of the C15, C39, the olefin and vital olefin and paraffin being generated. And this one shows the same thing except in the gas product. And again, we see that these are the lump species. The read here, the takeaway here is that at the end of the pyrolysis, I believe this one was about 800 Kelvin, we have about almost 50% of the gas yield is C15. And this is the breakdown between olefin and diolefin, and same thing for the other one. What I'm not showing here is the secondary pyrolysis when this C15 and C39, and perhaps even some of these carbon 5, that could further break down to lower hydrocarbons. Work is on the way actually to also look at that aspect of it. And last but not least, quickly, I should mention, since we're talking about liquid plastic, stickiness is an issue. And this is something that another colleague is working on. What you see here is red is plastic particles coming in and colliding with sand particle. And he's using some of the material in open literature in terms that's used in coating processes. And what you see here is that as the two collide, the plastic, basically, we assume that it is covering sand. And of course, as it goes through the pyrolysis process, plastic is pyrolyzed, goes away, and we get back to sand. Another issue is stickiness. And here we are looking at, my colleague is looking at the concept of bridging when the plastic particles, two plastic particles collide. This bridge is formed and a capillary force is calculated, which is added in DEM as a force. And this simulation, I believe, it kind of shows that these two up on top is when they collide, there is no bridging. And that's what I guess this is showing, that that the X location that continually they rebound. But when bridging is accounted for, we can see that the two particle stick together. And of course, they stick for as long as plastic is present. And once it devolatilizes, then we go back to a clean sand particle. This is a work in progress, and soon this should be included as part of the work we are doing. And I think I should wrap it up right here. This is just a disclaimer that that everything I said here is my own personal opinion, and it's not the opinion of the U.S. government. And I just want to put a quick plug here, an announcement that we do have an open position in our computational device engineering team. And oops, I did not mean to do that. Let me go back here. And I want to emphasize that since this is a federal position, and you must be a U.S. citizen to apply. And we invite you to apply, send a resume to the email cse@netl.doe.gov if you qualify. With that, I thank you for your attention and your participation. And Marianne, back to you.
Thanks, Mehrdad. It's really tough to tell your boss to wrap it up. He knows he's over time. But in the interest of time, I'd like to introduce our next presenter, Z Chow from Virginia Tech, I believe. And he's going to give us a talk on particle resolved approach for simulation of freely evolving sphere suspensions. So if you would please put your presentation up and begin when you are ready.
Yeah, good morning, everyone. My name is Zhe Cao, and actually I was a former PhD student in Virginia Tech, and now I'm working in the School of Hydraulic Engineering in Dalian University of Technology. And I'm collaborating with my former advisor in Virginia Tech, Dr. Danish Tufti, and working on the simulations for a particle resolved approach for simulation for freely evolving sphere suspensions. And I'm going to talk about my research in those four aspects: the motivation, the collision modeling, and the particle resolved simulation, which I will call PRS in the following. And finally, some of the statistics analysis of the suspension and the particle mobilities. And firstly will be the motivation. So if we look at the animation on the right, basically in fluid particle systems, right, usually the particles will be driven by the moving fluid, which means the particles will move along the particle path. The particle will move along the fluid path. And those applications will involve in like the animations on the right, which is the fluid as a bed or the sediment transport in rivers or oceans. And usually those animations, those type of simulations, they will require accurate drag models to account for the momentum exchange between the fluid and solid phase. But the correlations are usually derived from experiments of stationary packed beds or simulations for stationary suspensions of particles. And the figure on the left basically shows an example of the PR simulation for stationary sphere suspensions. And the colors basically corresponds to the pressure distribution and the flow is along the x direction. And to fill this gap, what we are planning to do is basically simulating the particles with the mobility to moving in the suspension, which is driven by the fluid motion here. And usually in particle resolved simulations, usually the approach will be involved is something like the immersive boundary method, we will call it IBM, or the lattice boson method, we will just call it LBM. And the characteristics of those methods is that they will usually require a few layers of fluid node surrounding the immersive surface, which we can see the immersive surface is a circle here. And they will require the flow informations from a few layers surrounding the particle. And they will define the probes that starts from the immersed surface and step into the fluid region and interpolate the flow information to the probe. And then using the probe information to calculate the viscous force and the pressure force on the surface. And this will lead to an issue when simulating the freely involving suspensions is that the direct contact will lead to probes from one immersive surface embedded into another immersive surface. And this will lead to accuracy or sometimes even stability related issues. And the way we deal with it is that we would pre-trigger the collision when the two particles gets to a distance that less than some buffer distance. And this is basically how we deal with it. Let me try to drag this one here. And when two particles are approaching and when their distance are equal or less than the 4 times of the background cell edge length, we will just pre-trigger the collision and we will resolve the collision using the soft sphere model. And then afterwards, we will just separate the particles using the post-collision velocity that is derived from the soft sphere model here. And this is a very simple and direct way to deal with the collision. And another thing we need to demonstrate with such a way of dealing with the collision is that when the density ratio between the solid phase and fluid phase is at the order of 1 or at the order of 10, there's one effect which is called as lubrication effect will come into play when two particles are getting too close here. And this basically the lubrication effect acts like a damper that impedes the particles' relative motion. So they will making the effective coefficient of restitution less than the condition in the cases like maybe the solid phase in the gas or something like that. And to account for such effect, we just apply the wet coefficient of restitution in the calculation to account for the lubrication effect. Basically, this is how the wet coefficient of restitution behaves at different Stokes number here, right? So when the Stokes number is low, we can just imagine like the density ratio between the solid phase and fluid phase are very close. And under this case, the lubrication effect will be very strong, and its damping effect against the relative motion between two particle collisions will be strong. So you can see the effective coefficient of restitution, which is the wet coefficient of restitution, will be very low here. And after those processes, firstly, I will just introduce the numerical setups that has been done in our calculation. As we are using a relatively new method to deal with the collision, so we need to testify the effect of the domain size and the grid resolution and their effect on the results. So the best case basically is the first case. It has a domain size of 5 by 5 by 5 times the particle diameter, and it uses a grid resolution of 1/40 of the particle diameter. And such grid resolution has been widely, I would just say, justified by our previous research. And the next one is setup 1. So setup 1 basically is this larger domain. It has a domain size of 9 by 9 by 9 times the particle diameter, and it uses the same grid resolution as the base case. And the third one is a setup 2, and it uses a much finer grid comparing with the base case. And the figures on the bottom basically shows the different grid resolutions, right? It uses a much finer grid comparing with set 1. So this means two things. One is the resolution on the particle surface. The other is basically the pre-triggered collision distance, right? As we said, we use 4 times of the background cell edge length as the pre-triggering distance of the particle collision. So this one, the collision distance will be 0.1 of the particle diameter. Where for the setup 2, the collision distance will be 0.05 of the particle diameter. So basically, here are two things that is changed in this case. One is the resolution, and one is the collision distance. And here also the symbol type. Basically, it will correspond to the results that I was shown before. I will show afterwards. And after giving the information of the different numerical setups, firstly, we did the simulation, the particle result simulation using our immersive bonding method for stationary, which are motionless particle suspensions here. And here we compare with 2 very typical correlations for stationary particles proposed in the literature. The reason for choosing those 2 correlations has 2 aspects. One is that those 2 correlations has been widely adopted by previous investigators for either comparison or just adopted in the CFD-DEM simulation. The other one reason is that those 2 guys, they also adopted their code for freely evolving suspensions. And the figure on the right basically shows the comparison of the suspension average drag force in the whole suspension, right? Yeah. And the x-axis is the Reynolds number, while the y-axis is the normalized drag. And the different lines basically corresponds to different correlations, while the different colors from bottom to top are the solid volume fraction from 0.1 to 0.4. So what we can conclude from this figure has 2 things. One is that we can see, right? Basically, the markers with different types just collapse on each other, which means neither the domain size nor the grid resolution affects the drag in stationary particle suspensions. The other comparison is the comparison with the correlations. What we can see is that our results agrees well with the correlation results at different solid volume fraction and the Reynolds number. So here is the comparison for stationary suspensions. Then followed by this, we performed the simulation for freely evolving suspensions. And here's an example of how the particles evolve and how the flow field develop in that suspension. Basically, the animation on the left shows the movement of the particles with respect to time, and the colors are the pressure distribution on the particles. And the animation on the right shows the evolvement of the flow field, which is the free stream direction flow velocity in the suspension here. And this is just the illustration of how the results works in our simulation here. And then we also did the comparison of the suspension average drag, and the different lines still corresponds to the correlation for stationary suspensions. We just want to see, like, with the mobility added to the particles, how the results differ from the results from stationary particles. And what we can see, basically 3 figures from the left to right are density ratio, which is the solid density divided by the fluid density from 2 to 10 to 100. What we can conclude from those comparisons is that at solid fraction of less or equal to 0.2, basically the drag is not affected by the inclusion of the particle mobility. When it goes to solid fraction of 0.3, we can see the drag, right? The blue one. The drag is much enhanced due to the inclusion of the particle mobility. Well, when it goes to the solid volume fraction of 0.4, right? We can just look at the circles, which is a base case, right? We can see our results just goes back to the solid curve, which means the drag is not affected again by the particle mobility when the density ratio, when the solid fraction goes to 0.4. But here's one special case, which is the down triangle. This one corresponds to the setup 2, which has a much finer grid resolution, right? We can see when using a much finer gray resolution at source fraction of 0.4, the drag is much improved comparing with the case with using the gray resolution of 1/40. So before investigating the reason behind this, the first thing we want to do is compare our results with the correlations proposed in literature for freely evolving suspension. Here we chosen three correlations for comparison. The first two are proposed based on freely evolving suspensions, while the last one, proposed by Huang, they assigned random velocities that obey the isotropic Maxwellian distribution to the particles in the suspension, mimicking the effect of the particle movement in freely evolving suspensions. And they also use different parameters to quantify the particle mobility. Basically, the Tavaneshant used the density ratio, which is the rho s divided by the rho f, while the Tang and Huang used the RET, which is a Reynolds number based on the granular temperature to account for the effect of the particle mobility here. And firstly, we did the comparison for the results at a solid Warm fraction of less or equal to 0.3. The reason to do this comparison firstly is that the reason in this solid fraction range is not affected by the gray resolution or the domain size here. So we only present the results from the base case. And what we conclude from those comparisons is that basically the dashed lines are the results from Tang. So what we can conclude from those comparisons is that Tang's correlation significantly overestimates the drag, while the correlation from Tavaneshant and Huang agrees well with our current PR's results. And lastly is the comparison at a solid fraction of 0.4. Here we only compare the results with the correlation of Tavaneshant and Huang. And if we compare the results with Tavaneshant firstly, which is a solid line, we can see its results agrees with the down triangle very well. While the down triangle results corresponds to the 1/80 gray resolution, and the dashed line and dashed line both corresponds to the results corresponds to the correlation of Huang. Why it has two lines is that in our simulation for 1/40 and 1/80, basically the particle mobility, which corresponds to the granular temperature, also differs. So using Huang's correlation, it will derive two different results for the different numerical setups. We can see basically Huang's correlation can both captures the variation in drag from the base case and the setup 2. And basically this one is the comparison for the drag. And finally, we want to investigate why the drag is improved at 0.4 when the gray resolution is improved. Firstly, we want to investigate its effect on the particle distribution to see if it is causing more clustering or making the particles to distribute more homogeneously. And here we use the radial distribution function to quantify such parameter. And what we conclude from this one is that we see that using different gray resolution or the different domain size, it doesn't have much significant effect on the radial distribution function, which means the different numerical setup doesn't affect much the particle distribution. And this is one aspect of comparison. And inspired by the comparison with Huang's correlation, we want to say maybe the increase of drag at a solid fraction of 0.4 is caused by the enhanced particle mobility. So here, to quantify the particle mobility, we use the granular temperature here. And the top equation is the definition of the granular temperature. And the below one is the Reynolds number defined based on the square root of the granular temperature. And what we can see from those figures is that the granular temperature at solid fraction of point equal to or less than 0.3 basically follows the same trend, and it's not a function of the solid fraction. When it comes to the solid fraction of 0.4, however, if we look at the circles, right, the granular temperature, the Reynolds number based on granular temperature is much lower than other solid fractions, which means at solid fraction of 0.4, if we don't do anything, we just keep the same gray resolution, which is 1/40, the mobility of the particles will be much confined. And we can also see an up triangle here, and it is just similar to the results for the circles, which means, and this up triangle corresponds to the case with larger domain. So this means that you increase the domain size won't affect the particle mobility here. If you look at the down triangles, the gray down triangles, we can see it agrees quite well with this approximately linear curve, which means the increase of the gray resolution will enhance the particle mobility and making it follows the same trend as higher surface fractions. And then we conclude that the enhance of the drag at surface fraction of 0.4 from gray resolution of 1/40 to 1/80 results from this enhanced particle mobility here. And here are basically all what we've done for this aspect of research. And finally is our small conclusions that's derived from this. The first one is just what we said, right? The increased domain size from 5 by 5 by 5 to 9 by 9 by 9 doesn't affect the suspension aperture drag. And secondly is that the drag enhancement from 1/40 to 1/80 results from the enhanced particle mobility. And this one basically combines with the third conclusion that explains such reason. And finally, is our conclusion is that Tavanashian's correlation agrees with current PRS data well at surface fraction of less than 0.3, whereas Huang's correlation reasonably captures the variation of drag from domains using different gray resolutions at surface fraction of 0.4. And basically, those are all I'm going to present. Thank you.
Thank you, Dr. Chow. In the interest of time, I'm going to hold off on questions for this presentation, but if you can engage directly with Dr. Chow through the chat or through email, that would be fantastic. Thank you.
Okay, thank you.
Our next presentation is from Dan Sun from the National Institute of Clean and Low Carbon Energy. And he's going to give us a talk on the numerical study of fluidization of binary mixture of particles using SOM KTGF-MP. When you are ready, sir, please begin.
Hello. So can you hear me or see my presentation, please?
Yes, I can hear your audio and we see your presentation. Okay,
thank you very much. So in this presentation, I'm going to talk about numerical method which in the Euler framework used for the fluidizations with the binary mixture of particles or different type of particles. So this model is called the second order moment of kinetic theory of granular flow for multi-type particles. Yeah, so the advantage of this Euler method, KTGF model in the fluidization actually can be easily adapted to the large scale simulations. For example, in this reactor, the height of the reactor is in tens of meters, and we account the particle inside the reactor by the weight of tons instead of the numbers of particles. So, but the challenge of the Euler method for the fluidization actually was how to predict the multi-scale structure inside this fluidized risers. So there are clusters inside this fluidized riser, and there are suspended particles dispersed inside the fluidized riser between the clusters. Professor Lee proposed the numerical models as to calculate the clusters and disperse particles separately using their own drag force strategies. So in their approach, they use the dense phase to represent the particle clusters and use the dilute phase to represent the dispersed particles suspended between these clusters. KTGF model as a Euler method can predict perfectly when the particle concentration is high. For example, in this bubbling fluidized bed, we can see the KTGF model can predict the location, size, and shapes of these bubbles inside this bed perfectly. In the literature research, I found that the classic KTGF is hard to predict the velocity of particles well. If we look at this line, so we can see that the classic KTGF method can predict the gradient of the particle velocity. So these are in this horizontal channel. So the volume fraction of the particles is in the range of 10 to minus 4 to 10 to minus 3. So when we use the second order moment kinetic theory of granular flow, we can see that the particle velocity profile are perfectly predicted and agreed well with the experimental data. We can also see that the bottom figure shows the particle distribution, their distribution of particle concentrations. We can see that using the second order moment of KTGF, the particle distribution improved as well. So the difference between the classic KTGF and second order moment KTGF is how to calculate this shear stress in the momentum equations for the particles in KTGF. So this shear stress in this momentum equations are comes from the 9 diagonal term of this second order moment of fluctuation velocity of particles. In the classic KTGF model, we calculate this shear stress using the pseudo viscosity times the full gradient of particle velocity. So this was based under the Bosniak hypothesis. When the particle volume fraction is high in the dense phase region, so this Bosniak hypothesis can be easily satisfied with the frequent intercalation between the particles. But in the dilute phase, when the volume fraction is lower, we have to use the full partial differential equations to solve the shear stress, to solve this second order moment of the particle fluctuating velocities, so that we can predict the particle flows in a dilute phase perfectly. So these are the examples of the simulation results using SOM KTGF. So in this bubbling fluidized bed, the SOM KTGF can also predict the shape of the bubble perfectly. So also in this SOM KTGF model, we can also predict the second order moment in each direction. We can also calculate the ratio of the normal components of the second order moment. So we use this ratio as the anisotropic turbulence ratio. We can see that in this bubbling fluidized bed, when the particle concentration is higher, this anisotropic ratio is in the range of 2 to 1. But we can see these dots, these are the particles when the volume fraction is lower than 0.01. So in this region, this anisotropic ratio is really high. On the right side, it gives the shear stress from a simulation in the fluidized riser. The black dot gives the calculation for the shear stress use the classic KTGF method. The red dot was predicted by the PDE in SOM KTGF. We see that the normal stress predicted by both methods are closer to each other, but the shear stress predicted by the classic KTGF is much higher than the shear stress predicted by SOM KTGF, especially in the lower, in this region, when the volume fraction of particles is lower than 0.01. So these are the applications of SOM KTGF applied in spotted fluidized bed and the fluidized risers. So SOM KTGF increased the fluidity of the prediction. We can see that this method can describe the interface between the spotted zone and annular zone. when we apply the SOM KTGF in the fluidized risers, it's also discovered that the anisotropic ratios of the turbulence intensity behave different in the dilute phase and the dense phase. Also, we can see when the volume fraction of particles increase. In the dilute phase, the anisotropic ratios of turbulence intensity increase with the volume fraction of particles, but in the dense phase, inside these particle clusters, the anisotropic ratios of turbulence and intensity decrease. Actually, from the previous simulation, it's evidence that the second order moment KTGF can predict bubbling fluidized bed, spotted fluidized bed, and fluidized riser in high fidelity. And it's also evidence that they can be predict both the dense and dilute phase in high resolution. So next, I'm going to talk about the second order moment of KTGF derived for multi-type particles. So this new method was derived based on the second order moment KTGF. And the interaction between particles and different types of particles was derived based on the binary relation between particles from the kinetic theory. In these equations, these pink terms represent the exchange of the momentum, exchange of energy between particles and between different types of particles. And these blue terms gives the flux due to collision. If we look at this flux due to collision in the momentum equation, for example, so on the left is the expression of the flux due to collisions in the momentum equation. So if we do the tensor construction, so we can achieve the expression which is the same as the classic KTGF for multi-type particles proposed by the, Professor Ostober's group. And if we assume that the two types of particles, L and M, are the same in this SOM KTGF MP model, we can achieve the same expression, which is from the SOM KTGF for the single types of particle. Using this SOM KTGF MP model, we did some simulations of two types of particles in fluidized riser. So in this case, the size of particle, the size of two types of particles are different. And on the right side, we can see that this new Euler method can predict the velocity distribution great with experimental data. We can also see that this numerical method can predict a slight difference of the particle velocities between these two sizes of particles. In this case, we can see the two types of particles, the velocity of two types of particles and the distribution of two types of particles are close. So they are moving together upwards. So next, I give the example of a prediction of particles with the two different densities. We see the high densities of particles mostly located at the bottom of the fluidized riser, and the lower density of particles moving upwards, and his volume fraction is higher than the high density of particles in the region above, near the top of the fluidized bed. On the right side, I plotted the normal stress of these two types of particles. So we see that this granular temperature normally increase when the volume fraction increase. So when the volume fraction decreased, on the right side give the anisotropic ratio of the second order moment. So we can see that when the volume fraction increase, this anisotropic ratio decrease. So especially we can see when the volume fraction lower than 0.01, this anisotropic ratio is increased sharply. So in this presentation, I propose a numerical method based on the kinetic zero granular flow, which is as a Euler method applied to simulate particle flows in fluidization. So second order moment of kinetic theory of granular flow is essential in the dilute phase of particles in fluidization, especially when the volume fraction of particles is less than 0.01. The second SOM KTGF for multi-type particles were further developed and derived based on the kinetic theory. So this can be used to predict particle flows with the various types of particles with different densities, diameter, and other properties in the numerical framework. Thank you.
Thank you, Dr. Sun. You had some beautiful data to share with us there. We do have time for one question. If there is anything in the chat, Arthur? I don't hear him chiming in. So I'm going to direct people to use the chat for questions, and in the interest of time, we'll continue to the next presentation. Thank you again, Dr. Sun.
Thank you.
Next, we'll hear from Arif Ozdemir, who will be presenting on CFD DEM modeling of conical spouted bed solar receivers. Please.
Can you see my screen?
Not yet, sir.
Can you hear me?
I can hear you, but I cannot see your presentation.
Sorry for that. Now?
I see your PowerPoint, but it's not in presentation. There we go. You're ready to go.
Okay. Good morning, everyone. Welcome to my presentation. I am Alper Özüme from the Mechanical Engineering Department of Hacettepe University in Turkey. My topic today is CFD-DM modeling of conical spouted bed solar receivers. This presentation is structured as follows. Firstly, I will give a brief introduction about concentrated solar power systems and spouted bed receivers. Then I will slightly deep into CFD-DM modeling, and after that I will give you some numerical and experimental results. Finally, future works will be discussed. As you all know, worldwide energy needs have been shifting to renewable energy source due to climate change caused by fossil fuel usage and energy shortage. Solar power is seen as a promising solution, and it is the cleanest, most abundant, and one of the most accessible renewable energy source. And CSP systems is a type of system that aims to reduce carbon dioxide emissions, and it can allow capturing of solar radiation in a heat transfer plate by using a series of mirrors. And these are the types of CSP pylons. Among all these, solar power tower is commonly in use. In CSP systems, there are three receiver types. In today, molten salt is commonly in use, but it has a very limited operating temperature. Gas systems are really used due to their poor thermal properties, and solid particles that we are going to use offer high temperature range and cheaper than the other options. And these are the examples of solid particle receivers. As you can see on the screen, fluidized bed or spouted beds can reach very high operating temperatures. Before we start modeling section, I would like to give some information about spouted beds. Spouted beds is an alternative solution to fluidized bed that has bed slugging, and it was invented in 1954. Its movement is based on the coarse solid particles with fluid injection and commonly used for coarse and heavy particles. There are three regions which is important in spout beds. This section is, as you know, spout region, and there is interface region between this section, and towards the wall we have annulus section, and this is the fountain line. It is important for our later analysis. Spout beds has an advantage for use of CSP systems, such as it can reach very high temperatures and it can handle coarse and heavy particles typically used in CSP applications. And in this slide, properties of solid particles are presented. In CSP applications, common solid particles are silica sand and ceramic propans, or in other words, carbo-HSP. Olivine is also a major candidate for CSP usage, since thermal properties and composition is similar to carbo and silica sand. One of the major advantages of the use of olivine for us, olivine can be found in large quantities in Turkey, so it is very cheap for us. As you can see in the slide, objectives are presented. Our main target is develop a CFD-DM model using MFIX open source software program to model our CSP plant. In the literature, there is no specific study to model CSP systems using discrete element method, although some of two-fluid model studies exist. Secondly, to develop to compare this model results with our in-house experimental data and expand our CFD-DM model with thermal radiation. As I mentioned before, in this study, MFIX open source software programs have been used. Due to our working particle diameter is too small, traditional DM requires large computational time. To save time in this work, coarse-grained particle method was used. Coarse-grained particle diameter is a method which specifies a specific coarse-grained particle diameter, and at this coarse-grained particle diameter range, particle behavior was the same. Also, our in-house post-processing code was used for the construct some particle velocity profiles and solid volume fraction profiles. Before the modeling, I would like to introduce small DM equations. In CFD DM, gas phases and solid phase of the particles solved separately. To solve gas phase equations, we use Navier-Stokes equations. So this first equation is about momentum conservation, mass conservation, and second one is about momentum conservation. In order to solve solid phase equations, we use Lagrangian dynamics equations. To model forces on a solid body, we use contact forces and drag forces and gravity forces. And there is lots of model is available for model drag and contact forces, but to keep this presentation as simple as possible, I will skip that section, but we will use it later. This is the cross-sectional view of our conical spouted beds. Used particles are almost filled the bed, and gas velocities measured from 70 millimeters above from the bed inlet, and our simulation time is around 5 seconds. As you can see, particle mean diameter is too small. As a result, we have to use coarse-grained particle diameter. And as you can see, particle density is quite high for the literature, in the literature review. And this is the mesh which is created in MFIX. Structured cells have been used, and around 18,000 cells have been used. And these are the solution case. In our cases, effects of drug model, this one is case 1, case 2, and case 3, and effects of coarse-grained particle diameter have been observed. And as you can see on this section, number of particles is too high, so we use coarse-grained particle methods, and some of DM parameters presented in here. These are the simulation videos of 3 different drug models. We will discuss later in some plots. Resolution is not too good for this case, but we can say that in visual point of view, fountain heights differ from each other. And before the comparison, I would like to introduce our small experimental setup. In this experimental setup, minimum spouting velocity, pressure drops, and interstitial gas velocities were measured. We used differential pressure transducer and pitot tube for measurement system, but our pitot tube was recalibrated to measure the gas velocity of the annulus section, because original calibration equation of pitot tube gives unrealistic solution in annulus section. For if you're interested for more detail, you can visit our reference one, which is completed in our laboratory. And these are the bed pressure drops. This data is taken from MFIX results, and this MFIX results compared with empirical relationships. As you can see, Hidaspol's predictions are higher than the others predictions. In general, pressure drop does not affect too much for changing particle diameter and drug model. As can be seen from these figures, interstitial gas velocities, interstitial gas velocity profiles of different cases are compared with experimental measurements. Both drug models, left-hand side, as you can see, nearly catch the experimental trend line in left figure. However, especially in the spout region, which stands in 0 point, Hidaspol's drug model prediction is more accurately, since Hidaspol drug model estimation is more suitable for dense systems. They can use combination of ergon and Van-Heu's equation for the momentum exchange coefficient. Also, the smaller size of coarse-grained particle diameter predicts more accurately than the other sizes, with slight differences, as you can see in the right-hand side. However, reducing coarse-grained particles diameter increases the number of completed particles, and as a result, computational time increases dramatically. In addition, particle velocity and solid volume fraction profiles don't differ significantly from each other, as you can see in these figures. However, the effects of drug models and coarse-grained particle diameter can be seen easily in spout region. And unfortunately, experimental measurements of these profiles are not completed yet, so we cannot compare directly which drug models suits the best. In conclusion, our 3D coarse-grained ZTDM model was developed and implemented in MFIX or conical spout beds. And we saw that olivine has a potential candidate for bed material, and our model results of interstitial gas velocity profiles catches the experimental data, and we saw that drug load and coarse-grained particle diameter affects the results too high, especially in spout region. In future, experimental measurement of particle velocity and solid one fraction will be done. Our research group have experience about this measurement using optical fiber probe, and real CSP conditions with incoming radiation will be simulated in order to obtain temperature distribution. These are my references, and thanks for listening. That's end for me.
Thank you very much for your presentation, and thank you for advertising MFIX. We like to see that at this seminar.
Thank you.
Does anyone have a question for Dr. Özdemir?
Marianne, this is Arthur Conan. I don't see any question in the chat, but there is a comment from William Fulmer. Should I read it?
Yes, please.
Okay, so it's written that just FYI, if you do a Google Scholar search for Aaron Morris from Purdue University, he has a paper or two on CFD-DEM application in solar receivers.
Okay, I will look at it.
Excellent. I do have a question myself. Did you consider using MFIX's PIC model in any of this work?
Sorry, can you say once again? I didn't hear it.
Did you consider using MFIX's PIC model in any of this work as a way to reduce your modeling time?
No.
Maybe you and I should talk about that offline.
Yes.
I can help you with it. Okay. Well, if there are no more additional questions for Dr. Özdemir, we're actually on time to have a break. So a miracle occurred in the last an hour and a half and we caught up. So if you will, take 10 minutes for an exercise break, stand up, stretch, and we'll meet back at 10:50. Hello again, everyone, and welcome back. I hope you had a nice break, a good stretch, and are ready to settle into some more presentations. Neil Raj is now going to give us a presentation on units for flow field and drag force predictions in dispersed particle flows. My voice is not cooperating with me today. Neil, are you ready to go? You are audible and I see your PowerPoint, and now you're in presentation mode.
All right. So let's see. All right. Okay. So good morning, everyone. So I'll be presenting my work, which is titled as Units for Flow Field and Drag Force Predictions in Dispersed Particle Flows. This is a work by me, my advisor, Dr. Danish Tafti, and another collaborator from Stevens Institute of Technology. I'm sorry, I didn't list that name out here. All right. So why am I not able to go to the next slide? Excuse me. All right. What was that? Okay. Is there a pointer? Am I not seeing here? Okay. Anyway, I see it. All right. So to introduce of my work, I'm sure most of you are aware of like places or instances where we see fluid flow through an array or a random array of like solid particles. I've shown a few instances over here. Flow through porous fibers, fluidized beds, flow through porous media are like a few examples of where we see systems like this. Now, the aim of my work is basically twofold. One is, can we make some machine learning based surrogate models to give us a quick estimate or a quick prediction of the velocity and pressure fields in these flow systems? And secondly, can we use those predicted fields and to do some downstream task, which in this case is drag force prediction, but can it be for some other applications as well, like surface heat transfer, skin friction coefficient on the surface of particles, and so on. So with that, let's move into the grand idea of what I'm trying to do over here. So if I draw your attention to this part of the slide. So this is the computational domain that we are working with. It's a random array of prolate ellipsoids of aspect ratio 2.5, and the idea is we take a 3D part of this big 3D domain, which is centered around a particle. We represent that image using some we represent that space of the entire domain using some geometric input representation, and we pass that information to a unit model. And can we predict the x, y, z velocity and the pressure field surrounding that particle of interest, right? So now coming back to the computational domain, the mean flow is in the x direction. So it's developing in the x direction and it's periodic in the y and the z directions, right? So as I said, we take a 3D part of this entire domain, and we will discuss what is the geometric input representation in detail, and we pass it through a unit. Now, again, in the interest of time, I'm going to give a brief description of what the unit is. So it has two parts, the encoder and the decoder. So what's happening in the encoder side is we're giving the input, we're applying successive double convolution operations, and we're reducing the dimensionality of the input tensor. And in doing so, we are the model is learning how to get some. It's learning the important details of that input representation and throwing away any irrelevant information. Now, in this bottleneck layer, we additionally provided more scalar inputs. So now, since this is just geometrical information, the model is not aware of what's the Reynolds number, the mean Reynolds number of the flow field, or the global solid fraction of the flow of the computational domain. We provide that information through these tensors here, and we upsample, which is not surprisingly, just the opposite of the downsampling double convolution operation, and we bring it back to the original size, right? And another key feature of unit models is skip connections, which is basically concatenating these two tensors and then performing the upsampling operation. Right. So with that, let's discuss a bit about the data set that I'm using. So as I mentioned, it's prolate ellipsoids of aspect ratio 2.5 randomly arranged, and we do three different we do three different geometries of three different solid fractions of 0.1, 0.2, and 0.3, right? And for each of those solid fractions, we have four different Reynolds numbers, RE 10, 50, 100, and 200. Now, our testing data set, which is where we'll be discussing all of our results in the upcoming slides, is by taking 40 particles from each of these experiments. So when I say an experiment, I mean a simulation characterized by its characterized by its solid fraction and the Reynolds number. So we take 40 particles from each data set as our validation data set, and we train on the remaining all the remaining particles in one time, right? Something further is the drag forces, which you can see, and inset within each drag force plot, the distribution of the drag force plot. We have an example of how a slice of that domain would look like after performing the CFD simulation or the particle result simulation. This is for solid fraction 0.1, this is 0.2, and this is 0.3. And one thing you can notice with the drag forces, and it's a kernel kernel density function. So with the lower Reynolds number, obviously the mean is lower, but it's also the variance is also much lesser. And as we're increasing the Reynolds number, the variance and the drag forces is also seeing an increase. All right, so I mentioned that we will discuss about the geometrical input representation, and what we use here is something we call as we give a phi channel input, which we call as the phi channel input distance function, right? So you might have all heard of the word distance function. So it's zero inside the particle, and for any fluid pixel outside the particle, the value is basically the distance to the surface of the nearest particle. And that's what in this work we define as the first distance function. And for the second distance function, the value at any fluid pixel is the distance to the surface of the second nearest particle, and so on, third, fourth, fifth, right? So basically this encodes information about the local neighborhood of the particle, and we'll see how that will be much beneficial to the unit model, right? Now, excuse me. Yep. So we make a classification on the inputs to the network. So the first one, we give it a very simple binary input, which is just 0 wherever there's a particle, and it's 1 wherever there's a fluid. And that is one method. We pass that information to the unit, and we predict the velocity, the flow field quantities. In the second, we provide the phi channel input distance function, pass that to unit, and we observe how we do the quantity, how we predict these quantities, right? So let's look at one case of a qualitative prediction of these two methods. And this particular image that you're seeing has been taken up from RE10 for solid fraction equals 0.1 dataset. Now I would like to remind that everything that we're doing here is three-dimensional, but for like representation purposes, I'm only showing you like one slice of a 3D domain. So the particle in between is basically the particle of interest. The entire 3D domain is centered around this particle. So I mean, obviously it's cut in between, so it's not really visible. It doesn't look like an ellipsoid, well, because it's not a 3D image. So the first row is the ground truth dataset. That is something we have got from our PRS simulations. The first column wise, we have the x velocity, y velocity, the z velocity, and the pressure. And we have on the second row, we have the binary input methods for the corresponding flow quantities. And finally, we have the phi channel method. Now, qualitatively, they may all seem doing pretty well. But if you notice, if I draw your attention over here, let's look at probably this region over here, the high velocity front, right? In this ground truth field. The binary input map was not able to capture that, but the phi channel input distance function was able to do that. That's something you might notice even, let's say, in the z velocity. There's another high pressure region, a high velocity region over here, which the binary map was not able to capture very well, but the phi channel method was able to do that well. So the idea I'm trying to portray is like the unit model will perform as good as the input representation you're giving. And this phi channel input representation gives a better embedding, so to say, about the neighborhood of this particle of interest, and thus we see better predictions in the velocity field. Now coming to the pressure field, so the binary method has performed really worse in terms of the scales of the prediction. And similarly, I mean, it does look like the phi channel method has performed well over here, but that's actually just an exception. It's not the norm, as we will see in the next slide. So we can measure the errors in a quantitative manner now, and the metric that I've used over here is the R-square, which is just the sum of the residuals divided by the total sum of the squares, and 1 minus that will give us the R-square. So as you all might know, an R-square equals 1 is a perfect prediction, R-square equals 0 is bad, and in some cases we have seen R-square is equal to negative, which is very bad in the sense like even a horizontal line is doing a better prediction, or doing a better prediction than what the model is predicting. So the first row, we see the x, y, and the z velocities, and the blue curve is for the phi channel method. And so the x-axis is basically the particle ID. So we had a validation data set of like 40 for each experiment. We are just taking one experiment, RE10 and solid fraction 0.1. And we see that the R squares are much better for the phi channel method compared to the binary method for all the three velocity cases. For pressure, though, we see that both the models have performed really bad. Like there are certain cases where it's able to guess the velocity, the pressure pretty well, but it's as I said, it's just an exception, not the norm. So why do we see this happening, right? And we went back to our CFD simulations, and we noticed this that so the pressure field inherently has a gradient in the x direction. This is because of the way, this is because of the boundary conditions that we're setting up. We have a developing flow in the x direction, so obviously there's a pressure gradient there. And then we have periodic in the y and z. So if I take, so this plot that you see over here is a mean plane-wise pressure in the streamwise direction for different Reynolds numbers, right? So what that means is if I take, as I mentioned, the flow is in this direction, and if we take a plane in the y, which is perpendicular to the x direction or the yz plane, and if we take a mean of the pressure at that plane and we plot it versus the streamwise direction, we see, obviously, if there's a flow in that direction, there should be a drop in the pressure, right? So inherently, the pressure, the pressure distribution is the value of pressure rather is a function of x, and that's not really the case for the x, y, and z velocity. So now, since this channel of information was inherently different, the unit model was really struggling to predict the pressure field, despite us scaling the field. So now, what could we do for that? Like one way is like we provide the x location to the unit model, and hey, this is a particle, this is at the x location, give me estimate of pressure. Now, while I've not shown the results for that, and we just found that it did as bad as what we are doing, even when we don't provide the x location. So what we did is, instead of training on this pressure, which I will henceforth refer to as the total pressure, we predicted on the fluctuating pressure. And the way we calculated the fluctuation pressure is, again, we took a mean, planar mean, and we subtracted all the pressure at that plane by this planar mean. So something like this, P flux, which is a function of x, y, z, is the P total minus the planar mean at that x location. So this is an example of the total pressure, and this is an example, and if we remove the mean and we're just looking at the fluctuations, this is how the fluctuating pressure would look like. So now we do a classification. Now, since our inputs, we notice that, hey, a phi channel input does so much better than a binary. We proceed with the phi channel input, and now we make a classification based on the supervision. So do we supervise it on the total pressure, or do we supervise it on the fluctuating pressure, right? So this is another qualitative prediction, and this time we choose a particle from RE200 and solid fraction 0.3. Once again, the particle in the center is the particle of interest. The 3D image is centered around that particle. We just show one slice of that 3D image. So we have already gone over the x, y, and z velocities. So now let's look at pressure. And we do notice, right? Like, so the first row is the ground truth, and the last row is the fluctuating pressure method. And we see there's these two correlate really well. And when we're using the total pressure, once again, the scales of the pressure predicted are just completely off. And right, and while we look at the quantitative errors, once again, we use R square. And again, for the x velocity, now the two different methods is the total pressure method and the fluctuating pressure method. And there's not a significant difference in the velocity predictions, but in the pressure predictions, we see that it's done like nearly well. Like R square values are close to like 0.96. All right. So for both these cases, I described I just taken the validation data set for a particular experiment. And now let's see that how are these R squares varying across different experiments, right? So as I mentioned, for each of my experiment, I had 40 different particles. I predict the velocity and the pressure fields for these 40 different particles. I calculate the R square on each of them, and then I get a mean over all those 40. And that's what you're seeing. The mean R square is on the y-axis. On the x-axis, you see the solid fractions. So we see a common trend across all of them, right? Let's, for instance, focus on x velocity. So the thing that we notice is as we're increasing the solid fraction, our predictions are getting better. And as we're increasing the Reynolds number, which is these different plots that you're seeing, the predictions are becoming worse. So essentially, like the best predictions we're seeing at like Reynolds number 10 and solid fraction 0.3, and the worst predictions are at solid fraction 0.1 and Reynolds number 200. That is true for like the XYZ velocity as well as the pressure. All right, so now to the second part of what I discussed, units for drag predictions, right? So this is something I presented in, I think, 2021 in NETL, where I'd given some input in the form of a phi channel distance function, which I discussed right now. I provided it to a convolutional neural network model, which again, in the interest of time, I'm not going to go over that a lot. I'm not going to go over that, but essentially, like it's some deep learning model. We give it a phi channel, just a geometrical information about a particle and its neighboring regions, and we predict the drag forces, right? What we did right now is, okay, we use that same geometrical information, we get the predicted velocity fields, and we provide this predicted velocity and pressure fields, and we provide this predicted velocity and pressure fields to the CNN, and we ask it to predict the drag forces. And we should expect that to do better, and we did see that. The metric that we have used over here is the mean relative error. So it's the ground truth drag versus the predicted drag over the ground truth drag, and it's 1/40 again for each experiment of the total 12 experiments, right? So the red bar curve indicates the mean relative error using method 2, wherein we provide the predicted velocity and pressure fields, and blue curve is for the errors when we're using only the phi channel distance function. And we do see that there is certainly an increase in performance when we're using the predicted velocity and pressure fields, as we would expect. I mean, if you're providing the pressure and velocity fields, it's essentially the model just needs to learn how to integrate over the surface of the particle of interest and calculate the drag force. All right. So to conclude my work, I think one of the main important takeaways was a phi channel input distance function outperforms like a binary input. And this is important because I still see a lot of papers where people are still using binary inputs for some deep learning models, but when you're giving some information like a distance function, it clearly improves the model. The errors in the predicted fields increase with the increase in Reynolds number, but decrease with an increase in the solid fraction. So the more dense our system is becoming, the deep learning model is sort of able to do better over there. And if we are working with developing flows, it's much easier and it's much more accurate to train on pressure fluctuations than the total pressure fields. And the drag prediction task accuracy is improved by pre-predicting the velocity and by pressure and the velocity compared to directly providing it the distance function directly. So for future work, so one thing that you might have noticed in these predictions is we are actually working on a much more coarser scale, right? The particles that you see over there are pixelated. And the reason for that, I mean, that's obviously not the grid sizing that we have used in the CFD simulations. It's just that using that same level of spacing, it's going to be the image that we'll be using to train the deep learning models are going to be much more bigger, and thus it'll take much more time to train. So we're using a coarser sampled version of the CFD simulations. So super resolution is one thing that we can add on to the model, and a global input representation is another thing that we're looking at. So that's what that really means is that so currently the predictions that we're making, they do conserve mass and momentum, but sometimes they are still different from what the actual predictions could be. If I just go back to one image over here, so the ground truth field looks something like that, but the predictions, if you notice, there are extremely higher gradients of velocity over here, but Over here, the flow field seems to be, the velocity flow field, the x velocity flow field seems to be a bit more diffused. Now, this is not to say that this flow field is unphysical, because as I'd mentioned, like if you calculate the continuity or the mass conservation, it actually does conserve it. I mean, these flow fields are still legitimate. The reason it's deviating from what the ground truth prediction is because, well, it doesn't have any idea of the boundary conditions. It doesn't know like what the approaching velocity front is. So it's making a guess of what the approaching velocity front is. So giving it a global representation of what the entire suspension domain is going to be like, I believe would like really improve that. And yeah, with that, I would like to end. Thank you so much for your time, and I would be open to any questions.
Thank you very much, Neil, for your presentation. There are a few questions I see for you in the chat,
Sure.
but I'm going to ask you to answer those in the chat
Okay.
so that we can go ahead with our next presentation.
Yeah, sure. Thank you so much.
Thank you. So next is a presentation from Prabhu Balasubramanian. I believe he's here, but we're going to see this as a video. Is that right, Brian? Or maybe it's Jenna Mears?
So we have a video for backup if he's not able to do it live.
I believe he wanted to run the video because he was having difficulty with his presentation earlier.
Okay, yep, I can share that now.
But I do believe he is here and able to answer questions for us later. Is that true, Prabhu?
I'm here with you, yes.
Wonderful.
Yeah,
Oh, thank
I
you.
really like the way you presented.
Okay, thank you.
Hello, I'm Prabhu Balasubramanian. I'm a PhD student at Glasgow Caledonian University. My supervisors are Professor Don Meglianci and Dr. Andrew Cowell. Today I'm going to talk about my experience thus far with modeling fluidized dense phase conveying of Gilda-Tate powders with M6TFM. I'll start with what fluidized dense phase conveying is, where on the phase map is it located, characteristics of the hypothetical Gilda-Tate powder that we have chosen to model, followed by some modeling options and some numerical intricacies that we encountered during modeling, some simulation results at the end. Fluidized dense phase conveying is the mode of dense conveying for fine powders, typically polydispersed Gilda-Tate powders. It's also proven for Gilda-C. In horizontal flow, it's typically a moving bed flow pattern. In vertical flow, it's the circulating fluidized beds, the dense suspension upflow and fast fluidization. A typical system consists of a blow tank, which is essentially a fluidized bed feeder, a conveying pipeline. The compressed air motive fluid enters in at the feed zone, and the emulsion is discharged at the ambient receiver, typically up to a few hundred meters away. The pipeline is predominantly horizontal with several bends. At the feed zone, the pressure is between 2.5 and 4 bar. The solids fraction is between 0.12 and 0.3, and superficial gas velocity is between 3 and 4 meters per second. Along the conveying line, as the air expands for the incurred pressure drop, the emulsion rarefies and the velocity increases. As you can see, the solids flux is very high. It can be as high as 3000, and the solids loading can be up to 300. Recall the S-shaped concentration profile of fast fluidization with a dense zone at the bottom and lean zone at the top, and a transport disengagement height in between. When we increase the gas flow gradually, the bottom dense zone gets leaner and the top lean zone gets denser, and eventually the transport disengagement height vanishes and the concentration in the axial direction becomes essentially uniform. There can be radial stratification though. And this phase map of width captures the locus of the top lean zone in blue color at the bottom and that of the bottom dense zone in green color at the top. And the location where the two loci meets marks the upper transport velocity VTR to this flux of solids flux corresponding to VTR2, the upward transport velocity, is the critical flux. Above the critical flux, we see the dense suspension upflow conditions, and below the critical flux, we go through fast fluidization. Fluidized dense phase conveying at peak flux typically operates at the dense suspension upflow conditions, with F as the feed zone and A as the ambient receiver, and the flow may not transition to dilute phase conditions at the ambient receiver. And as dense suspension upflow operates at similar gas velocities as that of fluidization, but at a much higher solids fraction, the slip velocities are even higher. This is the horizontal flow phase map of ZENS, showing the lines of constant solids flux. For the dense conditions in which fluidized dense phase flow operates, this unstable saltation zone is irrelevant. As we can see, dense conditions at the bottom of the pipe cross-section can coexist with dilute phase flow conditions at the top. The ability of a powder to aerate and retain aeration is critical for fluidized dense phase conveying. And the ability to aerate comes with the width of the size distribution. Powders at the gel.AB boundary may show interchange flow behavior. For example, a wide dispersed gel.B sample of fluorspar may show gel.A behavior, but a narrow dispersed sample of sand gel.A sample may show gel.B behavior. As we have chosen a monodispersed solids to be modeled, we need to be lower in material density and particle size to ensure gel.A behavior. But lower particle size below 55 microns will have cohesion due to van der Waals forces, and lower particle size is also computationally expensive. So as a trade-off, we have chosen 70 microns spheres monodisperse and material density of 1400 kg per meter cube, because this 1400 kg per meter cube corresponds to typical FCC particles, and there is experimental data available for model validation. Isangia et al. Have recently reported S-shaped concentration profile at high solids flux and gas velocities. For the riser diameter of 0.3 meters that they had used, we believe that the solids flux was below the critical flux. We have chosen the Simonen's unifying model for turbulence and granular kinetic theory for the viscous stresses, complemented by the Princeton model for frictional stresses to cover the full spectrum of solids loading. Regarding the selection of the drag models, the project requires the full range of solids volume fractions and Reynolds number up to 100, considering the high slip velocities in dense suspension upflow. And we also need a homogeneous drag model. So among the homogeneous drag models, we have the option between the models based on direct numerical simulation and the empirical models. The direct numerical simulations end up over-predicting drag at the limit of an isolated sphere due to the limitation in computing power and modeling the unbounded condition. The Stennety et al. Model is a hybrid model, but it does not cover the full range of solids volume fractions. So that leaves us with the empirical models. Among the empirical models, the Shamlal-O'Brien model is reported to be inaccurate at near close-pack conditions. And the Gidasco blend model comes up with a transition between Venue and ergon. And this transition is smooth with the arctan function, but it is steep except at solids volume fraction of 0.2 and Reynolds number less than 10, as we can see in this graph. And LBM simulations have shown that the Venue model is accurate up to a solids volume fraction of 0.3, and the ergon model is over-predicting at from between 0.2 and 0.5. So can we shift this transition from 0.2 to 0.3? If we did that with the Gidasco blend model, the transition is even steeper. The Simonen group have proposed this transition between Venue and ergon, considering this steep transition, which is essentially at this boundary between Venue and ergon, Venue equal to ergon boundary here, and the suitability of the Venue model at solids volume fraction greater than 0.3 is not clear. So we are left with the De Felici model, which is not widely used. And when we looked at the DFLHE model, it predicts within 10% of venue in the solids volume fraction between 0 and 0.3. It also predicts within 10% of ergon in the solids volume fraction between 0.5 and 0.6 for the Reynolds numbers of interest for the project in this range, and it underpredicts ergon between 0.3 and 0.5 by about 20% for the Reynolds numbers involved. But that is desirable too, because ergon is known to overpredict in this range. And most importantly, this DFLHE model does not have any steep transitions. So we have chosen the DFLHE model. Regarding wall boundary condition, we have chosen to use the Johnson and Jackson partial slip wall BC with variable specularity coefficient for the cylindrical coordinates and 2D Cartesian coordinates where it's available. And where it's not available for Cartesian cut cell coordinates, we have chosen to use free slip wall BC. Amongst the coordinate systems, our preference was to use 3D coordinates, and we chose cylindrical as it appeared to be the most perfect fit for the wall curvature, and it also offered a rigorous wall boundary condition. Subsequently, in the project, we chose to use 2D Cartesian for the long pipe model to capture the S-shape profile of past fluidization. For computing, we utilized the Google Cloud compute optimized machines up to 56 cores. We ran the case in the cloud in CLI and downloaded the results to the PC for visualization and post-processing. For parallel processing by DMP for the L by D of 125, the geometry it's intuitive, maximum axial decomposition and no radial decomposition. Cylindrical coordinates turned out to be unsuitable due to unphysical solids accumulation at the axis. Bakshi et al. Have documented this for dense bed conditions, and they have proposed an improvement by letting normal flow through the axis, and they say their model is very efficient because you only need a few azimuthal cells. But that is exactly the point. The axial boundary condition is so dominant in attracting the solids that there is nothing much happening in the azimuthal direction. With Cartesian cut cell coordinates with free slip boundary condition wherein the correction factors for the cut surfaces are not applied, we frequently find these small cut cells with higher solids concentration. This can also be perceived with relatively larger cut cells. Peñaya et al. Have observed this back and forth wall-to-wall oscillations in their 1D simulations. We have also observed this radial oscillations in our 2D simulations. Notice this range of the radial component of the solid's velocity varying between minus 0.6 and plus 0.6. Shamlal et al. Have attributed this oscillations to lack of grid convergence. However, fine grid simulations with cells of the order of 10 particle diameter and time step below 10 to the power of minus 5 seconds has not shown any improvement. Notice this range of the radial component of the solid's velocity, it's still in that minus 0.6 to plus 0.6 range. And these oscillations do not respond to the numerics either. With Cartesian 2D grid, the Simon and viscous stress model and pressure outflow BC under default under-relaxation factors, under gas-only conditions, we face this problem of backflow. A statistical experiment with the parameters relevant to gas-only conditions suggested that the V momentum is the most dominant factor, followed by the turbulent kinetic energy, and both should be kept at 1. And this is intuitive because if we throttle the axial momentum related to other factors, then it may result in backflow. And notice this range of wall time for this experiment, which motivated us to do further experiments to optimize these under-relaxation factors. This is the corangular flow in Cartesian 2D. Observe this inlet transition length of 0.5 meters here. This is at a velocity of just 3 meters per second. For cases with higher velocities up to 10 meters per second, we observe this inlet transition length to be up to 3 meters, costing extra computational effort. And also notice this range of the radial component of the solid's velocity, the radial oscillation. This is the typical simulation result for the feed zone at 3 bar. And of course, for horizontal flow modeling, we need 3D coordinates to capture the variation also in the azimuthal direction. We can see dense condition at the bottom of the pipe cross-section coexisting with dilute flow conditions even for this low velocity of 3 meters per second. You can see the inlet transition length of at least 2 meters of extra computational effort. Conditions at the ambient discharge. Notice the inlet transition length. Axially periodic boundary condition is an attractive alternative for horizontal flow. But we had some numerical difficulty in setting up the constant mass gas flux model. To conclude, we located fluidized dense phase conveying on the vertical flow map of width and the horizontal flow map of Zenz. We illustrated the suitability of the defilage drag model for cases with full spectrum of solids loading. We highlighted the numerical artifacts that we encountered with various coordinate systems. We proposed optimum under-relaxation factors to avoid backflow with pressure outlet BC. Here is a wish list that we would like for the M-fixed TFM features. One is the Johnson and Jackson partial slip boundary condition for Cartesian cut cell coordinates. Slip shear lift force model, especially for horizontal flow conditions where you've got strong velocity gradients. Coefficient model for mildly coarse powders to enable modeling Geldate powder smaller than 55 microns. Option to specify fully developed boundary condition at the inlet boundary condition plane, which will help in minimizing the inlet transition length to be modeled. Cited references. Thank you for the opportunity. I acknowledge the support received from the MFIX forum.
Thank you for your presentation, Prabhu, and thank you for the wish list for MFIX TFM and the shout out for our forum that we use. We appreciate that very much. Does anyone have any questions for Prabhu?
Marianne, currently we don't have questions in the chat.
Thank you. Well, I will wait a moment to see if questions come up, but in the interim, I thank you again, Prabhu, for your presentation and particularly for keeping it very tight.
Thank you very much.
Yeah. I believe our next presentations are also being done by video. Is that correct, Brian?
I believe Brian is out now.
Okay, so it's Jenna. So I think the presentations from Christian Milioli are also being conducted by video, but Fernando is here. I believe that's correct.
Yes,
I'm here.
I have the presentation, but if they are able to do it on their end, they can go ahead.
Fernando, do you plan to give the presentation?
No, please run the recorded one that you have there. Thank you.
Okay. Well, as I understand it, there are two presentations from Christian, but I would like to pause between the two in case there are questions.
Now, you'll see that the first presentation is going to take something a little bit more than 19 minutes, and the second one is much shorter. It's about 11 minutes. So I think we can take questions after the second presentation.
Okay, then we'll show them sequentially and then take questions at the end.
That's right.
Okay, fantastic. Jenna, when you're ready, can you go ahead and start the first presentation on effects of particle Froude number on the subgrid behavior of fluidized gas particle flows?
Okay, great.
Okay, so
good morning. My name is Fernando Milioli, and I work at the University of São Paulo at São Carlos in Brazil. In this presentation, I will show some of our latest results on subgrid modeling of gas particle flows under this title over here, effects of particle fluid number on the subgrid behavior of fluidized gas particle flows. Our developments were done on the MFX platform. In summary, we just apply microscopic two-fluid modeling under periodical boundaries to get mesoscale solutions by means of highly resolved simulations. Then, by filtering over the flow fields in the statistical steady-state flow regime, we derive parameters such as subgrid effective drag, filtered and residual stresses. Today, I will expose some of our results exploiting a range of underlying microscale conditions together with a variety of non-local influences enforced through ranges of macroscale conditions. At the 2021 NETL Multiphase Flow Science event, we presented our work under this title over here on the effect of particle fluid number in subgrid modeling of gas solid fluidized flows. Among the conclusions of that work, we stated that before new subgrid models could be derived accounting for particle fluid number, further work would be required to account for higher domain average gas Reynolds numbers and a variety of domain average solid volume fractions. Because in that previous work, we just considered one single suspension condition as for the gas flow, and we considered only one single situation of solid concentration in the flow. Now we need to extend those things so that we can get a better assessment of how fluid number affect subgrid parameters. Well, those goals that we stated above have been achieved, and related outcomes are now exposed here in two presentations. This is the first one, related to this first topic over here. Here we have results accounting for ranges of domain average gas Reynolds numbers and solid volume fractions for a range of particle fluid numbers. We are going to present some results here and give some analysis on that. And a second outcome was this, the new subgrid models for effective drag, filter, and residual stresses that we just proposed. And well, this presentation over here concerns the topic one. We go ahead then with this first presentation related to results analysis. Well, in this slide, we define the subgrid parameters of our interest. We ultimately aim to provide subgrid closures for effective filtered and residual parameters to be applied in filtered two-fluid modeling. This is a typical filtered two-fluid modeling formulation. And the parameters of our major concern are those here at the right hand side. This is the drag coefficient correction that we call 8. This is the filtered pressure of the solid phase. This is the filtered viscosity of the solid phase. And those guys down here are the residual parameters, the residual pressure, and the residual viscosity of both the phases. And those parameters are, of course, embedded inside this filtered formulation over here. Well, in this presentation, we show how those effective filtered and residual parameters over here, how they behave. We give some light on that. In the presentation to come after this one, we actually will propose some new models, subgrid models. Yes, as said before, we go for the desired subgrid data by filtering over predictions from highly resolved simulations with microscopic two-fluid modeling. And this is the microscopic two-fluid model that we applied. We follow the well-known Anderson and Jackson's formulation with microscopic closures as implemented into the MFX code by Agarwal and co-workers. That's the formulation. The drag, the closure for drag is taken from when and U, and the closures for the solid phase pressure and stresses are taken from the kinetic theory of granular flows of Liu and co-workers, as adopted by Agarwal and co-workers. Here, we have the usual, very well-known formulation of the microscopic two-fluid model. This slide here summarizes the physical conditions and the numerical setup that we applied in our highly resolved simulations. We emphasize in the table down below the underlying particle fluid numbers that we applied between something around 12 and something around 800. We also emphasize here in this table the local influences that we accounted for. This was done through a range of domain average solid volume fractions down here between 0.05 and 0.55, combined with a range of domain average gas Reynolds numbers down here between 1 and 24, around 24. This covers something from a very slow velocity suspension up to something close, like pneumatic transport. The bullets here up there, we show here some numerical conditions that we have applied. First, we applied all periodic boundaries as suggested in this figure. Where we have considered a domain 16 by 16 centimeter size. We consider 128 by 128 grids, giving a grid cells of 1.25 by 1.25 millimeters. We considered filter sizes up to 4 by 4 centimeters. Well, here we have an example of a snapshot of the mesoscale flow field solution that we get from our simulations, over which we apply filtering. The procedure of filtering and binding is quite usual, well described in literature. A box filter sweeps throughout the whole domain through successive snapshots inside the statistical steady-state flow regime, while collecting inside averages or filter data. And this data is classified by narrow ranges of mesoscale markers, while at the same time statistically merged. We apply a double marker bin here, taking the filter solid volume fractions I said down here. Taking the filtered solid volume fraction and the filtered slip velocity in the axial direction as markers. Those are our mesoscale markers. One aspect to mention here is that we filter all the results for all the macro scale conditions all together, so that our final results will be expressed as a function of particle fluid number and filter size, besides the mesoscale markers, those guys here. Well, before we go for the filtered results, let's take a look into a typical mesoscale solution that we have in our simulations. We have here grayscale plots for snapshots inside the statistical steady-state flow regime for 3 different parameters: the solid volume fraction here, the actual gas velocity here in the middle, and the actual slip velocity to the right here. All of those fields for those different particle fluid numbers that we applied. Well, as we can see, well, first of all, this condition here is a very particular condition for a domain average solid volume fraction of 15% and for a suspension, slow velocity suspension condition. Well, as we can see here, the effect of particle flow number is quite clear over the domain heterogeneity here, as you come down here with rising particle flow numbers. The higher the particle flow number, the more dense and thick the solid structures become, while the gas prevailing regions become larger. You can see that thing here as you go for higher and higher particle flow numbers. Well, we can also see that both the velocity fields on those two columns here, both of them respond consistently with the increasing heterogeneity as particle flow number increases, with larger regions of uniformity arising to reflect the larger regions of gas or solid predominance. We can see that you have larger regions of gas or solid predominance and more uniformity for the velocity fields as those regions enlarge as you have a higher particle flow number. Well, here we have some results for the drag coefficient correction. The two graphs over here stand for a particular filter size, for two different values of the second marker, the filtered slip velocity. Each one of those graphs stand for a particular value of the second marker. And the graphs, they show how the drag coefficient correction profiles change with the first marker, the filter solid volume fraction, and with the particle flow number too. We are most interested here in see how those profiles change with the particle flow number. Well, we see that H is higher the lower the particle flow number is. You see, for very low particle flow numbers, the H correction is very high, and when the flow number becomes higher, the correction decreases. This means that we are dealing with a much higher degree of heterogeneity for the lower values of the particle flow numbers. We also see that when we go from this top graph to the bottom one, we go from the higher slip velocity to the lower slip velocity, all the values of H decrease. So the profiles come down for all the particle flow numbers. And we also see that the occurrences of H, they are also more restricted to smaller and smaller ranges of solid filtered solid volume fraction. Well, here we have some results for filtered pressure and viscosity of the solid phase. The conditions are very much the same as in the graphs before for the drag coefficient correction. Many things to emphasize here, but I will touch two things here only. We see that the effect of particle flow number is significant only at its lower values. Here we have big variations between the profiles. When you come for higher values of the particle flow number, these differences disappear. So there is a relevance of the particle flow numbers only for lower values, not for higher values, regarding, of course, this the parameter over here, this filtered parameter over here. And this is true for both the parameters, for the pressure and for the viscosity as well. Other thing is that when we go for higher and higher filtered solid volume fractions, the differences among the profiles become lower, smaller, and this is not very well seen on those graphs, but this is true. It happens for most of the graphs that we got. Well, here we have some results for residual pressure and viscosity of the solid phase. Once again, the conditions are the same as before. Well, we see that particle flow number has mostly no effect over both of those parameters in all its ranges. No matter the range, the effect is poor, except for some effect over the residual pressure over here at lower slip velocities, this lower slip velocity over here. Apart from that, the effects of particle flow number over those residual parameters for the solid phase are very poor indeed. Here we have some results for residual pressure and viscosity of the gas phase now. Again, the conditions are the same as before. We see here, for the residual pressure, we see that particle flow number has no effect at higher filtered slip velocity, no effect, and some effect for the lower slip velocity over here. For the residual viscosity, we see that for the particle flow number has some effect at higher filtered slip velocity. We see up here, and in particular for higher values of the particle flow number, and we have mostly no effect. This effect is gradually disappearing for the lower filtered slip velocity. Here we have some conclusions. Well, flow heterogeneity grows with decreasing particle flow number. We've seen that. Decreasing particle flow number means more refined structures, also means higher local velocity fluctuations. This decreasing particle flow numbers cause higher drag coefficient corrections, meaning higher corrections over homogeneous drag, and caused also higher values of some stresses-related parameters and lower values of other stresses-related parameters. The comments here inside those brackets should have question marks indeed. Why is that some stresses-related parameters increase while others decrease with the particle flow number? We guess this may be related to a balance between opposing kinetic and collisional effects, but this is a matter for further investigation, of course. As compared to the previous study, the present results show similar qualitative behaviors for all the concerning subgrid parameters, while quantitative differences were observed in response to the similar non-local effects caused by a variety of macro-scale conditions that were practiced. Well, those are our sponsors. Please direct any questions to this email over here. And thank you very, very much for listening.
Thank you for the first presentation, Fernando. Jenna, I think what Fernando wanted to do was to run the second one, and then we'll take questions at the end since the two presentations are linked.
Okay, let me put that on now.
Good morning again. I am Fernando Milioli, and I work at the University of São Paulo at São Carlos in Brazil. In the previous presentation, I showed some of our most recent subgrid data relevant to gas particle fluidized flows. New related subgrid modules are now proposed here. Under this title over here, scale-sensitive subgrid modules for effective drag, filter, and residual stresses in fluidized gas particle flows. Well, by scale-sensitive, we mean that the data accounted for in the derivations came from a number of simulations imposing a whole variety of micro and macro scale conditions. Well, as stated in the previous presentation, our effective filtered and residual data were all derived by filtering over highly resolved simulations performed on the MFX platform, applying microscopic to fluid modeling under periodical boundaries. Well, we already presented this slide in the previous presentation. In summary, the present works are an evolution of our previous work on particle fluid number effect in subgrid modeling, as we extended the simulations to embrace ranges of macro-scale conditions going from dilute to dense and from suspension up to pneumatic transport conditions. The previous presentation brought some results. This presentation here is about subgrid modules that we developed. This topic 2 over here that makes this presentation number 2. Well, just repeating this slide from the previous presentation, here we define the subgrid effective, filtered, and residual parameters of interest, which are relevant to filter to fluid modeling. This is a usual formulation for a filter to fluid modeling, where those subgrid parameters of interest are embedded. Well, we are mostly concerned with the drag coefficient correction, this guy over here, 8, the filtered pressure and viscosity of the solid phase, those guys over here, and the residual pressure and viscosity of both the phases. Of course, those parameters are all embedded inside this filtered formulation. Those parameters over here are the parameters we are going to provide modules for. This slide here summarizes the physical conditions and the numerical setup that we applied in our highly resolved simulations. We emphasize in the table down below the underlying particle fluid numbers that we applied between something around 12 and something around 800. We also emphasize here in this table the local influences that we accounted for. This was done through a range of domain average solid volume fractions down here between 0.05 and 0.55, combined with a range of domain average gas Reynolds numbers down here between 1 and 24, around 24. This covers something from very slow velocity suspension up to something close, like pneumatic transport. The bullets here up there, we show here some numerical conditions that we have applied. First, we applied all periodic boundaries as suggested in this figure. Where we have considered a domain 16 by 16 centimeter size. We consider 128 by 128 grids, giving a grid cells of 1.25 by 1.25 millimeters. We considered filter sizes up to 4 by 4 centimeters. Well, here we have an example of a snapshot of the mesoscale flow field solution that we get from our simulations, over which we apply filtering. The procedure of filtering and binding is quite usual, well described in literature. A box filter sweeps throughout the whole domain through successive snapshots inside the statistical steady-state flow regime while collecting inside averages or filter data. And this data is classified by narrow ranges of mesoscale markers, while at the same time statistically merged. We apply a double marker binning here, taking the filter solid volume fractions, I said down here, taking the filtered solid volume fraction and the filtered slip velocity in the axial direction as markers. Those are our mesoscale markers. One aspect to mention here is that we filter all the results for all the macro scale conditions all together, so that our final results will be expressed as a function of particle Ford number and filter size, besides the mesoscale markers, those guys here. Well, and now we present samples of our results, plus related data fitting. In this particular slide for the drag coefficient correction, we have here various profiles of the drag coefficient correction as a function of the mesoscale markers, which are the filtered solid volume fraction and the filtered slip velocity. Each one of those figures is for a different particle flow number, and all of them for a particular filter size. The full lines in all of those graphs stand for the model that we propose to be shown next. Well, this is our subgrid model for the drag coefficient correction. Notice that we present a number of coefficients in numerical form in those tables down there. And why is that? Even though those coefficients, all of those coefficients showed systematic behaviors in relation to the various parameters of correlation, which are the mesoscale markers, the filter size, the particle flow number. In spite of that, no simple rules of correlation could be found. Therefore, we give those coefficients in numerical form in those tables down here. So this is our subgrid model for the drag coefficient correction. Well, here we have samples of results and fittings for the filtered and residual stresses in the phases. Here we have various profiles of those parameters as a function of the mesoscale markers, the filtered solid volume fraction and the filtered slip velocity, and as a function of particle flow number and as a function of filter size too. Well, the full lines in all of those graphs stand for the models that we propose to be shown next. Well, those are our subgrid models for filtered and residual stresses. Again, we present a number of coefficients in numerical form on those tables down there. The same comment as before. Even though those coefficients showed systematic behaviors in relation to the various parameters of correlation, no simple rules of correlation to be found. Therefore, we give those coefficients in numerical form in those tables down there. One aspect to mention is on that remark over here. Aiming for a smaller set of equations, we correlate only to a most influential third marker in addition to the mesoscale markers. And this third marker was the the particle fluid number for the filter pressure and viscosity of the solid phase. And this third more influential parameter was the filter size for the residual pressure and viscosity of both the phases. Here are some conclusions of our work about the comprehensiveness of the new subgrid models. We account for filtered solid volume fraction, filtered zero velocity, filter size, those at the mesoscale. We account for the particle fluid number at the microscale, and we account for the domain average solid volume fraction and domain average gas Reynolds number at the macro scale. Those macro scale conditions taken in average in our models. About possible improvements, we can mention account for alternative or additional microscale markers, further assess number and type of mesoscale markers, and actually correlate to macro scale markers. And finally, those are our sponsors. Please direct any questions to this email over here. And thank you very much for listening.
Thank you, Fernando. It looks like we had some questions asked and answered in the chat, but I want to give some opportunity to ask additional questions at this time of either of Dr. Miglioli's presentations on fluid number and subgrid modeling. Arthur, did I miss anything in the chat, or has Fernando missed anything in the chat?
No, actually, I mean, like you said, we had two questions and Fernando already replied.
Okay. Well, if there aren't any additional questions, then I think we're at a break point where everyone can go and enjoy some lunch if you're on the East Coast, or an early lunch if you're in the middle, or breakfast if you're out on the West Coast, wherever you are. Enjoy a nice break, and I want to thank all the presenters for being brave enough to get up and talk with us and share their research. So with that, let's return at 12:40 EST. And I think at that time, Will Fulmer will start us again for an afternoon session. Thank you, everyone.
We're going to start the afternoon off with experimental methods of multi-phase flow, starting with Anton Hardner from ETH Zurich. Sorry. And just sorry for the delay again. Please begin whenever you're ready.
Okay, so then thank you very much for the introduction, and welcome to my talk about the development of a high-temperature counterflow solar particle receiver. So before I start, I want to give you kind of like a bit of background and introduction. So our system is meant for a central receiver configuration, as you can see it here. And in such a configuration, you have a field of heliostats where the sun is getting redirected by the heliostats to the top of a tower. And in the top of the tower, there is a device called solar receiver, in which the radiative energy is getting transformed into thermal energy. And this is happening by heating up heat transfer medium, and in our case, we are looking into particles. And here you can see already kind of like a sketch of our solar particle receiver configuration we are going to develop and investigate. And it's like the following. We have a reservoir of particles, which are dropped into a duct, and inside this duct, we have a countercurrent airflow. And we hope, and also know already partially, that this airflow is going to slow down our solid phase, kind of like the velocity, the fall velocity. And why do we know this already? This is due to a study which was already done by Professor Coletti's group in Minnesota, where they kind of like investigated such a particle-laden flow for solid volume fractions between 0.1% and 0.8%. And they could see that due to this countercurrent airflow, they could degenerate the fall speed of the solid phase. And interestingly, they could also see a certain scaling, such that the solid phase velocity scales a bit like the terminal velocity of a single sphere in still air, minus the bulk velocity of the fluid phase. And another interesting observation I want to share with you is that starting from a certain threshold up on, they have seen that the particles are agglomerating and forming clusters towards kind of like the walls inside this duct. And in my PhD, we kind of like want to take this flow and develop it into an application. And by doing so, we want to first kind of like study the hydrodynamics of this system for more dilute cases, for solid volume fractions up to 10%. Then we also want to build this device made out of high temperature resistant materials, such that we can investigate like how much we can heat up these particles. And this is also partially supported by some simulations on heat transfer. So now I want to kind of like give you an overview how we are going to continue to study the hydrodynamics of the system. And here you can see a CAD drawing of the experimental facility, which is more or less, you can think about it as a vertical kind of like wind tunnel, which has all the features. So when we start here at number 7, this is kind of like the air inlet. Then the air travels through a flow conditioning section with a honeycomb and a screen, and afterwards a contraction, and then enters the test section, which is partially then from one part of this test section is made out of plexiglass, such that we can image the flow. Afterwards, it leaves the test section through a diffuser and then through the air outlet. From the top, we have kind of like we have this hopper, which is filled with particles, and beneath this hopper, we have a knife gate valve, such that we can control the orifice size and with it, the amount of particles we are dropping into the system. And to give you an idea how this kind of like all looks, because this is already, the CAD is finalized and we have the parts manufactured and assembled. You can see here from the bottom, we have this particle collecting system, flow conditioners, contraction, test section, diffuser, and then here at the top, the hopper with our knife gate valve. As you can see, the process, like the airline is not finalized yet, so we just got this part, all these parts, and it's kind of like where the experimental part of my project is at right now. However, in the future, we are going to investigate this flow with backlighting and high-speed imaging. And then now comes kind of like the second part of my talk, where I want to kind of like introduce a bit which heat transfer phenomena are taking place, and also talk with you about kind of like a small one-dimensional study I've done about this kind of flow inside the duct. So the situation is, as I already described, here at the top we have a schematic of it. The particles are falling inside this duct, and you have a fluid flow which is coming from the bottom. Then we impose a certain wall temperature, which is fixed in that case right now. And the wall temperature is significantly high, that we will have re-radiation of this duct walls into the inner volume of this duct. And to start kind of like this model, I introduced general assumptions, which are true for the solid as well as the fluid phase. And the first one is it's a 1D model, as I already was saying. Then that's a steady state model, so we have no accumulation of heat, and I'm assuming no pressure drop, which is of course a very strong assumption, but for the beginning, such that I don't need to couple it with the momentum equation and only look into the energy equation of this assumption. So then in the next step, for the fluid phase, I'm saying it's a non-participating medium, which is okay because it's air. Then I'm neglecting the conduction. However, I'm looking into the convection in the fluid phase itself, as well as between the heat transferred fluid and particles, as well as fluid and wall. In the end, you arrive at this kind of like energy balance here. You have the convection part in the fluid phase itself, the heat exchange between the fluid and the solid, and then the heat exchange between the fluid and the wall. For the solid phase, I'm assuming that we are looking into a participating medium. Something I didn't mention yet is that these particles are going to be ceramic particles, which are mainly made out of alumina. And this is indeed a participating medium. Then in the first step, I'm neglecting the inter as well as intra-particle conduction. However, we are looking into the convection in the solid phase itself, as well as the heat exchange between the fluid and the particle phase. Then in the end, you end up with this energy balance for the solid phase, where you have the convection part, heat exchange between fluid and solid, and then this radiative source term. This radiative source term is kind of like an interesting part of this heat transfer model here. And one way, there are some ways to go about it. And I was looking into using the divergence of the radiative flux, which is in short, like in units, it's watts per cubic meter. So if you can define the divergence of the radiative flux, you can multiply it more or less with the volume, and then get out kind of like your power input into this medium. And you can see here then that to find such an expression, you need to look into the intensity which is still present at the point where you're looking at in the participating medium. And you can do that with the radiative transfer equation. I don't want to go into too much detail, but So the radiative transfer equation is basically telling you how much of the initial radiation is still present after you traveled a certain path length S through a participating medium, and the intensity can increase or decrease due to these 4 different mechanisms. So then further going down, such that you can end up with an analytical solution, which was important for me in that early stage of my project. You have to go through quite some assumptions, and maybe the most crucial ones or debatable ones is B, such that I'm saying that the temperature of the particles is constant along the width and the depth of the duct, and also that I'm saying that the duct walls are only irradiating collimated rays, which is of course not true because it's a diffuse wall, but for starters, I think it's okay to do. And then going through a process to solving this expression above, you can come up with an expression for the divergence of the radiative flux, plug it in, and then finalize kind of like your heat transfer model. I used MATLAB, a boundary value problem solver, to kind of like get out these temperature profiles, and would like to discuss now with you kind of like my first results, which is the influence of the particle diameter. So here in these figures, I'm going to show it's always going to be the same. On the y-axis, you have the height. On the x-axis, you have the temperature. And then in the title, we have some fixed conditions. For example, here, the temperature of the wall is always fixed by 1,530 degrees Celsius, which is a value I've taken out from experimental work in Professor Steinfeld's lab, so temperatures which are achievable. Then we have a fixed solid volume fraction in this case, which is 0.1%. And the path length I'm looking at is 10 millimeter, meaning the average power input due to radiation, I'm assuming for each particle, is that for a particle in the center of this duct, because my duct has a cross-sectional area which is 20 by 20 millimeter. And now this temperature profile you are seeing right now is obtained for particles with a diameter of 150 microns. And what we can see is that the particle temperature is quite high and comes quite close to the wall temperature, which is our maximum temperature we can achieve in principle, because this is kind of, this is just, if this would be the same, then the driving force would be 0. And if we then increase the particle diameter, we see that the temperature of the solid phase decreases slightly, and also the fluid temperature decreases slightly. Why is this the case? So the main point here is that the available surface area of the particle decreases, and so the heat transfer between the fluid as well as the solid phase is not as efficient as for the other case. You will see this kind of like phenomenon later on in more detail. Kind of like the second result I want to share with you is the influence of the solid volume fraction. So in this case, the temperature of the wall is fixed again, and also the diameter of the particles is fixed now. However, now I'm changing the solid volume fraction. The temperature profile you see here right now is for a solid volume fraction of 0.1%, and the results are very similar to the one we have seen before. As soon as I increase the solid volume fraction to 1%, we see a slight decay in, decrease in the solid temperature, and also a strong increase in the fluid temperature. And this comes back to the point that now with the higher amount of particles, we have a way higher amount of available surface area for heat transfer. And so the fluid exchanges a lot of heat with the particle phase. And now something maybe surprising is happening, and that is that for a very high concentration of particles, you see the particles are not heating up at all in this very simple model. And I want to share with you a bit why this is the case, and that's important to come back to kind of like the path length I was talking about. And that was before I was always assuming that the average power input due to radiation is for a particle in the center of the duct, as you can see it here with the purple cross in the center. However, as soon as we are increasing the particle concentration significantly, which we are doing with 10% of solid volume fraction, this medium is almost getting like optically thick. And with an optically thick medium, we have a strong decay of the initial irradiation through this medium. And when here in this plot now, I'm showing kind of like what happens if I assume a different position of the particles. So by going always closer to the wall, like from blue to orange to green, which is then almost at the wall, we see that the power input due to radiation increases drastically, meaning the average outlet temperature of the solid phase is increasing as well drastically. So that kind of like tells us that this 1D model will probably be not good enough to describe kind of like this phenomena which is taking place. And also that if we have a laminar flow inside of this kind of like receiver, meaning there's not a lot of mixing between the particles close to the wall and inside of the duct, we will have strong temperature fluctuations. However, we have seen in the pictures before, in the beginning, that the particles start to agglomerate at a certain threshold of volume concentration, leading probably to cluster formation and then a good mixing kind of like, or hopefully that's something we are also going to investigate in the future, good mixing of the particle phase. So we hope at least. And that kind of like brings me now to the last part of my talk. And this is how do we kind of like get for us in an experimental or in a laboratory environment, the solar particle receiver setting out of kind of like this flow. So we need to kind of like place this duct inside the solar cavity. And the question is, how does the solar cavity look like? In the beginning, we were thinking of going with a configuration this configuration you can see here, plainly a duct in the center of the solar cavity. However, we imagine that, and also that kind of like the temperature gradient is probably quite strong, meaning that maybe this duct could crack in during experiments. And that is kind of like a safety hazard because the front of this cavity is open. So then we were thinking of kind of like moving what other configuration could be possible. So we moved this a bit to the back. And then as the last configuration, we have this kind of like more of a slab we are gluing into this large cavity you could see to build the second cavity in the back. And then we wanted to investigate kind of like what of this configuration is from a solar cavity perspective, meaning like the conversion efficiency, this is I will talk about later, the best configuration. To give you a short overview over the dimensions of these configurations, like configuration A and B are quite similar. We always have a large cavity 1, and then we have a cavity, a smaller, this duct, I call it now cavity 2, which is formed by alumina, either a channel or like here, you could really glue in like a piece. And the dimensions are very similar. This cavity 2 is always 20 by 20 millimeter, and cavity 1 is 100 by 100 millimeter, and the height of all of these cavities is always 200 millimeter. Then for configuration C, it looks a little bit different because we have this kind of like whole slab of alumina, which is glued into the back and is forming then with the back wall of this insulation, this cavity number 2. Nevertheless, the dimensions are also very similar to the other two configurations. Just to state, since it's very important, our diameter of the aperture here is assumed to be 40 millimeter. And then the simulation conditions, which I was running in COMSOL, is that I'm looking at the collimated ray source, and I have right now a source heat flux of 10 to the power of 6 watts per square meter, which is coming equal to a concentration ratio of 1000 suns. And also important, since I wanted to get already closer to the reality, is that such a solar receiver needs, or such a solar cavity needs a cooled radiation shield, otherwise the material would melt in the front. And this actually takes out quite some heat from the whole system. And then the most important point here to focus on is kind of like that I impose here where the blue highlighted surfaces are, I impose a sink heat flux such that I simulate kind of like the amount of heat which is transferred from the duct onto the particles. And the heat transfer coefficient I'm using is taken out from a paper from Flamand et al., where they are looking into fluidized solar particle receivers, which is probably kind of, you can imagine this like a fluidized bed reactor. And this is, in my opinion, coming the closest to our solar particle receiver, which is not yet much documented. And now to this small study where we wanted to find out which configuration is the best. We are looking into this conversion factor, which is basically telling us how much of the power input is getting then transformed onto the particles in form of the sink term. So how much heat we can extract from cavity number 2. And then in the end, we found out that actually even configuration C leads to the highest conversion, and configuration A and B are quite similar, however, not like around 50%, which is actually not a very good value for us. And so for us, this means we want to go with a configuration which looks close to configuration C. This also brings me kind of like to the conclusion of my talk. So we developed already a 1D heat transfer model capturing the most important heat transfer modi, which are convection and radiation. And this model represents already findings from the literature, which is that increasing the particle diameter leads to a decrease of the particle temperature, and also increasing the solid volume fraction leads to a decrease of the particle temperature, because the amount, so the second point is true as long as the power input keeps constant, because then I have more thermal mass in the system. So of course, if I have not more power input, the temperature must decrease in the end. Further, the second study told us that, or hopefully helps us to decide on how the solar cavity should look like, and this for us would be to go with this configuration C. As an outlook, we are now going to start the investigation of the hydrodynamics of the countercurrent solar particle receiver under room temperature conditions, and currently I'm also finalizing the CAD drawings of the experimental facility, which is going to be used to study the thermal performance of the solar particle receiver. And the main questions we want to answer is first the average outlet temperature of these particles, and then also what is the overall heat transfer coefficient. And then the point we want to assess as well is if this cluster formation helps us in form of in the perspective of heat transfer or not, because either it's going to help us mix, kind of like that we get an equal outlet temperature, or the clusters are going to block kind of like radiation for the inner particles, such that then in the end, the outlet temperature will be again very inhomogeneous. Yeah, with that, I want to thank you for listening to my talk, and I'm happy to take questions.
Thank you, Anton. First of all, just checking, can you hear me?
Yeah, I can hear you.
Okay, great.
Yeah, we can hear you. This is Shubhadeep. I don't see any questions in the chat.
No questions there? Okay. Yeah, if you have any questions, please follow up in the chat. Thank you, Anton. So if he got updated to panelists, next is Johnny Hyam. He seems to be in there. Johnny.
Can you hear me okay? I should be here. Can you hear me all right?
Yes, thank you.
Okay.
If you could go ahead and share your slides when you're ready.
Okay.
There we go. See your title slide. Thank you, Johnny.
Okay, no problem. So, well, thank you, Will, for, I'll just check the time. Thank you, Will, for asking me to present. So I'm going to start this presentation with a bit of an apology that I'm a little bit unprepared for this, and I'll show you why in a slide next, that I've not actually been able to use the slides in the exact presentation I wanted to, but I've picked up some previous work that we've done with two colleagues at NETL who you may have seen already today, or former colleagues from Avinash there. So what I'm going to talk to you about is a tool that I've been working with for maybe the past 10 years now, which is all about extracting coherence or patterns from different structures from a fluid mechanics perspective, from a granular flows perspective, and more recently looking at more environmental flows. So I'm sorry I didn't introduce myself. I'm Johnny Hyam. I'm an associate professor at the University of Liverpool. Scarily enough, I've been there 5 years now since leaving Morgantown to join Liverpool. So this is why my presentation isn't exactly on track. Unfortunately, on Saturday I managed to do this to myself, and I'm currently at the other side of the country giving the presentation from a different computer. Well, I can't walk, so that's why. So a little bit about the motivation for this. So I'm going to talk about some work a little bit later in the presentation, which we did actually in the labs, the MFIX labs. So as you can see here, we've got this fluidized flow, and I always think this is a really cool picture that we took, and it was just a jet of air really moving through some glass beads. And what you can see here is we can turn what we would think of as a solid into more of a fluid. And that means that effectively we might have some tools where we can begin to look at this. But maybe if we start to think of this solid as more of a fluid, we may need to think about actually what a fluid is. And this takes us back to our Fluid Mechanics 101 and thinking about actually how we might describe how a fluid flow works. So of course we see this equation at the top, and it's a short form version of the Navier-Stokes equations. So this equation can tell us exactly how a fluid moves, and if we delve a little bit further, we see it's just Newton 2. So effectively, we have some force terms, we have the pressure term, and we also have this dissipate or this viscous term. So inside of a fluid, we often think about how energy is communicated or is passed through a fluid as through structures. So these could be thought of as vortices or even maybe more abstractly as coherent structures. So effectively, if we take a description of what a turbulent flow looks like, we can think of it maybe as these collections of structures which collide with one another. And as Kolmogorov showed us, and Richardson and Kolmogorov both showed us, that through the cascade, it's possible that these structures collide with one another to transfer energy through a system. So effectively, if we're understanding how a fluid works, we can use maybe this 5/3 rule to a very short extent, universality, to describe how energy is passed around the system. So if we've got a fluidized solid, surely we should be able to have some sort of scaling relationship, right? So if we think a little bit about what these structures are inside of a fluid, I've brought out 3 people here, and if Justin's there, I'm sure he'll be glad to see a fellow Penn State person there also. So effectively, we can think of these 2 poems describing how this energy is transferred within a fluid, or potentially even if these things exist within solids too. Richardson's telling us that we have these large whirls and curls which collide with each other, or actually maybe Betchov's description showing these whirls and curls which feed on one another to be able to pass energy through a system. So we go back to this solid and we think, okay, well, maybe if this is a fluidized solid, how can we describe this in a similar way? Can we think of what's happening here as coherence? If we've got something perturbing a fluid flow, effectively we can describe the patterns as coherent structures. But maybe can we do the same thing inside of a solid, inside of a fluidized flow? Well, actually, some chaps in Australia have maybe showed us the beginnings of this with this eddy viscosity model, which they roughly described in a physical review e-paper a few years ago. Effectively here, they're driving solids to understand coherent patterns in there. So perhaps we might have the same things in our solids. Well, I'm pretty sure we do because these guys have shown it. So what this means is we need a set of tools or an arsenal of tools to be able to help us actually extract these structures. And this is where techniques like modal decompositions come in. So over the past, 30 years now, in the late 80s, or early 80s, these techniques started to come into fluid mechanics. And I'm going to focus on just this proper orthogonal decomposition, which is a method which allows us to extract spatial coherence. So what do I mean by that? So effectively, what we could do is we can feed in a set of data, as I've got here, as a cylinder flow. And what we can pull out is a set of spatial modes or representations. And likewise, we can also describe how useful they are to the system. We can create a percentage showing how much variance this captures within this whole system. And even more interestingly and importantly, we can extract these temporal evolutions. We can explain how these spatial pictures evolve through time. So effectively, we have a very, very powerful tool which allows us to be able to deconstruct a flow. So if we could deconstruct a fluid flow, surely we should be able to deconstruct a solid flow. And that's what we wanted to show in this work we did a few years ago. And that's what we did show. So to show a little bit further mathematically how this works is effectively we can take a set of data here and we can solve through a singular value decomposition a set of eigenvectors and a set of eigenvalue values. We can then map these eigenvectors. I don't know if you can see the pointer here. Maybe I should get the pointer. We can take these eigenvectors and we can then map this back onto our original data here, which means that we're then also able to create these spatial modes. What this also shows is, if we were to follow the mathematics through, which I don't have enough time for today, is that these spatial modes are orthogonal, but we only have one of them actually in the data set. Well, we have one which is existing. So effectively, we can show spatially independent modes as well. So there's only one of these, so that's going to be a coherent structure. So maybe just to explain this a little bit with a video, because the maths isn't always so isn't so simple to follow. Effectively, if we took something like a cylinder flow that we've got here, what we can do is we can maybe feed this in to our data stream. It says our data stream. We can column vectorize snapshots of these data. And then from this, we could begin to reconstruct this flow as well. We could take the two spatial modes described here by about 50% of the variance, and we can create this pattern. Effectively, what we're showing here is that from our data, we can describe in a single sinusoid the temporal evolution of these structures, which is a simplistic form. For modeling, really important because we can project these into our models. What we can also do is move into higher harmonics and look at other things that might exist on top of these. If it's going to let me transition. We have another harmonic that sits on top of this, effectively taking up about 20% of the total variance. And effectively, this is another pattern which is superimposed on those original data. Yet, we couldn't see this from just analysing the data alone. So this highlights how powerful this tool is to be able to extract structures from one another. We could then reconstruct all of the data, and as you can see here, we could use the first four modes to be able to almost reconstruct that original data set and actually describe things. Again, a very useful tool for helping us to project into models that simplified version of this flow. Okay, we've maybe deviated a bit too much from what we're talking on granular flows, but if we were to move this back into this realm and pick up some experimental work that we did back a few years ago in the lab. So again, this was, I've got in the corner, this was all Mehrdad's work, and Avinash and Mehrdad both worked on this with me. So effectively what we had here was a pulse fluidized bed in which at the base we fed from a fractal distributor, we fed a set of number of sinusoids of gases in the inlet. We set these at 4 Hertz, 5 Hertz, and 6 Hertz. And what these did is they created a set pattern, different patterns, and I'll talk about those in a sec. What we could also do is we could track each one of these individual grains, and that's down to a tracking code which is for another talk. Effectively, we had now some really good information we could begin to apply to this proper orthogonal decomposition. Also, just to point out, this was the same picture that was on the front of the poster that Will sent out. So effectively, if we look a little bit closer to how we pulse these beds, we actually had two pattern regimes. We had what we called a 1-1 pattern regime, and as you can see here, where one bubble forms and then another bubble forms in its slipstream. On the far end at 6 Hertz, we had almost a smiley face, where we had two bubbles, and then from its slipstream, another bubble was formed. In the middle, we had some sort of transition, which was a bit of a mess between these two. But effectively, what we could see is between 4 and 6 Hertz, we were creating some sort of change here, which was changing the way in which this mixed. So what we wanted to do was understand what was causing this effectively to understand how we can become more, or how we can understand the efficient mixing of these systems. So what we could do is, using some bubble tracking techniques, we could track the individual bubbles, and we could also transform what we've got here of the granular movements into velocity, or maybe we say granular temperature if we look at that approximation. And what we can see here around the bubbles is we were getting higher velocities as these were raising through the beds. So this is just the raw data. If we were then to take this a little bit further and do our POD results, and we were to apply our proper orthogonal decomposition, what we found is we could extract a set of patterns. And these patterns all had their individual sinusoids. What we did find also is that we found that there was a harmonic and a subharmonic. These two things were driving our system. Effectively, we found this out by applying a Fourier transform to these temporal evolutions, and we can see at 4 Hertz, our first mode is governed, or in all the cases, is governed by our first harmonic. In our second mode, this is also governed by the subharmonic. And as we get higher in the modes, the different cases show that maybe in this fourth mode, we begin to see that there's some sort of breakup in the 4 Hertz. This begins to see, we see a second peak at the 0.5 Hertz, and this transitions up to this 1 Hertz. So effectively, what we were able to describe with this technique is that as we get higher in the order, we were actually swapping the way in which the harmonics were acting. Effectively, this was the thing that was controlling the bubble pattern. So by extracting this, we could extract these spatial pictures to look at the harmonics and also look at the half harmonics. And when we look back to what we found from these results, effectively, we found that in the first mode, in all the cases, we had a set of harmonics. In the second mode, we had a set of subharmonics. And then we can see between the cases, we almost see this switch. And it is this switch in these harmonics which means that we have this change in pattern regime. So effectively, what this proper orthogonal decomposition technique allowed us to do was to open the door for a next piece of research. It showed us that actually it's not the largest scales or the largest amount of energy which is changing. It's actually as we get higher up, and that is the thing which is driving the bubble patterns. So effectively, this then began to raise questions. Is this something to do with how these are mixed? And effectively, this led us on to another piece of work, which I'll briefly touch on. So by tracking each one of those individual grains, you saw that picture and on the presentation, the first on the slide, the post that Will has shared with you, we could individually track these particles. And as you can see, we can find that just between this is just the 4 and the 6 hertz, we have almost these curly patterns, which between the two cases do differ. And these are just some extracted paths that we did find. We did expect to do a few thousand of these. And actually applying a few statistical tools to this, we managed to find that as we increased the bubble pattern, effectively, we increased the efficiency of the mixing and we increased how energy is dissipated through this system. So, to bring it back as to a round circle, is what we managed to do with our work is, first of all, the idea was to apply a tool which lived in the fluid mechanics world, and we found that it worked. And what this also helped us do was then elucidate some of the system properties and further apply different tools, which again come from the fluid mechanics world, to better understand how these flows work. So, as I say, this isn't my current work at the moment. We have got some other work with rise piles, which we are working on, but we're working more on some of the large scale stuff. These are transformable techniques. Currently, this is the very large scale stuff. This is a coastline at 5 kilometer scale. And effectively, we can apply the same methods and we can begin to describe patterns. And some of the work we've been doing is using this for forward prediction. So that's just maybe a taste of what we do. So looking at the time, I've done my 20 minutes, maybe just a little bit over. So I'll leave it there as a thank you with our sickly slide from the university that we have to now use. So I'll leave it open to any questions about the technique. And apologies, it's a little bit thrown together, as you can see. I'm a bit of a predicament.
Thank you, Johnny. Thank you for presenting through the injury.
No problem.
Any questions here? And I don't think we have any in the chat, but I will, if you don't mind, take the opportunity to roll on to the next one so we can try to make up some time. If there are any, just keep your eyes on the chat for the remainder of the session. Thank you. Okay, so up next we have Professor Bardet. Is he a presenter? Yes.
Hi, can you guys hear me and see everything right properly?
Yes, and we can see your slides. Thank you very much.
Sounds good. So yes, thank you for having me. I'm gonna present some recent work we did in my group on measuring momentum transfer and getting into mass transfer measurements between liquid air interfaces. So most of the stuff I saw today was in the solid gas interface. Here were liquid gas interfaces. Kind of the motivation for us, broad level, lot of simulation, a lot of motivation. Sorry, but one of the motivation is to really understand how like small scale waves, capillary waves, really affect momentum and mass transfer. If you look into most of the existing correlation for CO2 absorption in the oceans and many other processes, this is typically neglected, and it's kind of in correlation, doesn't even appear, or if it's appear, it's highly empirical. So there is a need for experimental data to understand some of those processes better, and the techniques don't really exist for that yet. So let's start a bit with the physical processes of interest, and then I will present the techniques we've been developing. So if I look into interface shear between a liquid and a gas, or it could be between two immiscible fluids. So you can decompose your stress, putting your cell in a curvilinear coordinate system that is following the interface S. You can define your surface normal N and your surface tangential vector S. And so you will have a tangential stress, which is in the S direction, and a normal stress sigma in the surface normal direction. So one of the couple of things, if you look into your tangential stress that comes into your equation, and it has to do with your coordinate system, is kappa, the curvature, local surface curvature in your system. So what we see here is that even if I have a free surface, my free surface actually will have a vortex layer of vortex sheet below the surface if the surface has a curvature, that means if it is deformed. And so we did some first measurements on this a few years ago, and what we were doing at the time was fairly traditional, was time resolve PIV in the liquid phase and the gas phase simultaneously. So we had an open flume moving at fairly high speed, and we were having one laser plane coming from the top to do PIV in the gas phase, one laser plane from the bottom to do PIV in the liquid phase. And again, they were, so you could create a mask using the gas phase image on the liquid phase, and then process the data independently in both fields and then merge them. So here, oops, the video didn't play. Here are some of the data that we got. So again, the liquid is on the top, the gas is on the top, the water is on the bottom. This is water air. And you can see some very small wave. Your scales here is millimeters on the bottom, millimeters on the vertical axis as well. And you can see this this vortex layer below the surface that come from our initial conditions. So anything that is yellow, orange was initially present. Anything that is in the bluish color scale was vorticity generated at this interface. So we could identify some flow regime and do some conditional averaging, understanding better the wave statistics, but skipping. Here's what it gets juicy. Here, what we try to reconstruct is the typical velocity profile as a function of the wave stiffness. So the wave stiffness, we use a parameter AK, where A is really the amplitude of the wave, and K is the wave number, if you want the wavelength of your wave. And so, oops, the video didn't play. There you go. So here we see kind of the mean velocity structures as we're changing this stiffness parameter, and we start seeing as the waves become very big over our wavelength, we see some interesting things going on in the gas phase and in the liquid phase. Looking at the individual images, so our data at enough resolution, we could measure directly the interface shear, and so we could do conditional averaging based on the amplitude of the wave, and so on the stiffness or amplitude. And as we can see, there's something happening above a certain stiffness. We see this secondary peak appearing here that actually dominates what we have. So in most of the model you have for momentum transfer, the secondary peak that is present here is not taken into account. And if you look here, that is a huge effect on your interface shear. Looking into projecting it differently, we can see that above stiffness of 0.45, you start seeing the secondary peak coming into play. And what we found is that actually this is coming from flow separations behind the very steep capillary wave the gas phase separates, and you create a vortex in the gas phase. In the liquid as well, you have vorticity generation at your free surface, and you're going to have a vortex that is going to recede below the trough of your capillary wave. So the combination of those two vortices really explain this secondary peak we see in momentum transfer. And so we can develop some correlations to understand how the mean viscous shear stress changes with AK. So we had everything with the stiffness. We had everything we could do to get the momentum transfer, except we were missing the pressure reconstruction that we could have estimated because our data were time resolved and the flow was mostly 2D, but we have not done it at this time. So we are almost at everything we need. So that's kind of a preamble. So we really see at the small scale, there's a lot of things interesting going on that is really ignored. And so one of the limitations we run into here with PIV, our resolution was fairly high. Our interrogation window, which sets the resolution of your PIV, was about 100 micrometer. That's still a bit coarse for some of the things. So we need to have a way of doing measurement with a higher spatial resolution for velocity. So we need a better velocimeter. Ideally, also the flow I showed you were nice and clean, but it was mostly 2D. It would be nice to get into 3D regimes. And so having a way to measure the surface profile in 3D, and ideally, once we start entraining a lot of bubbles, it would be nice to prop those bubbly flow with a high void fraction using optical techniques as well. And so, and can we at the same time add the mass transfer measurement to this? So I'm going to show you some of the progress we have done toward those questions. In my lab, we're specialized in laser-based diagnostic and optical-based diagnostic. So the benefit of my tools, they are fairly non-intrusive and they are minimally perturbative. You still affect your flow a little bit by shining a laser. You put a bit of energy in your system, but we try to minimize this effect as much as possible. So on the velocimetry aspect, one of the big efforts we have done lately is what we call microscopic molecular tagging velocimetry, MTV. MTV, if you want, is like PIV, particle image velocimetry that I showed you earlier, except instead of using a particle to seed the flow, we use molecule. So if you want, it's the molecular equivalent of PIV. So here you see an example. So compared to PIV, we have now two lasers in our scheme. One laser that we call the right laser in purple here that is used to create a pattern in the flow, and the read laser that we use to read this pattern. Okay, so on the bottom here, you see on this image, on the bottom image, you have a straight line. This is the tracer we have created locally with our first tracer. On the second image, you see this tracer being advected. And let me see if I can find the laser pointer with this, but anyway, it's fine. You can see this tracer being advected, and so you can reconstruct visually what your velocity profile looks like. So that's the concept. Historically, though, MTV has had very poor spatial resolution, very poor temporal resolution, and that use very specialized laser. I won't go into too much detail, but we made a lot of progress on this. Here is MTV or micro MTV applied to a wall-bonded flow. So this is a high Reynolds number turbulent channel flow, and we're writing a set of lines vertically. The wall is at the bottom. That's the black line, horizontal black line at the bottom. And we are writing a pattern and then looking at 10 images of this pattern being deformed, and then we print a new pattern and we look into this pattern being deformed. So with this, we can really measure the wall shear stress directly with that technique. Here to give you an idea of the scale, the beamlets we write are about 25 micrometer, which really sets my resolution of my system. In the wall normal direction, with the high resolution camera I have, I discretize on the order of like a couple of micrometers, so sub-viscous wall unit. So similar in resolution to what you will have, or superior to what you will have to DNS of wall bonded flow. And so here are some of you can play with your MTV parameters and identify flow structures fairly nicely. So we can identify like big vortices, vortices into the buffer layer of this wall bonded flow. And to give you an idea of the resolution we get in wall bonded flow, we can measure instantaneous wall shear stress fairly precisely with a resolution better than 5% on the instantaneous and better than 1% on the mean. Now we applied this to capillary waves, and so here we get back to the same experiment we did with the PIV, and so here we're writing our lines starting from the bottom image on the left, our line normal to the surface, And then as your wave is traveling, you see this vortex being created below the trough. You see this acceleration locally of your vorticity. What you can see also directly is really your shear at the interface, right? So with PIV, we're estimated as best as we could. Here we have a much higher resolution on the shear directly. So that's very attractive. This is still in the early development, so we haven't published that work yet, but we hope to get back to that fairly soon. We have a big project on this. One of the things that is interesting here as well is the dye we use is quenched by oxygen. So here what I'm measuring, I started with water that was depleted in oxygen. So low oxygen content in my fluid means high fluorescence signal. Dark signal means high oxygen content. Okay, so my signal is inversely proportional to oxygen content. And we can see here on the top image that I have a dark layer that marks really my interface profile. And this is diffusion of oxygen from the atmosphere into this water that was depleted in oxygen. And as the trough, as the wave traveled, the vortex in the trough actually creates free surface renewal, enshines this layer of enriched oxygen from the surface into the bulk of the flow. And we really see now the signature of this vortex that is here. But again, here what you see is really your local concentration of oxygen. So now we're doing this, the beamlet, we're writing the straight line, we're writing about, as I said, 25 micrometer here. So very high spatial resolution for those measurements. That would be nearly impossible to do with PIV. I mean, we did it, and with the best resolution in this configuration, this is far superior than what we could do with PIV. So that addresses the need for higher spatial resolution and also the need for a way to measure the mass transfer. And so then how do we do about, so this is still 2D, how do we go about going to 3D velocity profile? So we adapted our scheme to write this pattern in the flow, and that we saw in the previous series of slides for MTV. And now what we're doing, we're putting a camera in the gas phase. And so what that gives us is that, oops, I need to start from the beginning. So here the video plays. Here what I see is a flat surface initially, and I'm writing this pattern in the liquid. And I'm imaging from the top. So what I'm from the gas phase. So what I'm going to see is this pattern being refracted going from the liquid to the gas phase. And so if my interface is deformed, which is going to be the case here with this 2 millimeter droplet falling on this quiescent pool initially, I can really see the waves between the laser plane, which is vertical, and the camera, the observer. I can really see this pattern being deformed, and I can reconstruct using Snell's law in 3D. So doing some ray tracing in 3D, really, what does the flow look like? And here are some reconstruction of my interface profile in 3D from this data set and this algorithm. So this is now published. We have done some progress on the algorithm using the fact that our data are time resolved. We can increase the robustness and the efficiency of the algorithm as well. So this works great if you have very sharp interfaces. We wanted to also have a larger field of view. And so we are developing, this is nearly finished. We are developing another technique that is complementary to this structured illumination planar laser induced fluorescence scheme that is based on polarimetric slope sensing. Here you rely on inexpensive polarimetric camera, and you can reconstruct your velocity, your surface profile in 3D from a single image fairly efficiently. And so what we see here below the PIV plane with this 3D profile, and those are time resolved. We don't have animations yet, but because this is fresh off the press. But we're preparing the manuscript on this new progress. So this is moving forward nicely. Finally, how to resolve bubbles optically when I have high void fraction. So we are studying UFOs, ultra-fast optics. And so really the concept is here is what matters for us is my optical thickness tau. So the optical thickness tells you how many times your photon will scatter with an interface, a liquid gas interface. If it scatters less than one time, I can rely on my traditional technique like PIV or regular shadowgraphy images to reconstruct my my bubbly flow. If I have more than one interaction, I'm having issue knowing what my photon did. So up to optical thickness of 2, I can get away with a structured illumination. Above 2, structured illumination techniques failed. Above 10, a lot of scattering, expert techniques become very efficient. But between 2 and 10, there was really a gap, and we think we're in the process of filling that gap using concept of ballistic imaging of ultra-fast optics. So in a nutshell, what's going on is that here I see my photons in blue incoming into a droplet, and as the photons arrive on the droplet, some of the photons will be reflected. That's what we see the blue line here coming at an angle. Some will be refracted. So the red line those are photons that are refracted one time and then come out of the bubbles. Then sometimes they can get refracted a second time, and that's what we see in green, or a third time, that's what we see in pink, or a fourth time, that's what we see in orange, and so forth and so on. So they can do multiple reflections. So taking this into account, I have a way of actually reconstructing what my flow, what was the bubbly distributions in my flow. And so here another aspect that is important is the speed of light in air is faster than the speed of light in water. So to simplify, by looking at the time of arrival of my photon in air versus water, without going into too much detail, I can see if the photon went through bubbles or if they went through purely a liquid phase. So the photons going through bubbles will arrive before the photon that went purely into the liquid. And so here are some first data that we got in the lab. So we use an ultra-fast laser, very short pulse laser. What you see here is a pulse train. So each of the purple dot you see here, that's an independent laser pulse. So the laser we use is 70 femtoseconds. So if you want, your laser pulse is really an electromagnetic field that is 21 micrometer in length. So you're really sending photons over a very narrow space or extent in length. And so based on that, we are having this the system here. I won't go into too much detail, but we are using this gate here to change the time of arrival of my photon on my sample, and that allows me to reconstruct if I went through liquid or through gases. So here is the first data we got 2 weeks ago before we burnt the camera. You're sending a very powerful laser onto a camera, and we fried it fairly quickly. But to simplify, here on the left, on this first image, I'm going through the liquid, and then if I look later in time, I'm going purely into the gas. So here we just had a small cuvette, 1 centimeter in length, 10 millimeter, and we are scanning our laser as we are going partly in gas, partly in liquid, and we could reconstruct by looking at where the beam was and the time arrival of the photons if I was going into liquid or going through gas. So in a nutshell, that's what we have. We have been doing a lot of work on 3D measurements, extending those velocimetry techniques in 2D to 3D. I won't have time to go into details, but here are the same type of data I showed you to measure the shear at the liquid air interface that was planar. Now we have the same resolution. Really in 3 dimensions. So here the spacing between those series of vectors is about 500 micrometer, and the beamlet used to create those vectors. So that's lateral spacing is 500. In the world normal direction, the distance along one series of vectors between vectors is about 30 micrometer here, and the beamlet used to create those vectors about 30 micrometer as well. So we are getting into the 3D world fairly quickly, and I hope to be able to get some physics to you guys fairly soon, now that the tools have evolved quite a bit. So I will leave my conclusions here, and if there are any questions, I will be very happy to answer them.
Thank you so much. I don't see any questions in the chat. Do we have any here in person? Doesn't look like it. Okay. Well, that's not so much a question. I guess it is a question, but I can imagine it would be hard, if not impossible, to parse out whether you've had a ray go twice through one droplet or once through 2 droplets. Does it get to be impossible to really predict that once you get too many?
Yeah, so what you don't want the rays to look into this, right? You don't want the rays to go to, so if you see here, most of your photons will have this very energetic profile that is here, but the first photons arriving, that will be the one that go one time through the bubbles, okay? And then the second bump you see here will be the photon that went twice through a bubble. And after that, you cannot distinguish anymore. But the idea for me is to know what is my void fraction, what is this distribution of my bubble. So here I'm showing you some monodisperse distributions. But if I take enough data, I should be able to reconstruct the spectra of my bubble distributions.
Thank you. And thanks again for your presentation. I hope Roberto and Deepak were paying attention. We have some interest, like we always have some interest in putting a multi-fluid model into our codes. So that's some great data that you have that will be of interest in the future. Thank you. So next is Gia, who fortunately is in the presenter slot here. I can see your slides. Could you test your audio, Gia?
Can you hear me?
Yes, I can hear you. Thank you. Please begin when you're ready.
Okay, thanks. So thanks for inviting me for this talk. So we're going to talk about 100 years of scaling up fluidized beds. My co-authors are Wai Lemache and Ray Coco. So we put this together in conjunction with the Fluidization Centennial Special Issue in Powder Technology last year. 2022 marked the 100th year anniversary of the commercial fluidized bed reactors. So this means 100 years of scaling up and optimizing of these reactors. And the goal has been obviously consistently trying to reduce the time to market and to reduce the cost. And so if you kind of look at this chart, so the first commercial fluidized bed is the coal gasifier in the 1920s, and then FCC came along. This played a very important role in World War II. And then as we moved along and look to the future, you'll see that as we go towards having this cleaner energy, green chemistry, and circularity, fluidized beds continue to play a very important role. So why did fluidized bed become the breakthrough technology in these applications? So applications of fluidized beds, we kind of put a chart here of the various types, whether it's heterogeneous gas phase and so on and so forth at different temperatures and pressures. So fluidization has diverse applications in many of these. It has very diverse applications, and when heat control is important, when moving solids is important, fluidization is the technology to go to. So all of these processes are considered breakthrough. So some of these processes, as we'll talk about through this talk, started with some other unit operations, and then fluidization came along and disrupted the old technologies and became the dominant process. So despite the added complexity of operating fluidized beds, there are a lot of these high pressure, high temperature fluidized bed applications, as we see here. So then as the list continues to grow, even as we go towards energy transition, sustainability, circularity, we see a lot of new applications continue to rely or continue to try to develop fluidized bed processes for these applications. So this is the outline. We broke down the 100 years into kind of 4 eras, the early years up to 1930s, and then the second era up to the 90s, and then today would be the past 2 decades, and then we'll talk about tomorrow. And then the second bullet is going to be shorter. We're going to look at the challenges and how scale up has evolved. So let's look at the early years. So as this audience probably knows well, Winkler gasifier was the first commercial application. It was about 1921. And so the focus was on coal gasification, hydrogen for the ammonia plant and liquid fuels. And the key advantages over the traditional gasifiers is the good mixing, excellent heat transfer, and the ability to add coal and remove ash. So moving solids into and out of the reactor. And then a more sophisticated version came along. This is a circulating fluidized bed. So this involved additionally a cyclone, a loop seal, and heat recovery coil. And because it's a circulating fluidized bed, the throughput was a lot higher than the Winkler. and it gave a 15 times increase in capacity. So a higher temperature, and then in the 1950s, they also bought the rights to this Lurgi process. So this early years up to the 1930s, it started with coal, and the onset of fluidization actually saved the whales from extinction, because then coal became the fuel for street lights, and kind of replaced whale oil. And then as we kind of went along, the personal automobile industry started by Carl Benz in about the 1850s. And coal is not so good as a portable fuel. It can be used for trains, but then not so much for cars. And so then the drilling and the ability to drill for crude oil came along, and then the FCC and all those began developing. But then the coal gasification still continued, because most countries have coal, very few countries have crude oil. So then the Renaissance, obviously, this audience will know that this is one of the most important fluidized bed process. This helped the Allied forces win the World War II. So in 1920, Houdry came up with this catalytic cracking of oil. It provided significant yield improvements, but then the deactivation was very quick. And so in 1940, as we know, the World War II was starting. And so US formed this Catalytic Research Association. So all these companies which were developing these cracking on their own were forced to come together. All the walls were taken down. And you see that within 5 years, a very, very short 5 years, 35 operational FCC units became available in the US. And so this helped the Allied forces win the World War II, because this higher quality gasoline made the planes fly higher and faster than the German planes. And polyolefins came along. It started in the 1890s, but it was very, very difficult, and it was very, very expensive. So catalytic polymerization came along. And then polypropylene also came into prominence. And then Dow developed the loop reactor for commercial production. And this reduced cost by 75%, but then the scale up was problematic, and then you can have narrow distributions of the molecular weights. So Union Carbide then came up with the Unipole gas-phase fluidized bed polymerization reactor, and subsequently the brighter colors was developed, and by 2018, 40% of the polyethylene production is made using this process, this fluidized bed process. Acrylonitrile, 1930s. This was for synthetic rubber, commercialized in Germany. So this was very, very a very difficult reaction, highly exothermic. So it's very difficult to manage the heat. And then an alternative reaction route came by, a single-step process. But again, this remains problematic, because this process is very exothermic, so the heat management was a problem. So Sohayo in 1960 developed the catalytic oxidation process, and this high heat of reaction, it was very well managed by a fluidized bed, because this is one of the key advantages of fluidization. And today, 90% of this acrylonitrile is produced by this Sohayo process. So in this era, from 1940s, this was arguably the most important fluidized bed application because of its role in World War II, and it continues to be very, very prominent to this date. And then the catalyst development continued. We know polyolefins came along, and fluidized bed became a very good or very cost-effective process an easier to manage process for producing polyethylene and polypropylene. And then as we kind of went along, biomass, the greener energy came into play. And then the gasifiers continue to increase in the wattage producible. So in the past 2 decades, modern FCCs. So the FCC process are still very well in play today. And the designs have improved significantly. one of the key issues was to decouple the solid circulation and energy circulation. So it's a trade-off, right? The faster you circulate the solids, the more difficult it is to manage the heat balance. So these newer designs are able to decouple these two, and so enables a higher level of flexibility, and then structured packing for better mixing, and then better terminators for minimizing particle attrition and for better gas-solid separation. So pyrolysis, fast pyrolysis has limitations. So catalytic pyrolysis came along to address these limitations. And so it started with wood, and now there are a lot of other feedstocks, including plastics, recycling, and then coming up soon, or it's already in development, methane pyrolysis. Polysilicon, so in 1950s, polysilicon, so this is the feedstock, or this is the ingredient for semiconductor chips, and then for solar panels. So Siemens was developed in 1950s. This is a very, very energy intensive process, but very, very pure polysilicon. 1987, Ethel came with a fluidized bed process for producing polysilicon, and this is in Pasadena, Texas, and so the first commercial fluidized bed polysilicon production began, and then several other companies followed suit. And then in 2011, Samsung and MEMC had a joint venture for a new high-pressure fluidized bed reactor to increase the throughput for polysilicon production. Chemical looping. So this started in the 1990s by Dow and DuPont, and then now it's still being developed for natural gas combustion, hydrogen production, carbon capture. So this is a schematic Dr. L.S. Van's chemical looping combustion unit. So FCC, the improvement of FCC reactors continued. The green energy, the energy transition, solar, trying to make use of solar energy. The gasification increased in wattage. The worldwide gasification reached 285 gigawatts. And then, so this is Dr. Alice Van's Bright Loop CSC. We presented this at Fluidization Conference in May. He told us that this is going to be operational within 12 months. So that's today. So tomorrow, where is this heading? So as these very, very urgent issues of sustainability, renewable energy, green chemical circularity, all these new processes are still relying on fluidized bed reactors. So let's now kind of talk about a little bit quite quickly about the scale up. So the main challenges with fluidized bed reactors are the solids losses, because the particles keep rubbing against each other, keep rubbing against the walls or the internals. Attrition could be an issue if not properly managed. The entrainment rates in terms of solids losses, if it's not properly managed, you might suffer too much of these losses, and catalysts are expensive. Cyclones also need to be properly designed to manage these solids losses. So then as we scale up from, say, the lab to the pilot to the demonstration unit to the commercial unit, these have to be properly the skills, like the bubbles, because they determine the mixing and the residence time, they shouldn't change too much as you go to different scales. And then the bed density. For hydrodynamics, there's things to look out for, like fluidization regime, Gaudat group, mass transfer, bed mixing, and so on and so forth. So this is a chart for fractional conversion for heterogeneous first order reaction. You see that for a packed bed, it behaves like a plug flow reactor. Very, the conversion is excellent. Bubbling bed is not so great. And then there's turbulent bed and a fast fluidized bed. And then to kind of make a CSTR-like reactor behave more like PFR, we could stage CSTRs in series by inserting internals. So historical scale-up procedures, traditionally is by trial and error. You see here that the fluidized beds have been kind of behind. When plug flow reactors and CSTRs were scaled at 1,000 to 10,000 times, in the 1940s, these FCC reactors were scaling at factors of only 20 to 150 times from pilot to commercial scale. And then in the 1950s, fluid coking, it only scaled at 37 times. So these fluidized reactors are kind of behind if you compare it to the plug flow reactors and the continuous stirred tank reactors. And then, of course, everyone, since then, the demand for faster, cheaper scale up is very important. So this problem was thrown to the academics. So in the 1960s, a lot of focus was put on bubble behavior and bed density. 1970s, 80s, transport disengaging height, entrainment rate, cyclone design, jet penetration lengths. There are a lot of papers to kind of flip through it on these to try to plug the gap. And then in the 1990s, the scaling laws by Horio, Glicksman came into play, and then the compartment models. So all these fed into plugging this gap of this slower scale up to make scale up faster and cheaper. So for recent scale-up procedures, if we eliminate one scale-up unit, the savings is roughly about 3 years and 30 million. So it's very attractive, especially when we have all these very urgent climate change issues that we need to be addressing very quickly. So CFD, we can use CFD to make potentially bypass a step. PBM, population balance model, for example, for attrition to de-risk particle loss, and then experiments properly designed, and more emphasis should be on particle properties as applied to the hydrodynamics. So tomorrow's scale-up procedures in the late 1990s, the DOE came up with this Vision 2020 of implementing scale-up using computations. This has not really realized, but the experimental procedures, experimental probes, data analysis have improved. The models have improved in terms of CPU and also as well as the CPU, GPU speeds and memory architecture. Machine learning AI came into prominence, so it could kind of bridge a lot of lack of understanding in terms of first principles understanding, and then AI-driven optimization can be used for equipment design and flow sheet design. So in summary, fluidized bed reactors have been responsible for a lot of breakthrough technologies. It's used very widely, and we can expect more breakthroughs. So the first 80 years, pretty much Edisonian or stochastic. It's probably mostly a trial and error. And then the Renaissance era moved us towards a deterministic discipline. There were a lot of efforts into trying to get first principles understanding, but we are not quite there yet. So with ML and AI, the future is likely a combination or hybrid of stochastic and deterministic, since ML is stochastic, so it's probably a marriage between the two. So this brings me to the end of this talk. Thank you very much.
Thank you, Gia. I don't see any questions in the chat. Do we have any here in person? Okay. Well, I will ask one. So I don't disagree with you that the Vision 2020 didn't really pan out. But I guess my question to you is, what do you think is either the single biggest or some big reasons why that it didn't pan out, and what do we need to do to bring CFD into the design phase more?
To bring CFD into design, we work very closely with, for example, the CPFD guys. I believe Jim Parker is giving a talk sometime tomorrow or something. I guess the validation part has to be done right, and there has to be more the validation part has to be done right at each step, because for a lot of, for example, when we talk to a lot of our clients, they kind of think of experiments and simulations as two separate things instead of both going in parallel to kind of complement each other. So possibly a kind of a mindset change and in trying to do both in parallel rather than separately.
Okay, thank you. Yeah, that's a hard one to solve. Thank you, Gia.
Thank you.
Okay. Okay, we have Tai Yang. You are in the presenter. Oh, there you are. Yeah. Thank you. We can see you. Can you share your slides?
Yeah. So let me just share my screen. Ready? Can you guys see my screen now?
Yep. Yeah, we can see it. Begin whenever you're ready. Thank you.
Okay, thanks. Okay, so hello everyone. I'm Dan Zhang, and I'm a graduate student of Professor Caleb Brooks. So we are from the University of Illinois at Urbana-Champaign. Today I'm going to present some of our ideas and practices in collecting trans and two-phase flow data from some periodic flow oscillations. So let's just begin with some of the instructions. So if we look at all those system level analysis of two-phase flow, we'll realize that many of those system analysis code are actually built based on some stochastic and based on some deterministic and continuous formulations. And in the reality, the two-phase flow is, however, stochastic and complex with some small-scale randomness and some discontinuities. So those deterministic and continuous formulations actually developed for the mean flow behavior of those two-phase flow and derived based on some averaging procedures. The underlying assumption that the averaging actually removes all the discontinuity and gives you the mean behavior rather than randomness is actually not super trivial in the actual practices. Even the theoretical, so theoretically, regularly speaking, it actually requires both the time averaging and the enzyme averaging if you want to apply those formulations for the general transient. So in the actual experiments, we actually face a similar requirement for sampling sufficiencies. So if we look at all the current available techniques in measuring two-phase for this mean behavior, we realize that most of those techniques are actually developed with some requirement for the sampling sufficiencies, something like the bubble counts, measurement durations, the exposure times. And for the current presentation, I'll just talk about the one of the example case with the conductivity probe, which we will talk later as well. So the conductivity probe is basically point measurement device designed for the measuring the gas liquid two-phase flow, and it's basically distinguish the two phases based on their conductivity differences. This structure typically look at the left-hand side figure. It comes with like several sensors and with insulated coating and housed in a metal casing, and it's only the tip of those sensors are exposed to the fluid. When we are using those probes, we basically connect the fluid between the sensor tip to a common ground inside voltage divider circuit. When the sensor tip is immersed in the gas phase, basically this circuit is broken, and we measure high voltage signals from our DEX system. And when the sensor tip reattached to the more conductive and continuous liquid phase, we would get a low voltage signals. Essentially, every sensor is just measuring what we call the phase indicator functions locally. And with one sensor, we can actually get the void fraction by performing time averaging. If with two sensors, we can use the delay between sensor to get the gas velocity or the bubble velocity. If we have like four sensors with one leading sensor and three trailing sensors, their relative locations actually form three vectors. And those three vectors can be used as a base of the 3D coordinate system, which allows us to reconstruct all the 3D velocity of the bubble interface, and so we can further derive something like a mean individual error concentrations. So back to our current topic, the sampling sufficiencies. In order to use this type of device, the conductivity probe, this actually requires like thousands of bubble counts if you want to get a reliable measurement just at one point. And this typically leads to the measurement duration of around 1 minute or like 2 minutes. And for the steady state application, it's okay. The steady state is just treated as stationary ergodic process. However, if we want to do the transient measurement, and if you only have one single realization, you will face like somehow the awkward situations. So here's an example for the transient measurements. The left-hand side, this bottom figure is basically shows the actual phase indicator function signals we will measure from one of the sensors during our measurement of a traveling wave. This traveling wave residents at that location in around 4 or 5 seconds, and those are just the phase indication function. This right-hand side figures, they basically shows the void fraction we get by doing the running time averaging through these phase indicator functions. And we use different time windows. So this figure basically shows that only if we increase the time averaging window to around 1 second or 1.5 seconds, we can reach some of the smooth measurement that match our theoretical descriptions. And this becomes problematic for this case because this phenomenon itself is characteristic time is only around 4 or 5 seconds. If you choose like a time window of around 1 second or 1.7 or 1.5 seconds, you basically just blur out all the details of the phenomenon, and you don't even be able to resolve the edge of those traveling waves. And so how can we solve the problem? And the direct answer is that we should introduce the ensemble averaging back, just like what we do for the theoretical analysis. So here are some other examples. It's basically these figures are organized in a similar way of the previous one. However, now we have like 2 of realizations. The void fraction derived through the running averaging shown as the color curves, and the mean behaviors or the ensemble average behavior shown as black curves. And we have different time average windows, basically represented by each figures. We can see that the black curve, which representing the ensemble average result, is always much smoother than those of the single realization results. And then we also notice that now with the ensemble averaging, which adding the additional samples, we can actually reach some of the smooth measurement even with a time average window of around 0.2 seconds or 0.3 seconds. So based on this discussion or this idea, that's we think that the genuine way to collect the local chance and two-phase data should involve the ensemble averaging. However, in the actual applications, we know that the repetition of transients can actually multiply the cost and involves additional difficulties. Typically, for some of the traditional experiments, setting a target condition can involve many of the preparation procedures, such as the preheating, degassing, and also some fine-tunings. And it is also much harder to repeat than just hold the same set of boundary conditions, considering all the ambient temperature change or the limitation in the controlling resolutions and many other practical factors. So luckily, there are some of the flow that we can implement as they are actually beyond the steady state and they actually repeat themselves. By definition, those flows are actually the periodic two-phase flows. And from this perspective, we think that collecting the periodic mean flow is actually a good option to start collecting transient two-phase beyond steady state. And this is actually the basic idea and what I'm going to talk about the details for this current project. So essentially, these ideas demonstrated our practice on a low-pressure natural circulation loop in our lab. It's a 5-meter tall loop. And interesting with this type of loop is that when it is operated under low pressure on the natural circulation mode, it can actually experience some of the flow instability, which eventually leads to a periodic flow oscillations. So this loop looks like the left-hand side figures. It comes with like a 5-meter tall Howlett channel. This channel is basically an annular channel. It comes with 1.5 outer diameter and 3/4 inch inner rod. The first 3 meter is heated, and the other 2 meter is basically adiabatic. So we install some of the customized measurement devices along these Howlett channels. We call those measurement locations as the measurement ports. And on each measurement port, they have there are 2 traversing mechanisms. Those traversing mechanisms basically just move those point measurement devices, including the thermocouple and the connectivity probe, across the flow channel so that we can also capture the radial structure of the flow. We also install some of the direct visualization viewports along the channel so that we can perform the video taking or direct visual inspection or even some high-speed visualizations. So a little bit more detail about the instability we see in those type of the flow. Those instabilities are called the flash instabilities. They are basically the low pressure natural circulation instability, and it occurs when the facility is operated in a transition stage between the 40 single-phase natural circulation and the two-phase natural circulation with falling happening inside the heated section. So between those 2 stages, there's some transitional stage. You would expect the saturated vaporization actually initiated inside the adiabatic chimney. That's just because that under low pressure, the saturation temperature has a very strong dependence. Saturation temperature has a very strong dependence on the pressure, And along this 5-meter tall channel, due to the gravitational pressure drop, the saturation temperature at the top and the bottom can have a difference like around the 10 Celsius degree. While subcooled liquid leaving the heated section can actually become superheated inside the adiabatic chimney, and which causes a very rapid vaporization or sublimation. And this type of flow is unstable, and it can lead to some low frequency oscillation, typically range from the period of this oscillation typically range from 7 seconds to 30 seconds. And those oscillations can be very strong. And some of the, as an example, that some we can measure some of the inlet velocity variations that range from 0.2 meter per second to 0.8 meter per second just in the experiment. And that's quite different from the steady state, which is good because that's our target. So our measurement methodologies. So the basic idea of doing the measurement or extract all the realization is that we treat each oscillation cycle as a different realization of this type of the mean flow behavior. So what we do is that we choose one of the signal, like one of the global parameters, as a natural oscillation phase indicator. So for this example, we choose the pressure at the inlet, or what we call the system pressure. You can always choose all the other signals like the inlet velocities or the pressure drops through some of the inlet flow resistance, as long as it has a very clear patterns, such as the very large peak or some other behaviors that is very clear. So what we do is that we measure all the other signals simultaneously with this phase indicator signals. So for this example case, we show how we do the measurement for the local temperature. We measure the local temperature for some iterations. Then we can use the traversing mechanism to move those measurement point to another locations. And we always do the measurement together with this phase indicator signals. And then eventually what we do is that we use some of the peak detection techniques or some of the techniques based on the maximization of cross correlations. We can actually identify the beginning and the ending timestamps of those oscillation cycles. Then we basically slice all these signals, and using the same timestamp for the other signals, we basically cut all the oscillation cycles out into some of the signal segments. Then we basically lumping all those signal segments onto one representative period. On this representative period, we can do all the ensemble averaging and get our results. And how does this method perform? Essentially, this is what this slide are showing. So the first row basically shows all the aligned signals, and we do the measurement for the pressure. This is the pressure drop through some inlet flow resistance, and this is the inlet velocity, and this is the absolute pressure measurement. These color lines, they're actually the measurement for different oscillation cycles. There are around like 200 oscillation cycles overlapping together, and the dashed black lines, they represent the mean behaviors we get from the experiment. And in this figure, we also show the measurement for the local wave fraction, and this is actually at the end of the channel and at the center locations. And for the radial measurement, we can actually do like over 10 realizations for each local measurement. And also, since we do have the ensemble averaging, we can quantify the uncertainties by doing the combinations of the instrumentation uncertainty and also some of the random uncertainty based on the calculation of the variance. So this is another demonstration of how our data looks like. The first column shows the measurement of the void fraction at 5 different actual locations, and also with 10 radial locations. Essentially, all the different colors they represent the measurement at different radial locations. And the second column shows the similar measurement organizations for the fluid temperature. And by doing some of the area averaging, we can also provide the data that can be used for the one-dimensional system as a code for the validations. We have the area average void fraction as well. We have the area average temperature as well. We have the pressure measurement, pressure difference, and inlet velocities. And a good thing with this type of the data is that we only use like 5 probes, but we actually measure like 50 measurement locations because we use the traversing mechanism, and also we are measuring the periodic behaviors, which allows us to automatically synchronize all the measurement at different relay location to one representative period. So this is the measurement result, but we show it as some of the animations. It actually provides quite a lot of details for this type of transient behaviors. We have all the measurements and we can even do the synchronization of the videos as well, as long as we can synchronize the clock of our camera with the clock of our computer or the DEC systems. And we can see it basically shows all the detailed behavior of the mid-cycle oscillations of the flashing instabilities. And we can also use this type of the data for the code validation, and we actually did it. So what we do is that we test the code performance of a code that is called Advanced Fluid System Thermohydraulics Analysis version 3, or what we call ACE version 3. It's basically a system analysis code that's quite close to the relap. They have same modeling methodologies, and they have even compatible input and output. So we can do some of the modeling for a single channel. We can also do the modeling for the four systems. For the single channel, the code can be used for the validation by providing the precise periodic boundary conditions, and we can check whether the code can reproduce the detailed two-phase phenomena inside these single channels. And as those codes are designed for system analysis, they should be able to capture the systematic behavior as well. So with a for-loop model, we can check whether the code can predict the stability and predict the limit-cycle oscillations as well. So here is the result with the single channel validations. What we are seeing here is that those curves are actually coming from the simulations, and all the points are from the experiments. We do see some of the detail difference. For example, here we see like a traveling wave of void, but in the simulations we don't see it. It's just because probably the system analysis code is actually over predicting some of the condensations, and this traveling wave behavior is actually a transient behaviors. And so with this transient data, we can actually do some of the comparison to the code. This is another example that we are doing some of the comparison to the for-loop models. First, we can do something like the validations for the prediction of the stabilities. We are basically showing the comparison of the simulation results and our experimental stability boundaries. And this right-hand side basically shows the simulated systematic behaviors and its comparison to the experimental values. We do see that for some of the cases, the code actually predicts the natural circulation patterns quite well. And based on the detailed measurement, we also know that it's not basically just matched to these style patterns with some unphysical results. It actually predicts the detailed two-phase traveling waves quite good. So as a summary, for this project, what we want to show here is that if you want to use the measurement of transient two-phase flow to capture some transient mean behavior, you may have to consider the ensemble averaging. And the periodic flow condition is actually a quite useful and valuable candidate for you to choose to begin with the measurement of the transient two-phase flow beyond steady states. And we've shown that this is basically doable, and this data they can be used for the validation of system as code. And for the future application, those data can also be used for some of the development of new techniques for the transient measurement of the two-phase data. So that's basically conclude my presentations, and thank you for your attention, and please send me any questions.
Thank you, Taiyan. I don't see any in the chat. Do we have any in person? So I guess my question is that code that you mentioned, I assume if it's like Relab, it uses static flow regime maps.
Yeah, I think the code is basically, like it's like something that's branched out from the Relab. So they do use the static, they do use the similar treatment for the flow regimes.
So is there work in your group to use interfacial layer transport equation to try to predict this? I don't even know if that would really.
So we do have some of the students that were previously working on using the interfacial various the IETs with all those one-dimensional simulations, but we currently we don't have those work that's actually coupled with this data set. No.
Okay, thank you. And with that, I'll thank you and all of our presenters in this section. I think we have most of a 10-minute break remaining before continuing with the afternoon session. So thanks, everyone.
Hello, everyone. I hope you can hear me. I was going to get the next session started, the last session of the afternoon. We have a nice lineup of presentations. Sundaresan Sankar from Princeton. It looks like you're ready to go. Is your audio working?
Can you hear me?
I can, and I got your slides. And I'll just want to take one more second to remind everyone to please send in any questions you might have to the chat, and we'll try to make sure if there's time to get those addressed, or after this Sundar is gone, he can address those in the chat too. So thank you. Sundar, if you have the floor is yours.
Oh, thank you, Janine. Hello, everyone. I would like to share with you my thoughts on contact charging in particulate flows. For the last 20 years, we have worked on trying to understand interparticle forces and how they affect the flows of gas particle mixtures. There are three types of interparticle forces that one can consider, which we have studied in our group. One is van der Waals interaction, liquid bridge force, and the third is electrostatic charging of particles and how it affects the flows. And in today's presentation, I'm going to talk about the third one, electrostatic charging. So I'll give a brief review first, and then I'll share with you some results on charging and the effect of charges, and I'll end with some questions. That's the plan for the presentation today. Tribo charging causes particles to stick to the wall. So when the charging is acute to the point that we can actually see them, this would be an example of that. Here is an illustration that comes from a paper published by Alyssa Park and L.S. Fan, where they're trying to do some measurements, and then the polymer particles in the bed are sticking to the probe, as you can see in here, which makes the measurements difficult. In a study that comes from Marani Pupap's group, where they have flow of polymer particles in a riser, some of the polymer particles are sticking to the walls of the pipe, where you can see the white deposits here. That again is due to electrostatic charging causing the particles to stick. We did some work where we collaborated with the research group in Finland, where they did some experiments over there, and we did some experiments in Princeton and some modeling. And here's an experiment that they did in Finland, where you had a fluidized bed, and they had you can look at the top of the fluidized bed through the illumination on the camera, and then the right-hand side figure shows you what you see in that. You can see that layers of particles adhering to the wall. So again, this is again polyethylene particle on a glass container. So you can see that when there is acute amount of charging, that to the point where the particles stick to the wall, that you can see them, then you know that the charges are affecting the particulate flows. But the particles, they don't have to necessarily stick to the wall, but you can still see how it affects the flow behavior. And here is a simulation that came from University of British Columbia, where they looked at how particles, the bubbles form and flow when the particles do not carry any charge versus when the particles carry charge. When the particles carry charge, an electrical field automatically develops, and the electrical field affects the motion of the particle, and that then changes the nature of the bubble flow, as they're illustrated from in these two slides that I'm showing here. And here's an experiment that we did in our group, where we find that here we have a glass container and polyethylene particles, and we fluidize them with air, but they have two different humidity levels. One is 20%, the other is 60%. So when you do the fluidization of the 20%, and then you do the fluidization of the 60%, you can see the 60% humidity level bed fluidizes more vigorously. The 20% bed actually began behaving like the 60% bed, but afterwards it settled down to a lower level, and it did not behave fluidize the same fashion as the 60% relative humidity bed. So what's the difference? Well, the humidity can affect the amount of water absorbed and cause liquid bridge to form. But if it were due to liquid bridges, I would have expected the opposite behavior: more humidity, more liquid bridge, and so on. But here it's opposite of that. So if you take the particles out and then if you measure the charges, you find out that these particles carry a lot more charge than at 20% humidity than at the 50% humidity. And it is a charge difference that is affecting the flow behavior, even though not many particles are sticking to the walls. So we can ask a bunch of questions. One is that what are the typical charge levels? Can these charge levels affect the flow behavior? If so, then how do you model them and so on? I'll come to that as we go by. So if you look at the literature, and then you find that depending on the material, you can have a wide range of charging of particles. Typically, they tend to be of the order of microcoulombs per meter squared. It can vary from 0.1 to 10 microcoulombs. And the number I showed you in the previous slide was sort of in the middle of this range. So now that we know that these numbers can be like this, can it affect the flow behavior? So now keep in mind this number, 0.1 microcoulombs per meter squared. That's the low end of the range that you can find in the literature. So one of the questions that people have often wondered is that when you have fluid particle flow, gas particle flow in a riser, where we know that the particles segregate towards the wall region, what causes this segregation? One of the mechanisms that can drive this is aerodynamic in nature, where particles form clusters and streamers, and the clusters get pushed to the wall, and they form the particle-rich region near the wall. And when that happens, the particles can fall down near the wall, while in the core region, the particles are going up, while the overall flow of both the gas and the particles are going above. So we asked the question that can electrostatic charging cause this kind of a radial segregation for realistic charge values? So we set aside these aerodynamic fluctuations. We assume that we have fully developed flow, particles carry a constant charge. We simply specified how much gas and particle fluxes are in the system and how much charge the particles carry. And then we just solved the Poisson equation for the electric field and the steady state axial and radial momentum balances. This was something that we did 20 years ago. And what we found was that the problem is actually described by one parameter, Q, that tells you about the charges, and two parameters that tells you something about what is the gas flow rate and what is the solids flow rate. So for specified values of solids flow rate and gas flow rate given as US plus and UG plus, we can ask the question, what happens if the particles carry more and more charge? That means the number Q becomes larger and larger. Q can become larger when the particle surface density of charges go up. I told you before that sigma is in the range of 0.1 to 10 microcoulombs per meter squared, and R is the radius of the tube. So larger and larger the tube, larger the value of Q is going to be. So if you look at an experiment that was done at PSRI, the 15 centimeter diameter pipe, a typical FCC particles, and if you assume that lower end of charge range, you find out the Q is of the order of 1,000 when you plug all these numbers in. So just remember, Q is of the order of 1,000. So we asked the question, what will happen when Q is varied between 0 and 1,000 to see how it affects the flow? And what we found is that for a specified combination of gas and solids flow rate, here I show you the results for two different combinations. And what is the average solids hold up in the cross section of the riser in a fully developed flow? As you vary Q, you find that when you increase Q, then you start getting this complex behavior. And so you can see that depending upon the level of charge, that means the value of Q, you can have very different solutions. And so I'm showing you that is the solution profiles for these 4 points A, B, C, and D in this diagram. And the red circles are the experimental data of Bader et al. So when there is no charge, this simple model tells you that there is no profile. The concentration is uniform across the cross section, but as the particle picks up more and more charge, the profile becomes non-uniform with more particles near the wall. And at some values of charge, you can get something that looks something like the experimental data. And indeed, what you find is that correspondingly, you can get downflow near the wall as well. So you can capture those types of flow behavior. And I presented this result in one of these MFTRC meetings, and because there was a lot of discussion at the time as to charges are important or not, and so we came and presented this. And but then afterwards, there was not much of enthusiasm for this, so I stopped that. But then about 10 years ago, we started returning to this problem, and we asked the question because the people are beginning to think that maybe we dismissed that too much. So going back again, is the charge level? The answer is yes. So people have been asking questions for the last 15 years. How do you model these tribocharging particles picking up charges? And then how does the effect of gas, humidity, particle size, and so on affect the charging behavior and also the consequences of charging behavior? In today's presentation, I'll only talk about the effect of gas in the interest of time, but we have published on humidity and particle size as well. So let me talk about how do you charge this tribocharging rate. So to do that, we just published a paper in the last couple of years, is that we took a bed of particles, and then we took a square cross-section bed for the sake of ease of simulations. The bed is made of PMMA, acrylic bed, and then we did experiment with glass particles or polyethylene particles of different sizes. So we put them on a vibrated bed, we cover it up, and then we shake it. The particles make lots of contact with each other and also with the wall, and then they accrue charge after 5-10 minutes. We make sure that we have shaken it long enough so that the charges have equilibrated, and then we measure the charge using a Faraday cup. We also do complementary DEM simulation, CFD DEM simulation. The CFD part is incidental in this case, not very important, it turns out. The DEM simulation with different types of tribocharging models to see whether we can use the experimental data to determine some of the model parameters that are associated with the tribocharging process. So first, here's some experimental data. When we did the experiment with dry nitrogen, we do them all in a hood, but even dry nitrogen is not fully dry. If you look at the humidity probe, it will tell you that somewhere between 2 and 5% relative humidity. And then we did dry argon, which again tend to have 2 to 5% relative humidity according to the humidity probe. So you find that if you look at the particle charge, which is measured by the Faraday cup, versus the mass of particle, which we convert to surface area, external surface area of particle, because we know what the particle size is. And if you plot them against surface area, you find that the red symbols are for nitrogen, and they're for 2 different particle sizes, and the blue symbols are for argon. The thing to note is that the argon, in an argon environment, the particles acquire a lot less charge. And if you do the same experiment instead of glass particles with polyethylene particles, you find that, again, the glass particles acquire more charge compared to the polyethylene particles acquire more charge in nitrogen than in argon. Okay, the difference between these two is that in the glass particles acquire positive charges while the polyethylene particles acquire negative charges. That's the only difference. So the main message is that the charge levels in argon are lower than that in nitrogen. So we asked the question is that if you have data like that, how can you use simulations to help us learn something about the nature of the charging? So if you look at how tribocharging models have evolved, they say that when 2 particles come into contact each other, they can transfer charge from one to the other. This can be 2 particles or a particle and a surface, in which case surface is treated as a particle of infinite radius. So you find that there is a quantity called effective work function difference that tells you whether charges want to go from one surface to the other. And it also depends upon what is the prevailing electric field at the contact point, which tends to either help or work against the charge transfer. So this effective work function is kind of a lump parameter, averaging over all of our unknowns as to what is causing the problem. And there is a separate field of research of trying to understand exactly how the charges are actually being transferred, what is the charge transferring agent, and so on, which I don't want to get into. But the effective work function is a phenomenological parameter that is used to fit the data. That is a property of the material and the particle size that we are looking at. There's also a time in which the people noticed that when the two particles come together, they pick up, the charge transfer occurs. But when the two particles come apart, the charges relax back. And the Laurenti et al. Came up with a model for the charge transfer, and the charge relaxation was modeled by Itakura et al. Quite much earlier than that. So these two are models that are available. But if you only use these two models and try to reproduce our data, it turns out that we cannot, because they would predict that you would get the same extent of charging in both argon and nitrogen. So we had to recognize that the dielectric breakdown strength of argon and nitrogen are different. And so when at the interface contact between the particle, the electric field reaches this value or is predicted to exceed this value, a dielectric breakdown will occur, and then a charge will get transferred to try to bring the local voltage down below the dielectric voltage trend. So we added a mathematical component to capture these effects, and I'm not going to go into the details of the math in the interest of time, but we can allow for charge transfer, charge relaxation, and dielectric breakdown in the gap between the particles. So when we do that, we can then begin to see whether or not we can capture the effects. So what we do first is that we analyze the nitrogen data. These are results for two different particle sizes. What we find is that in the case of nitrogen, in that small experimental system that we had, hardly any dielectric breakdown occurs. And then we were able to fit all the parameters that are associated with the model to try to fit those two curves. And once we fit those parameters, we hold them constant and simply change the dielectric strength of the gas from that of nitrogen to hydrogen. And then the model predicts that these curves will collapse down to this level, which is closer to the experimental data. So again, we had some parameter fitting to fit the red or the orange circles and squares, but we did not have any adjustable parameters when we tried to fit when we tried to predict the blue data points. So it just shows that our approximate model to account for the effect of the dielectric breakdown captures the results that are there in this system. We did the same thing for polyethylene particles, where we fitted the particle properties, the effective work function to be precise, to try to fit the nitrogen data, and we were able to predict the argon data. So what it tells us is that you need a combination of tribocharging, which is empirically modeled using the effective work function, charge relaxation, which tells you how charges flow back, and third one is dielectric breakdown. So if you consider all three of them, then we are able to predict the experimental results in a number of our experiments, like I illustrated here below. But if you look at the kinds of surface area that I'm talking about here, they are quite small. They're only 400 centimeters squared. So if I consider a real fluidized bed, even a laboratory fluidized bed, I'm going to be way to the right of this axis. So I'm going to be going way to the right. So what will happen to these curves if I extend to, instead of 400, what if it is 40,000? Which means that a lot more particles are in that system, or 400,000, like a real large fluidized bed. And so if you look at this and try to analyze this, and this is something that we did in a joint work with the Xiaotou B's group in UBC, and we published a paper on that. And what we find is that every system, even the nitrogen environment, when you go to a large bed, the dielectric breakdowns are going to become important. And to the point where in large process vessels, the particle charge level is at the cusp of dielectric breakdown in most systems. So if you imagine a fluidized bed in the lab, the dielectric breakdown is constant, not in a very small laboratory experiment. I'm talking about in a pilot plant experiment. The particles are charging, dielectric breakdowns are occurring, but they are occurring in a way that is fast and to the point that where we cannot see them. If you can see the effect of the spark, that means it's clearly there. But even if you don't see it, this is happening all the time. And that's what we think is happening in the system. So to summarize, we have been studying the effect of interparticle forces on gas particle flows. And this particular talk focused on how electrostatic charging in fluidized beds occurs, and then how do you model them. Electrostatic charging affects the rates of elliterations of particles, rates of segregations of particles towards the wall, and if you have bipolar charges, particles can form clusters as well because of electrostatic charges. So this can affect the flow, and I gave you some examples of how it can affect the flow. And to really take it to the next level, we need to have better understanding of the charge transfer mechanism. What we have done is use some phenomenological parameters like the effective work function. But what does an effective work function mean for dielectric particles like polyethylene or glass is a big question. And what exactly is the species that is being transferred? A lot of work is going on, but it is still not very clear. And we do know that changing humidity or adding electrostatic antistatic material affects the flow behavior. So how does it affect is something that we need to understand. I've cited a couple of papers that talk about humidity effect and particle size effect, but we need to understand them better. And the interesting thing that we find, we are making a prediction is that electrostatic breakdown is always happening, irrespective of what the gas is in a real large fluidized bed. And you can use that statement to predict how much charges there are in large bed. And we don't know how much of that's true, but that's the hypothesis that I would like to propose, and then see where it takes us. Thank you for listening. That's all I have to say.
Thank you, Professor Sundaresan. There is a question in the chat, so I'll direct you to that to maybe start answering questions as they come up, but I'm going to move on to our next speaker just to keep us on schedule.
Sure, thank you, no problem.
Thank you, it's very interesting, very nice.
Okay.
And Joseph Defek from University of Oregon is our next speaker.
All right, let me just pull up the talk here.
You know, if it makes sense, I don't know if Professor Ahmadi is here. Maybe we can switch slide and just give you a moment to load those up. Would that work?
If that works for them, yeah.
Professor Ahmadi, would that be all right with you?
Sure, that would be fine. Certainly, I can start. Yeah.
Okay.
Yeah. Let's just rotate and just give you a chance to work out the technical challenge.
Okay. Thank you.
And so I guess we will just move to the next speaker and come back to Defek for those who are just joining us. And then we got your slides. And you are welcome to start presenting when you feel comfortable. Thank you, Professor Ahmadi, for being flexible.
Thank you very much. Okay, well, okay. I'll be talking about modeling of dilute two-phase flow with application to transmission of respiratory viruses, with some connection with coronavirus. And let me get started with that. So those are the sort of list of topics I'm going to go quickly through. We'll talk about dilute particle laden flows, computational modeling of the fluid flow, aerosol motion, and then talk about how aerosols are generated by speaking, coughing, and maybe sneezing, and then give you a few examples basically of different applications, and then conclude. Obviously, for this group, excuse me, direct numerical simulation is probably most accurate, that you can generate all fluctuation of turbulence, these tiny droplets that leave the human mouse or animals. They are very small in the micron, submicron, nanometer ranges, and therefore they're affected by turbulence quite a bit. The next level, of course, is large D simulation, still computationally kind of extensive, and we need to develop some subgrid scale model that's being researched these days. And there will be, again, another paper in this regard, in a next session, I think. A RANS model for practical situation, or probably still for application large scale, large room, classrooms, cars, and other stuff, is probably the method to use. And in those cases, is important to account for the subgrid, essentially fluctuation of turbulence. That dispersion effect is critical for this. I'm going to show you only one equation, and that's the equation of a particle motion in a dilute case. So it's no interaction between particles. The Dirac force, Lift force, gravity, electrostatic, which someone just mentioned, and also a Brownian motion could be important if you're dealing with nanometer range particles. And I'm going to show you one example of critical research issue. Is this plot is actually has a lot of data on it. I apologize. It shows the deposition velocity, which is essentially flux to the wall, per unit area, and normalized by shear velocity versus particle relaxation time, which is down here. It's tau plus, which is proportional diameter squared times density. And you can see the experimental data of a collection from a variety of sources shows a U-shaped variation for very small particles, nanometer range. Brownian dominates and is important, and the deposition increases. Then it decreases around about 0.1 to 1 micron, and then again increases again for larger size. This large increase here is kind of somewhat unexpected, maybe because the particle become larger. Nevertheless, the diffusivity increases and you get more diffusion because of the interaction with essentially turbulent eddies. Now, modeling this, the various models have been developed in the literature, some of it by our group. We can do a reasonable prediction, but if you use some of the, standard commercial code, which are the two lines, the blue and red on the top, shows that, the deposition could be overestimated by a factor of 100 to 1,000 times in certain particle size range. For large sizes, we do very well. Small sizes, reasonably well. This is in the range of the order of maybe, 100 nanometer to about 10 or 20 micron range, that there is a big difference there. And to be able to correct this, we have been working on this quite a bit, and there are several references I put here. And if you do it correctly, you can get this U-shape predicted, basically, but this black kind of circles here, which is the normalized CRW model, we called it. But the standard model gives you quite a bit of error in this range, and this is critical for the aerosol and viruses because they are in this sort of size range. I'll give you just a little hint. Of course, you can, more details on it. But one reason is very close to the wall. Velocity fluctuation perpendicular to the wall is proportional to y squared, and that comes from the conservation of mass and discussed in literature long ago. And this is somewhat difficult in some of the commercial code to account for, and that gives, quite a bit of overestimation. That could happen. And then there are also some more refined points which are in the so-called normalized CRW model, which are just appeared in the last couple of years to make it more refined. But anyway, now I'm going to give you a bunch of examples. These are two people sitting across a desk, and one is coughing or speaking and releases a bunch of droplets. And if the person has some flu or corona or something, these viruses are transported inside the droplets, and if the other person inhale those, the chances for getting sick increases. This is another one, sort of two, in a hospital room, two people are sitting, and one may have some respiratory diseases. Again, one can, use CFD and hopefully correct them properly, try to estimate the risk for the other people. And general idea is to design air conditioning system for these units so that the chance of exposure decreases, basically. This is an example of a respiratory tract from nozzle passages toward the trachea and down to the top few bifurcation of the lung, that you can again trace the particles and see how basically droplets or particle transfer through those. These models have been extended, becoming larger and larger. We can go deeper into the lung, and here is a passage, a review article that Tian and I wrote a couple of years ago, that would go up to about, maybe 7 or 8 or 10 generation in the lung to get more details. Okay, coming back to the transmission of infectious diseases, if you remember when COVID started 3 years ago, the first impression was it's by direct transmission by touching, essentially. And the idea was we should wash our hand constantly, make sure there is no, viruses get to our hand, so we touch some face or something. Later, it was realized that aerosol transmission actually is the main cause. And this is through sneezing, coughing, and speaking that droplets comes in, and then air conditioning system and the flow move them around, and people at different location could get infected. There's, it's a quick review of literature. This is the size distribution during coughing, which is peaks at about 12 to, between 6 to 20 micron range droplets. And this is Doge's paper long ago. And the top figure is the sort of the velocity, volumetric flow rate during sneezing, about half a second or so. The peak is of the order of 4 meters per second and things like that. There is also data for speaking. If people sneeze or cough, you realize that they have some issues, so you can stay away from them. But speaking might be more difficult. But and there are more data here from Asadi and Wexler. The peak is of the order of 1 micron. If people speak louder, you get more intensity, and if you use quieter, is lower intensity, and that sort of shows the trend. And these are actually these days, as almost everybody knows, they have to stay 6 feet apart to reduce the chances, based on the work of Wells, which was done in 1934 actually. And he sort of understood that the droplet, when leave the mouse, they evaporate, and if they're very big, they're going to fall to the ground. So basically what he calculated was, in this schematic graph here, is large particle drop to the floor, small one evaporate. And then, if you find essentially, what's the maximum or the suitable distance to stay away is about 2 meters or about 6 feet. So that the particles, droplets, are either evaporate or the only issue here is when the droplet evaporate, the viruses and are not going to evaporate, so they're going to become essentially tiny nuclei, and it can stay in the air for a longer period of time. All right, well, now we have, of course, much more tools like CFD tools and so on, and we can try to look at more carefully what's going on. Here is a small office actually in EPA. There are 2 mannequins are shown here, very simplified mannequin. One is, on the right, for example, maybe coughing or speaking. And then the question is, what's the chance of the other mannequin get exposed to, to respiratory droplets carrying viruses? And there was some kind of partition here. And at the time, EPA was interested to see if we increase the size of the partition, would it help reduce the chance of infection? And this is a flow modeling here that shows this picture essentially use the condition of that room, and then and this is for air change rate of about 2.4. That means every hour the air is exchanged 2.5 times. These are velocity magnitude contour in the room. We can see that person in this case is speaking. This is the air conditioning system that has high velocity coming into the room and so on. And this on the other side is essentially the outlet flow. And you can see that near the next person or on the other side, velocity changes and depends on the air conditioning and so on. It will vary. This is a concentration of 1 micron droplet if somebody is speaking, and the peak is about 1 micron. You can see, of course, here we cut the level of the level to very low, about 10 to the minus 3, and these are relative to the concentration at the mouth of the speaker. And you can see that, near the speaker, of course, concentration is high. As you go further away, it drops, and near the other person, the concentration varies. And here we found the average concentration is in the range of about 0.003 to 0.0335. So about 3 over 1,000, average concentration is the other person is exposed for the condition we have done here. If you go to much larger, somebody's sneezing maybe and so on. Of course, this is with a low velocity here, not the actual velocity. Sneezing is much higher, is of the order of 20, 30, and sometimes 50 meters per second. These are at much lower velocity, and most of the large droplets fall to the ground, basically. Then we did another example here, which is the larger EPA room with 9 persons sitting working on a desk. And then we looked at each one of these persons are maybe speaking, talking on the phone, and just, releasing droplet. Then what are the chances of the other people get infected? And there are a linear diffuser here, and there is a regular inlet and also an outlet here. So these are all sort of based on the standard that was in that room we used here. And this shows, again, the velocity magnitude. This is for air change rate of 4. And the mannequin number 4, which is the one in the middle, we went from the top, from the front to the back, 1, 2, 3, 4, 5 is in the middle one. We have done it for each one of those, of course, but the one in the middle one, if you can see carefully, you can see that there is a little red close to the mouse here, which is essentially the flow comes out. And so we can find the distribution of the flow in the room and also then look at the concentration, for example. This is again the concentration level near the, emitter is quite high. As you go further away, it drops. And we calculated maximum and average concentration at different location of the other people sitting in the room. And the average concentration here is written down is 410 to the minus 4, for example. And then if you use a fully mixed model, which does not do fluid mechanics, it just averages everything. Again, we can actually calculate the value, which is about, in this case, is about 6 or 7, 10 to the minus 4. This is just a bar chart showing, the emitter is in the middle, and we are showing for different partition here, 56 inch and 64 inch, and also the maximum and average concentration. Near the emitter, of course, we cut it because this is huge value just to show where the location is. And at the different other location, the other 8 location, we can look at the concentration. And what you see is typically as you go further away, it decreases. The other thing we found out is actually the airflow condition is very important, and so air conditioning design can have a huge effect. For example, in this figure, as you can see, the air conditioning system moves the essentially the cough droplets backward toward the person in the back. And in this figure, sorry, where am I here? Okay. Sorry, it's okay. You can see here that, the emitter, essentially the person in the back gets more exposed rather than in the front, for example. And this is because of the airflow condition in the room. This is the similar graph, except here, is a 9-person room, and we have the air conditioning ratio is again 4 here. The size of the particle are here larger, in this case 10 micron, and you can see that it drops very rapidly as you go further away. With a couple of examples on coughing here, this is the person in a 2-person office coughs, and it's of course a short term, and then it decays after a while. And this is the same thing, except use the larger size here, 20 micron droplets, to see how they decay, basically. There are a variety of things one can look at, and don't have a lot of time to go through all of them. This is a little bit more fancier simulation with more realistic mannequin shape between, and different ventilation system. The picture on the left are for mixing ventilation, and the one on the bottom right is displacement ventilation. Displacement is more effective to remove the droplets typically compared to the mix. Mix essentially mixes everything, and everybody gets roughly uniformly exposed. And this is actually another study that was done again just recently. It's in a room, a classroom, and the teacher is speaking up front. And in this case, actually, is coughing. And then, we are looking at, how the droplet disperses in the room, and we use the cases that there are shield near the chair and not. And you can see at different time, short time, the concentration is near the teacher, and as time increases, it spreads. And finally, after about, 10 or getting to about 25 seconds, it decreases and finally decays after 50 seconds, essentially. To summarize is, for the transmission of diseases, aerosol transmission seems to be the main mechanism for spread of respiratory diseases, including COVID and flu and other respiratory diseases. Concentration typically decreases with the distance from the source and also with the increase of ACH. So to have a safer place, you want to increase the rate of essentially exchange of the air. And then computational modeling could provide insight into the developing medication against aerosol transmission. And thank you very much. If you have any question, I'll be happy to answer. And or you can email me at gmadi@croxton.edu.
Thank you, Professor Ahmadi. Do we have time for maybe a question if anybody has one? I don't see any in the chats, but they might come through. Professor Ahmadi, if you can monitor that as well, you can bring your attention to it too.
I'll take a look at that. That's an issue.
It looks like you have a number of scenarios you could explore with varying complexity. Did you are you still pursuing this work?
Yes, we were studying different geometries. I just showed a couple of examples. Yes, definitely.
Very nice. Well, thank you. I'm not sure if Professor Defek has had a chance to rejoin us.
I did. We'll see if it works. I did also sent the slides to Karen just in case, so we'll see.
Okay. Let's give it a try real quick and we'll get back on order.
How does that look?
I do see your slides. And
Okay,
thank you, Subar, if that was the trick. I'm not sure, but looks like you're good to go.
All right, excellent. Thank you. Yeah, and thanks for the swap up here. Thanks for organizing the session. What I want to do is talk to you a little bit about some of the multi-phase dynamics in volcanic eruptions, specifically explosive volcanic eruptions. And I think a lot of the dynamics will share a lot in common with things we've discussed. And then there are, of course, some other things that come up because of scale, which are, I think, interesting and push us on interesting parts of the physics for multi-phase flows. But to get kind of everybody oriented with this perspective, here I've shown a picture of the eruption of Mount St. Helens in 1980 with a little cartoon superimposed. And the zeroth order thing going on here is that there's this silicate melt that has dissolved volatiles in it, primarily water, carbon dioxide, sulfur dioxide. And when that's decompressed, those volatiles exsolve, creating a more buoyant mixture. So it's a really, really viscous melt plus gas mixture that eventually goes through the yield strength of the material fragments and then accelerates rapidly at high pressure, typically up to a choke condition, so speed of sound condition as it exits the vent. And then you have this mixture of particles going up into the atmosphere. If it entrains enough air and it's warm enough and buoyant enough, it'll form a plume that will go high up into the atmosphere and cause air traffic issues as well as respiratory issues and in some cases very large eruptions that can get up to the stratosphere and have implications for climate. But if it doesn't, it'll collapse back down and form these pyroclastic density currents, which are ground hugging currents. And there are, of course, a rich amount of physics that can go on in these flows. And I've kind of illustrated some critical moments in these. I'm only going to talk about two today, microphysical interactions, excuse me, and entrainment and pyroclastic density currents. We're typically interested in microphysical interactions for two reasons. One, they can change the dynamics of the flow. These are small scale processes happening at the scale of volcanic ash grains. And here, ash, when I say ash, it's really silicate. So think about glass when I say that. And one interaction we were quite keen on, and actually how we sort of started this session off, has to do with charging of particles. In the volcanic case, volcanic lightning is observed in many explosive eruptions. For us, it's one of the great ways of actually detecting eruptions because the radio waves generated from lightning discharge can be detected at great distances from the event. So if the eruption is happening in the Aleutians or something in a remote place, that's a good way to detecting an eruption going on. And so we've been primarily interested in tackling this problem from experimental approaches, and that is to say, I guess I need to pull full screen here. That is to say, looking at different processes that can cause the charging. We heard about tribocharging earlier from particles contacting each other. And in volcanic eruptions, we can also create charging from breaking up of glass. Here I just have a Prince Rupert drop exploding as one illustration of this. And then, of course, there's a lot of water vapor in explosive volcanic eruptions. So you can also get ice grapple interaction in the upper atmosphere, much like a sort of dirty thunderstorm. One of the interesting things with going back to why these are great for detecting eruptions is that they're very sensitive, of course, to the background gas discharges. And so what I've shown here is a set of shock tube experiments set to mimic an eruption. And the idea here is we have different overpressure ratios shown by K in this upper panel here. And so this is just showing the pressure evolution as it goes above the vent. And if we have basically we have the exit of the material here. We actually overshoot, and we have this sort of underpressurized region. And then we have the shock going back up to the atmospheric pressure. If we look at this on a kind of typical Paschen curve, where we use this to look at peak discharge or basically the saturation levels that we can have on a particle. Initially, we might not be saturated in charge, but we could hit the saturation level as we decompress, have a bunch of discharges, and then once we have that shock, we quench that discharge. So we can look at it as a way to map out where that shock is, and consequently, we can map out the overpressure ratio, which is something we have a hard time doing from a distance. And that's kind of shown here, illustrating some discharges in a shock tube experiment. And then the bottom plot, we're illustrating discharges relative to these different modeled Mach disk elevations based upon the overpressure ratio. Another keen process we're interested in constraining in these sort of eruptions is how much does water absorb onto the surface of particles. This ultimately impacts the water budget, but of course, probably more important for us is aggregation of particles. Of course, the particles aggregate, they fall out of the plumes sooner. And in that eruption episode in Iceland about a decade ago, this was one of the principal sources of uncertainty in our simulations of ash dispersing over Europe, was this lack of aggregation physics. So all these processes are super important. These are very interesting to us in terms of trying to map out microphysical properties because they do change the dynamics of these larger plumes. But what I thought I would do the rest of the talk really is dive into some dynamics of these pyroclastic density currents, which are a type of particle wave gravity current, so acting under the influence of gravity. They're hot, and the gas in them is buoyant as a consequence. So they share a lot in common with other particle-laden gravity currents, like snow avalanches and dust storms. But they also, if they sediment enough particles, they form secondary plumes. And that's illustrated in this cartoon here. And one of the challenges we have with trying to simulate these sort of currents is that they contain a really wide range of concentration gradients. So at the bottom, they may be, almost close packing. We have to worry about things like fluidization and really dense granular flow, whereas at the top, it becomes quite dilute. And it's hard to see inside these currents, so it's very difficult to get real-time observations. And so one of the goals with what we're doing here using multi-phase models, and we're going to talk about some variants of simulations using MFIX, is really to get at some of these large-scale processes so that we can start to parameterize, simpler models that can be run at observatories like depth average models or dilute models. And so I'll show you some simulations we've done with MFIX, modifying it somewhat in terms of the turbulent scheme and some of the granular closure schemes. I won't talk much about the concentrated part of the flow today. I'll focus mostly on dilute dynamics. And what I'm going to talk about primarily is a set of experiments that we've compared, or set of simulations we've compared to experiments as part of a large benchmarking activity in the volcanology community. And this is a big set of experiments that were conducted in New Zealand over the last several years. As you can see from the schematic, there's a large hopper that heats volcanic ash and gas that's dropped onto a ramp, and then it propagates down the ramp, and we measure the dynamics at various profiles. And this hopefully shows a video of one of these experiments. This experiment is conducted at Massey University. The first bit of it is conducted inside an old boiler house, and then it goes outside. As it goes outside, of course, the conditions become a bit more variable and harder to control. So I'll show a set of simulations aimed at looking at some of these dynamics. They are simplified. We're not simulating the hopper drop. We're just looking at a concentration and velocity profile a little bit downstream and using that as our initial conditions. And in this set of simulations we're only going to look at one particle size, basically an aerodynamic equivalent 36 micron particle size. And again, these are aimed at simulating volcanic ash. And just to orient you, I'll show a simulation on this. This is a cross-section showing volume fraction. These are all fairly dilute. You can see it's a log scale here in terms of the color scheme. But they are, of course, very turbulent and entrain fairly efficiently. The simulations we've conducted, if we use this solder mean for our grain size, it does a reasonable job, except perhaps maybe at further times as we get outside that boiler house and we have a little bit of turbulence in the atmosphere that we didn't put into the simulations. We have found that as we add a broader grain size distribution, the dynamics do a little bit better. We also found that just due to the quirks of this experiment, we had to simulate outside the actual channel because there were walls of various heights that caused some issues with entrainment. We are keenly interested in determining the entrainment from these flows, and the process we've used a few different ways of getting at entrainment. But the process that I'll talk about today is we basically define a certain surface based upon volume fraction of the particles, and then basically look at how the gas fluxes inside or outside of that surface. And that's, of course, nice to do with numerical results. And this shows for a very dilute surface, the places where gas is going inside the flow, which we would call entrainment, the blues in this case, and then we have expansion is the sort of warmer colors. As you can imagine, how we set that surface is really important in terms of determining what our entrainment coefficient will be. And so if we set a very dilute surface, we're typically entraining more, basically efficiently across that dilute gradient. As it becomes more concentrated, it's harder to do work against that stable stratification, and the entrainment coefficient consequently goes down. So if we talk about classic entrainment coefficients, we're probably closer equivalent to the really dilute systems shown here at the top here. But for us, it's also really interesting in terms of mixing, how well does gas mix into different parts of the flow. And so as we get to really more concentrated, for us, more concentrated sort of currents, you see that the gas has quite a bit of trouble getting into that more concentrated part of the flow. And that has consequences in terms of redistributing temperature, which is one of the things we are keen to look at. To give you a bit more of a flavor of what's going on here, this is just showing some passive tracers where these passive particles, parcels really, as they entrain to the flow, they turn red. So you get a sense that a lot of the entrainment's going on through these Kelvin-Helmholtz instabilities at the top of the flow, with a little bit going on into the lobe and cleft or overriding instabilities. You can see this again. This is showing just a layer of different species of fluid at the bottom that's getting entrained, and you can see as it goes over the top there into those Kelvin-Helmholtz instabilities, it becomes part of the flow. But actually, it's having quite a bit of trouble mixing into the interior or the bottom of the flow. So a lot of the cooling and dilution is occurring at the top and not the bottom. So how does this play out in terms of a real flow? So I want to show you just some examples of calculations and observations from a volcano in Ecuador called Tungurahua that erupted in 2006 and subsequently. And from a distance from the observatory, this is basically what you see, which is not much because it's obscured by the volcanic ash, which is very opaque. But when we simulate these currents, we can take a look at how they interact with the topography. And typically on this volcano, they take advantage of pre-existing fluvial or river channels, and they can become quite concentrated as they go down those river channels, but they avulse or go over the side of the channel and form a sort of dilute surgy behavior. And also this particular flow dammed a river, this Rio Chambo river, over the eruption, which lasted basically one night. And this picture on the right here just showing a set of dunes that were formed over this eruption over one evening, and these are flows that actually jumped the riverbank and went on the other side and formed this dune field. The simulations do a fairly good job at predicting this, so where the concentrated flow should stay in the channel and where it should avulse and go outside the channel and form these dilute currents. This is important for a volcanologist because we've typically, when we've seen events from paleo events where we didn't actually get to observe the volcano, we might even map these as separate currents, the concentrated part and the dilute part. But here we see that they're easily transforming from concentrated to dilute in a single flow. A student, Mary Benage, did some interesting work trying to get at the temperature structure of these currents. And what she did was she observed that there were these large clasts. We call them volcanic bombs in the volcanic literature, but they're large clasts that are composed of these silicate materials. These are 10, 20, 30 centimeters across. And they're continuing to exalt volatiles as they're transported down the mountain. And so you can look at the bubble sizes at different radii to get a sense of their cooling behavior. And so she included these in a set of simulations along with the larger current and looking at the entrainment. And she found that, much like we were seeing before from the benchmark case, that it's pretty warm at the base of these currents. Over here, and it's not entraining much, mostly because we're just fighting against that stable stratification. So we have these really hot bottoms of these currents that stay in the channels, and the really dilute stuff that avulses is quite cool, actually. And that's shown more here. And so Mary's calculated entrainment into kind of what she calls the suspended load surface, and then also into bed load surface, which is the concentrated part of the current. And again, we see that these are varying from quite high values to relatively low values for the more concentrated part of the current. So to summarize, where we've typically have constrained entrainment in the volcanic literature has been based on turbidity current experiments using relatively limited entrainment. But we've seen with the comparison to those larger experiments and a number of other set of observations from Mary's work at Tungurahua, that the entrainment is actually quite a bit higher than this. And so this has implications for how quickly these cool and how quickly they entrain, and that influences ultimately the run-out distance of these currents. So I'll just leave the summary slides up here. But the important for what we're doing is we're typically using microphysical interactions to really feed into some of these simulations because they really play an important role in determining the dynamics. And of course, the challenge here, like many of you face, is that this is multi-scale. And so you have things going on at the grain size, but then in the case of volcanic eruptions, dynamics can be important over tens or 100-kilometer scales as well. I think I'll stop there and see if there are any questions.
Thank you, Professor Zach. Does anybody have any questions?
I'll go ahead and ask one, Janine. This is Jordan at NETL.
Hey, Jordan.
Where do you think that we need to go next with some of our modeling capabilities to kind of further advance this area of multi-phase flow modeling rather than just kind of focusing on traditional reactor design that we're used to?
I think, some of these feedbacks between the microphysics and the large scale would be important. So I mentioned aggregation as one example, but including, how the grain sizes are changing during an event is going to be important. Also, comminution or breaking up of particles is important for like the pyroclastic density current example we just looked at. Yeah, and I guess there are all sorts of resolution issues too, because I didn't talk about the denser part of the flow, but for us to really accurately simulate that, we typically have to be really pretty fine grid. And so how do we kind of grapple with that fine grid at the sort of base of these flows versus much more dilute dynamically is probably one of the things that would be really of interest to us.
Thank you.
I'm actually going to piggyback one more quick question on that one. Were all these simulations done in MFIX, or were there, if I missed it, I apologize.
Nope, all the simulations I showed on this talk were all in MFIX, yes.
Okay. Thank you. So we are actually probably back on time, so I'm going to move us to the next speaker, and if anybody has any questions, please just put them in the chat. And I'm not sure if we have Ray Fontenot with us.
Should be able to see my screen now.
Yeah, it looks like it's coming up. There it is. Ray is from CFD Research Corp, and looks like he's ready to go. Thank you, Ray.
Thank you. Yep, thank you. So, yeah, my name is Raymond Fontenot. I'm with CFD Research, and today I'll be presenting to you my work from NASA Phase 1 SBIR on uncertainty quantification for crater formation due to plume surface interactions. Now, granted, I will say this: a lot of what I talk about is, widely applicable to not just PSI, but any of our gas granular flows that we would typically care about. Okay. So when you look back, now we're trying to get to back to the moon. We think about, what were some of our big issues. And if you go look at any of the technical debriefs from Apollo, this is just from 12, dust is a big issue. Where does the dust go? How does it obscure what you're seeing when you're trying to land? Is it, collecting on equipment? Are you breathing it? And is it making where you're landing unstable? So effectively, dust and gas predominant flows are a huge challenge for us as we push beyond the Earth's surface. And if anybody happened to see what SpaceX did a couple weeks ago with Super Heavy, you realize that's not just an issue on the moon, that's an issue here. So plume surface interaction, we've got these high-powered rockets impacting, either a loose bed or some concrete on top of sand. All these simulations are frequently overly conservative, and the designs are because there's just so many unknowns in the process, which increases costs and penalties associated with how we go about simulating and building any of this equipment. What it does is a major concern to NASA designers, rocket companies, or anybody. In the space environment, low-side GGFS is the prime solution capability. So we rely on models for gas particle and particle-particle interactions with a limited fidelity and considerable uncertainty in the range of applicability we're working at. You're looking at very low pressures, rarefied conditions, compressible, from in the compressible gas regime to fully packed. So you're covering the gamut of potential flow regimes. So just to highlight this, you've got a high-speed nozzle, a rocket nozzle. You've got shock discs that form where the ejecta is going to be clearly seeing high-speed flows. You've got viscous erosion. You've got fluidization. You basically see any and every flow you could possibly imagine in these situations with gas particles. Now, what are the particles? Well, there's several different simulants, but effectively you're looking at a bunch of irregular shapes, multi-material, multi-sizes. It's also very dependent upon where you are on the surface of the moon as to what these particles look like. So knowing what these are and being able to simulate them is an issue. Also, especially in low pressure, low gravity environments, you have to worry about more so than you do here on the Earth, cohesive forces. Effectively, your classification shifts. So, larger particles may effectively be more cohesive. Regolith will fall into classes C and A due to this effect. You also have to worry about your small scale forces, van der Waals, electrostatics, and capillary bridging. Either due to liquid or ice. And this isn't just from the natural lunar environment. This is water from the rocket plume adding liquid to the lunar surface, so you induce a capillary effect. Now, as far as the constitutive models are concerned, granular frictional stress, just as in this classical form, hasn't, and from the literature even recently, isn't based on any proven physical basis. It just sort of happens to work. And there's a blending between these regimes, especially as you get to the frictional regime. So what does that do for us? Where does that uncertainty come? Is this true for all soils, especially low pressure. We're not entirely sure. Coefficient of restitution is another one where, especially in Eulerian simulations, it's typically fixed, but this is all material dependent. It's, due to the nature of the volume averaging, there's no variation with a normal collision versus something that's tangential. And additionally, even though there's been some corrections in the models due to, something, say, as a function of granular temperature or the friction of the material, you can get a wide variability in what those coefficients actually are. And then finally, you can go through models upon models. The internal angle of friction. So effectively, how the material comes to rest, depending on how you measure it, will give you a totally different answer as to what the internal angle of friction is. And again, typically, we'll only use a static value for internal angle of friction, which this can be a very dynamic quantity. And then specific for regolith, the known uncertainty is between 2 and 10 degrees, which can have a significant effect on the results of your simulations. So as far as, say, the gas dynamics, there's a significant number of forces: drag, lift, buoyancy, time history forces, PTKE, particle fluid particle, and then your nanoscale forces, Brownian thermophoresis. Most of these models have only been, well developed or validated for terrestrial conditions, typical STP conditions. What happens when you've got, and single particles. So what happens when you've got a dense suspension in a low pressure environment that's going supersonic? There's not a whole lot of literature, even for a single particle, with the exception of drag in those regimes. And even then, the literature, the models typically will only use a correction for dense regimes that has only been developed for incompressible regimes to correct for the porosity effects. You look at potential model development, you have to worry about this rarefied regime, this high pressure regime, rarefied compressible regimes. How do we typically model PSI? So, due to the scale of the problem, Eulerian-based two-fluid models are effectively the only practical treatment for this, because you're simulating hundreds of thousands or millions of particles over, they want to do kilometer scales for effectively, where does the dust go on the equipment, and that could be miles away. And again, we use all these models to reduce the scale and computational burden of the problem, but most of these haven't been tested under relevant conditions. Let me start this. So, and as far as we know, there's very limited experimental data in these regimes. And the experiments can't cover, it's difficult. We all know the problem. It's difficult for anybody to see into the granular material. So it's hard to get good validation data for these PSI conditions. This happens to be with loci GGFS, a simulation of the BFGT experiments that were carried out at Nash and Marshall. This simulation has 150 million cells. It took 5 weeks. It doesn't really lend itself, especially this is lab scale. It doesn't really lend these simulations don't lend themselves a lot to let's vary parameters and see what happens. What do we do in that situation? We've got your typical models that will bring in its uncertainties for the gas phase and again for the granular phase. So how do we actually approach uncertainty quantification for these kinds of problems? There's two typical approaches. You've got non-intrusive, so you use some external method to drive sims based on whatever analysis criteria you have. You can use Monte Carlo or sampling methods, stochastic expansions of surrogates for uncertainty analysis. So you insert some efficient propagation of uncertainties through your inputs and outputs. Or sensitivity analysis, where you've got some qualitative approach to evaluate the impact of those uncertainties versus your inputs and outputs. You use either screening approaches such as Morris one at a time, which we'll show in here, or global sensitivity analysis such as Sobol indices. Or you do intrusive approaches. So you've got significant code modifications where you do forward or backward automatic differentiation or adjoint methods. The plus or minuses between the two is that sensitivity, non-intrusive approaches, there's no code modifications. You have to run a significant number of simulations to get the relevant information that you want out. With intrusive methods, it's typically going to be only a handful of simulations you need to cover the basis you need. So we have two tools. We have SPLOT, which is a non-intrusive tool, which was developed under a previous NASA contract that we leveraged Dakota to do drive all these simulations and help us extract our sensitivities. And this we use herein as a verification approach for our forward automatic differentiation. Just for completeness, moat is, I'll show some results where as we go higher modified mean, it's a more important parameter. And as we go higher standard deviation, these terms tend to interact more. We can test all these in succession or simultaneously. It'll give you effectively elementary effects, so you don't necessarily get a lot of the coupling that might actually happen. But it's very dependent on the step size of your derivative that you choose. So this step here. Forward automatic differentiation is a mathematical tool of sensitivity analysis. Can be easily implemented, and you have a significant number of fewer simulations compared to non-intrusive methods. We do this by operation overloading. So effectively, we carry derivatives around with us through each computation. So like every addition, subtraction, multiplication, division. And this allows us to effectively, if I say I want to specify the uncertainty with respect to gas inflow, I can carry that throughout my simulation, and I can tell based off of these derivatives how different my simulation would be if I changed the gas velocity by, say, 10%. And we've enabled this within loci, so we can do this through any of our codes. So with respect to PSI, there's a canonical case done by Lamarche for jet impinging onto a granular bed of steel balls. So it's not quite representative of regolith, but it's much easier and it's safer to handle. Given these parameters, there's no turbulence. We do two studies. We do FAD with, say, plus or minus 10% variation, non-intrusive, Morris one at a time with 15%. And we're looking at, say, crater depth, width, and mass injected from the crater. So we're looking at crater shape and how much material is being injected. For comparison's sake, you can see how expensive this is. Mode requires running 32 separate runs to get the same data for 450 hours on this particular setup on the NASA systems. Sobol indices at the time when we did this data required 113 plus SEMs, so significantly expensive. We did non-FAD runs, so effectively we ran at our various conditions. And And then FAD, it takes, for the 4 parameters we look at, it's 4 runs. It takes about the same amount of time, and part of that is due to the inefficiency of how we implemented it initially. We have a phase 2 that's going on right now where this gap between these 2 numbers should be a lot wider. So with respect to moat, Lamarche shows that for the mass flow rate, it's a fairly, as time goes on, a fairly, there's not a whole lot of interactions affecting mass flux. All these parameters effectively are going to affect it about the same. There's not a parameter that's necessarily more important than one another. It's all nonlinear too. When we get to crater depth, their mass flow rate is linear with respect to how the crater varies. Internal angle of friction is very nonlinear. At startup, at later times, effectively everything else is very low importance, except for the mass flow rate has a high impact on how big the crater is. And again, you see similar trends here. For FAD, you can show we did the base, the plus or minus 10% FAD. There's data missing because the system, NASA was upgrading their systems and a lot of the information is lost. You can see very little variation between what we computed and then FAD informed information. So we're not technically running a simulation there. And you can see we effectively matched the data. So we were very happy with this. And then finally, as we go through and evolve the simulation with time, you can see we do a very good job with that capturing the crater shape. With the exception here, slight difference between the mass flow rates for the variation in the actual off design case. And this variation has to do with nonlinear effects, which we know we aren't capturing. This is a first order sim. So we hope that we can bridge this gap. And honestly, if I match this, I would be a little surprised. But you can see the shape varies mostly due to the mass flow, which is what we saw with the Morris one-at-a-time approach. So to conclude, as far as we are concerned on the moon and beyond, dust is and was and will be a major source of problems and uncertainty for any of our exploration efforts. And the bigger the rocket, the bigger the problems. Not only aren't landing surfaces aren't necessarily the only issue. Am I making a crater? How big is a crater? It's more, where does the ghost go? And as far as maneuvers, well, why can't I see anything is a big problem. So I need to know how much dust is actually there. There's not necessarily a silver bullet to which material property or model is a primary driver of uncertainty. We do have some suspicions, but a lot of that has to be compared with experimental data, and there is a sheer significant lack of that. We can, at least with our sensitivity analysis, identify our sources of uncertainty within our models for PSI. And as a lot of it's been talked about today, we really need to bridge the gap between the experiments and the modeling community, and work hand in hand to design better experiments so we can validate all of these tools we have. What's next? We have a lot of numerical work we have to do behind the scenes to allow us to more efficiently solve for these intrusive uncertainties with FAD, which is my work in my current phase 2. And with that, I thank you for your time, and we'll entertain any questions.
Thank you, Raymond. I think we'll probably just direct you to look at the questions in the chat. There appears to be one, just to keep us on schedule so far. Thank you. It was a very nice presentation. I'm going to move it to our next speaker. If they are ready, Jingsen Ma from Dynaflow. I cannot hear your audio. I'm not sure if you can unmute just to check. And
hi, what about now?
Perfect. And your slides you can share.
All right. For the internet speed, I will stop my video and share my slides. You see my slides now?
Yes, thank you.
Perfect.
You are good to go.
Thank you. Good afternoon, everyone. It's my honor to share with you our Dynaflow work on hybrid MPI OpenMP accelerated oil Lagrange modeling, a multiphase flow with bio applications. By the way, I'm Jingsen Ma at Dynaflow. You will see today the main application I'm introducing will be on NIH-sponsored applications. But actually, this numerical platform is actually be actively serving as a powerful tool to help DOE, ONR, and a variety of industry partners to solve their difficult problem. You will say I will mention a little, expand a little bit at the end. By the way, don't get confused. The application, even though it's mainly on NIH-sponsored project, but it's still within the energy category, and it's a smart way of using energy. High intensity focused ultrasound. I'm gonna start with a very brief introduction of that, and then we will go into the numerical modeling. Okay, then I'm gonna introduce how the hybrid parameterization scheme is being implemented to address that kind of application, followed by demo simulation with quantitative validations, and we will end up with the parameterization's efficiency analysis. Okay, why I call the high intense focus ultrasound is still energy, and it's a smart way of using energy, because HIFU can be used to thermally ablate solid tumors. And what's going on here can be explained by the picture below. Here, the blue thing, the blue dish you are seeing on the most left is the focused ultrasound generator, which generates ultrasound from outside the body and deliver the energy in a way such that the energy is deposited into a spot inside the body where there is tumor. Because the energy deposition there, it can cause temperature rise locally. So the tumor cells are being ablated, which means killed. Of course, this kind of therapy is very targeted because we can control where the energy should be focused on and deposited there, right? And non-invasive, because the focused ultrasound is sent from outside our body. And what makes it more exciting is by adding microbubbles. These kind of good effects can be further enhanced. So it's very important to NIH and the biomedical industry to develop a numeric platform which can allow us to do further analysis and to improve our understanding of the fundamental physics of this. And practically in clinic, the physician gonna need a numeric platform for treatment planning and optimization purpose. That's why we develop our software And for the in terms of numerical model, it's nothing. I think most of the most of our colleagues here are familiar with. So I'm going to be very brief. It's Euler-Lagrange two-phase flow model, which means we solve the mixture and Navier-Stokes equations for the overall flow field, but for the bubble inside, let's say zoom a small region of the computational domain, it will be tracked each individually by solving two equations. So the first one, the UB is the velocity, so it's a motion equation, which I think has already been introduced by several speakers during this workshop for particle tracking. So I will not go into there. And what's interesting and important here is the second question. You see, we have R dot, which means the size variation of the bubble. And you can see actually it's mainly determined by the pressure difference outside of the bubble, which is PT. At that instant of time, what kind of pressure is being encountered by that bubble. And PB, the pressure inside, and other terms. So this is a modified Taylor-Harry equation or Rayleigh-Placet equation. Based on these two equations for each individual bubble, we know what should be the void fraction in each cell, right? So that the bulk media flow is being modified due to their property change. On the other hand, the overall flow field provide pressure, velocity, and other quantities to drive the bubble dynamics and motions. So that's how the two-way covered Euler-Lagrange model is being configured. Now let's talk about, because we are trying to solve very challenging real-world problems, we need parallelization. So at the first level, we use MPI to do the domain decomposition. And the Eulerian grids will be distributed into different processors based on the subdomain. And correspondingly, the bubbles will be distributed into different subdomain based on where they fall into. So this is straightforward, right? As we know, for MPI domain decomposition, there is a very important thing. We need some ghost cells around each edge of the subdomain. So as you can see here, for example, we have a subdomain A, okay, and we have the blue cells, which is ghost cells around each edge. Traditionally, how we use the ghost cells, we use it to communicate with the subdomain. For example, we have subdomain A, subdomain B. When we solve the subdomain of B, we need the ghost cells of subdomain B to be filled by copying the edge real cell information from its neighbor, subdomain A, right? So just pay attention. The copy is from the real cell to ghost cell, and vice versa. A needs information from B. So this is being handled for the Eulerian solver. However, here comes the question about the Euler-Lagrange mapping. We are using a Gaussian spreading for void fraction scheme. For example, here the circle, that circle you are seeing is the inference range of each bubble. For example, here for bubble J, it's spreading its factor in a Gaussian distribution to influence the void fraction in neighboring cells. For example, I. What if? I mean, it's okay when both the bubble and the cells are inside the same domain. What if there is a subdomain edge separated them, and we have the issue, right? Because bubble J gonna need cell information such as I, which is in another processor. And same thing, cell I needs information of bubble J. So traditionally, people may think, okay, we can do the broadcasting of the bubble information. That's the whole list of bubble information to be known by every subdomain. But that's very costly. So here, that's one of the things we're doing very interestingly. So now let's talk about how we handle the data transfer about Y fraction. For example, here, near the edge of the left edge of subdomain B, there is a bubble. Okay, now we can allow the bubble to spread its void effects into the all neighboring cells, including ghost cells. And then we will have the void computation from that bubble in the ghost cell to be transferred into the edge cell, the subdomain A, so that without really sending bubble informations, the contribution of the bubble located in another subdomain is being mapped into the neighboring subdomains. And same thing when for the corner bubble, which means it has more than one direction as the neighboring subdomains. Okay, we do that one by one direction, and it's a sum of the Y fraction. And just do a very simple and quick test how it works. On purpose, I put the bubble at the very right top corner of subdomain A, which means subdomains B, C, D have no information, know nothing about the bubble. But we can see it's being very well smoothly contributed into all the neighboring subdomains. Okay, now let's use this parallelized solver to do some interesting app simulation. So here, focus ultrasound is generated and getting propagated through where there are bubble clouds and where we supposed to kill the tumor based on a temperature rise caused by these dynamics. And that's what the pressure control we obtained. And you can see the microbubble clouds modify the overall pressure waves. And actually, if we look at the temperature rise history at the folks, here, green, no bubble. That's the time history of temperature rise at the folks where there is tumor. Okay, when there is no bubble, you see you get the green curve. When we add some bubble, red, and more bubble, black. As you can see here, the temperature rise is being magnified by adding bubbles. Also, I like to point out the discrete points are from experiments, and we can see that overall the prediction match experiment measurements quite well. So this validates the all proof of the software. And actually, we have more advanced validation, including the ex vivo. Due to time limitation, I will not show here. But if you are interested, please contact me for more. Now let's talk about the efficiency about parallelization. As you can see here, that's the time for each step as a number, as a function for the number of processors we are using. And this is the speed up. Let me zoom in this one. Okay, first the red is the computation time for the neural solver. It's nearly linear. And for Lagrange, especially for the Lagrange mapping, by doing the way I just introduced, it's even better than linear. So that has something to do with the memory optimization by doing those kind of procedure. I don't think I have time to expand there, but that's interesting. At least he approved the way we are utilizing ghost cells has very minimum or negligible overhead. And that's the overall scaling testing. You can see when we have more than 100 processors, the speed up is also about the same, right? Now, maybe sometime it will be a little bit more challenging. What if there are very huge amount of bubbles, and which make the bubble computation become dominant? Since the bubble only cluster in a very small region, right? So what I'm showing here is an axisymmetric view, okay? And the black lines you are seeing are the subdomain borders. Okay, now let's activate the OpenMP inside each subdomain. Based on the bubble numbers, that subdomain or those subdomain hosts, okay, we distribute the number of threads. Here we call NTH. That's number of OpenMP threads, proportional to the bubble numbers inside the subdomain. Okay, by doing this, using the same workstation, for example, here is just a quick demo. We have a workstation has 4 12-core CPU nodes, which means in total, we have 48 cores. What if we use all 48 by MPI, which means we have 48 subdomains? Okay, then for that specific test case, the computer time is about 3 seconds, right, per step. What if we combine with OpenMP? We can see that can be reduced about 1/3. That means the hybrid, even using just exactly the same facility or resources, can significantly enhance the computation speed. By the way, I have another application example, which maybe you think will more fitting. We actually have done the bio-extraction of LG for DOE sponsored project. Okay, and actually the key technology here is a nozzle and cavitation. And you can see if inside our pattern nozzle, we generate cloud cavitations where you see the white color, that's the micro bubble clouds. And because these bubble growth caps can generate a very strong pressure oscillations, which will rupture the cells. So that's what you are getting. You see the foam, that's the LG is being ruptured and being extracted by the cloud cavitation generated by our pattern nozzle. And we like to optimize by taking advantage of our CFD capability. So this example, what I'm showing here. So here, the top left is the nozzle. Okay, the white bubbles are cavitation the white spheres are cavitation bubbles, and the black dots are the samples we release. And the color is the vorticity. And you can see when the bubble gets entrained into the vorticity, they grow, and as a result, the particles also being trained, interacting with them. Here is a zoom view of what we can capture. We can get the detail for each single biomass particle and the pressure history, each of the particle in count as a function of time. So this serves as a very powerful platform to do very fundamental analysis and then lead to optimization of the whole facility. Okay, I think it's time for me to wrap up. Rather than reading the summary, I will share a few papers on our speed up for real world applications, which has been very well recognized by the fluid engineering communities. For example, for our OpenMP parameterization, when I presented in the ASME conference, later it becomes a material and for HPC tutorial. And for the MPI parameterization, 2 years ago, we won the ASME CFD best paper. And then 2 years ago, the hybrid won the Multiphase best paper by ASME. In addition, our high performance computing for multiphase application also recognized by DOE as a NERSC user science highlights. Any question or your collaboration inquiry is more than welcome. And here's my email and also our company ad website. If you like to get a copy of the papers, actually they are available on our website. In case you cannot find it, just send a message. Thank you.
Thank you, Jinsen. I'm going to direct any questions to the chat.
Yeah.
It's a very impressive work. Appreciate that. We're going to move on to our next and I believe final speaker who has 2 presentations to give us. This is Farid Rusta.
Yes.
From Clarkston University.
Yep. Can you hear me?
Yes.
And can you see my screen?
Yes, we can. Thank you.
Thank you so much.
Good to go.
All right. Good afternoon, everyone. I'm Farid Rusta from Clarkson University, and today I'm going to present our research under the title of Stochastic Approach to Modeling Subgrid Scale Velocity Fluctuation in Large Simulation of Turbulent Wall-Bounded Particle-Laden Flows. For this presentation, first I'm going to go through introduction, a little bit motivation and objective of our work, going through the solver, our in-house solver and the computational domain that we are focusing on. Then I'm going to go through the result first, focusing on the DNS result that we got for particle deposition and dispersion. Then I'm going to go through the LES and the importance of subgrid scale velocity fluctuation on particle statistic and trying to model this subgrid scale velocity fluctuation to improve the LES prediction of particle deposition and dispersion. Then I'm going to go through the conclusion and future study. So the focus of this study is on a turbulent particle-laden flow. It happens in lots of industrial process and natural phenomena. I have some examples in here. For example, aerosol in exhale, breeze, or sneeze is a example of the turbulent particle-laden flow. Aerosols are scatter phase or particles in the turbulent flow of exhale, breeze. Or the other example can be sediment transport in river and blood flow, which carrying red blood cells solid can be assumed as a solid particles, and air pollution, volcanic eruption, rain formation in clouds, and sand and dust storm are all some examples of turbulent particle-laden flows. Two main approach for study of turbulent particle-laden flow can be categorized as experimental studies and numerical studies. Experimental studies can provide very useful information, can be used as the data can be used to validate the numerical solver. But sometimes it's hard to perform these experimental studies of turbulent particle laden flow, and most of the time it's expensive and time consuming. On the other hand, for the numerical simulation, first of all, we need a robust numerical algorithm, which is an ongoing topic of research. And through these numerical studies, we can go through a study of different parameters, effect of different parameters. We can actually study the behavior of the flow, the future behavior of the flow, and we can go through the design optimization through this approach, the numerical simulation. So the focus of this study is in numerical simulation of particle laden flow. We are using Eulerian Lagrangian, which is like Eulerian equation of the fluid flow is coupled with Lagrangian particle tracking. We have the assumption of point particle, as we are focusing on a particle with the diameter of in the range of Kolmogorov length scale. The advantage of this actually method is high accuracy to resolve the dispersed phase at lower mass fraction, and simplicity of modeling the interaction between two phases. For the carrier phase or Eulerian equation of fluid flow, there are three main approaches: DNS, LES, and RANS. DNS, as you may know, resolve all the turbulent scales. No modeling is needed, but it's computationally very expensive. On the other hand, we have RANS simulation, which Reynolds stress terms are modeled, and it gives us the mean quantities of the fluid flow, and it has lowest computational cost. LES, which stands in between of RANS and DNS, is basically a trade-off between accuracy and computational cost. Subgrid scale stresses are modeling this method, and it just resolves the large scale of the turbulent flow. So this seems like a good approach for like modeling the Eulerian phase and couple it with the Lagrangian phase of the Lagrangian equation of the particles. But the drawback is the only fertile velocity after the using the LES is available for Lagrangian equation of the particles. So we want to first of all get to know how much the subgrid scale velocity fluctuation can be important, and if we are using the LES, is there any way that we can actually model those subgrid scale to improve the LES prediction of second phase or the particle motions. So in lots of real world application of LES, when we are focusing on the interaction between the turbulent flow and the second phase, these grids, LES grids, are very big compared to the size of the particle or our second phase, and lots of stuff is happening in the subgrid scale. This subgrid scale velocity fluctuation, for example, in atmospheric science, can be very important in a study of cloud formation. For example, grid spacing in today's highest resolution operational global model in atmospheric science is in the order of 10 kilometers. And for study of like cloud formation, we have to have some model for modeling these subgrid scale velocity fluctuation, because it all depends on the interaction of the turbulent flow with this droplet in subgrid scale of the grid resolution that we have. First of all, for motivational objective of this study, I can say that first of all, we want to develop a computational model for accurately predicting the particle dispersion and deposition in channel flow as the simplest geometry, to assess the influence of different assumption and different assumption that we have in the numerical simulation of particle laden flow. For example, the particle wall collision mechanism, the importance of lift forces, gravity, and particle Stokes number, and eventually we want to validate our result from the computational modeling with the experimental results. Then we want to focus on these subgrid scale velocity fluctuation. First of all, show how these subgrid scale, how much these subgrid scale fluctuation are important, and if they are important, how we can model this subcritical velocity fluctuation to improve our LES result. So for the geometry that we are focusing in here, as I mentioned, we are focusing on channel flow. We are using DNS or LES for carrier phase, and it's coupled with Lagrangian particle tracking. We are using the point particle assumption, one-way coupling. Vertical channel can flowing downward or upward, or we can just neglect the effect of gravity. As you can see in here, the dimension of the computational domain is 2 pi h, 2h, pi h in streamwise, normal and span-wise direction, and h is half of the channel width. And we have no slip boundary condition for walls and periodic boundary condition for the others. Friction Reynolds number that we are focusing on in here is 180, and we are, for most of the cases, we are tracking 200,000 particles. Particle wall collision can be fully elastic. When the particle hit the wall, can bounce back to the domain, or can be fully absorbing. When the particle hit the wall, we just take them out of the domain and replace them with a new particle randomly through the domain. For the DNS study, we are using 128 mesh grid in each direction, and the in-house solver is parallel running distributed memory environment. So basically, we can increase the grid resolution, Reynolds number, grid resolution, and the number of the particles. You can see the range of the particles that we are considering for this study in this table, starting Sux number from 1 to up to 130. Sux number, of course, is the relaxation time for particle velocity divided by fluid time scaling wall unit. So the particle that we consider for this study have a Sux number starting from 1 up to 130, and the dimension of particles in wall unit are from 0.1 up to 1. Here you can see how this motion of the particles in the channel. This is like wall-to-wall cross-section of the channel, starting from bottom wall to the top wall. As you can see, we have two Sux number of 5 and 100 in here, two particle wall collision mechanism, elastic wall and trap wall. As you can see, for both particles, the Sux number, eventually for the case of elastic wall collision mechanism, we have a accumulation of the particle close to the wall, and you can see how these particles are following the coherent structure of the turbulence, especially in near wall region. So as I mentioned, for the case that we are using the elastic wall assumption, when the particle hit the wall, they bounce back to the actually channel. Eventually, when we simulate the flow over time, we have increasing concentration of the particles in near wall region. The graph on the left of the page shows the concentration of the particles in near wall region as a function of time. For the case of elastic wall assumption, as you can see, we have a constant migration of the particles toward the wall. And as you can see in here, in like a snapshot of particle dispersion after 200 non-dimensional time, you can see that eventually for the case of elastic wall, we have all the particles accumulating in near wall region. So for solving this problem, we focus on the trap wall assumption, which when the particle hit the wall, bounce back to the domain. As you can see, it solved the problem of accumulation of the particles in near wall region due to turbophoresis effect. And we show that it gives very considerably good result when we compare the result with the experimental result. So for the rest of this study, we are focusing on the trap wall assumption for reaching to a steady results of particle laden flow. Here we can see the deposition velocity of the particles as a function of a Sux number. For the case of downward flow, no gravity, and upward flow, as we expected, for the particle with a Sux number less than 20, we have higher deposition velocity for downward flow. And it's because of the lift force, shear-induced lift force pushes the particles toward the wall for the downward flow. so it increased the deposition velocity of the particles. But for Stokes number higher than 20, we have the lowest deposition velocity for downward flow, and this is against what we expected before. So the reason can be we can focus on the finding a reason for that behavior by looking at the lift force equation. As you can see, lift force direction is a function of a slip velocity, the velocity, streamwise velocity of the particles with respect to fluid flow, and the sign of a slip velocity actually detect the lift force direction. If we just focus on the graph on the left of the page, you can see the streamwise velocity of the particles compared to the fluid flow, downward red, no gravity black, and upward flow blue. And the fluid streamwise velocity is dashed line for 4 different particle Stokes number. If we focus on Stokes 32 blue line, you can see by marching from the center of channel higher y plus toward the lower y plus, the streamwise velocity of the particles and following the blue line is less than fluid flow at the first, but at some point when we are getting close to the wall, it increases and the slip velocity become positive, or the actually velocity, streamwise velocity of particle becomes higher than fluid flow. This change of direction of the lift force, as we can see on the right figure in this page, at the bottom blue line, the change of direction of actually lift force causes a buffer layer which has like high concentration of the particles. Because of this change of direction of the lift force, pushes to the wall when it's like negative, when it's positive, push the particles far from the wall, and it causes a buffer layer with high concentration of the particle, as we can see when we look at the concentration of the particles for as a function of y plus. Here again, when we focus on the Stokes number of 32 blue line, you can see that we have a high concentration on y plus, like let's say 5 or 6, the exact location that we have the highest velocity fluctuation. So this high concentration of the particles at the location that we have the highest velocity fluctuation causes that like high deposition velocity for upward flow for the case of highest Stokes number particle with highest Stokes number. So in this way, we can justify the unexpected behavior that we saw before for like deposition velocity of the particle with high particle Stokes number. So that was some example of our result for the DNS simulation. For more results, you can refer to recently published paper in the International Journal of Multiphase Flow, just for the DNS result. So for looking at the importance of this subgrid scale velocity fluctuation on particle statistic, we actually filtered our DNS result. We used sharp cutoff filter with different filtering width. As you can see, when we increase the filtering width, the normal velocity of the normal velocity fluctuation of the fluid flow decreases. When we have the, for example, for FDNS8, which is the highest filtering width, we have the lowest fluctuation in normal direction. So basically, we are filtering the DNS data, and we want to see how this affect the particle statistic, especially particle deposition. Here, when we look at the deposition velocity of the particles for cases of DNS and filter DNS with different filtering width, we can see that by increasing the filtering strength or filtering width, we are increasing the deposition velocity, as the lowest deposition velocity belongs to the FDNS8, which has the highest filtering highest filtering strength. So this proves the importance of subgrid scale velocity fluctuation on the statistic of the particle, especially deposition velocity. So for increasing the accuracy of like LES, we need to model these subgrid scale velocity fluctuation. For modeling the subgrid scale velocity fluctuation, we use the stochastic modeling, the CRW or continuous random walk method. I don't want to go through the detail of deriving the equation. It starts with the like base Langevin equation, and it comes with some modification based on adding some drift velocity and make it a function of a Stokes number and normalize the equation. But this is the final equation that we're going to use for generating the velocity fluctuation. These like velocity fluctuation at each time step going to be added to the filtered velocity of LES, and then we use that as the velocity that particle seen as the velocity of the fluid flow. Two important parameters that need to be specified in this equation are Lagrangian tau or Lagrangian time scale of the particles, and sigma or RMS of subgrid scale velocity fluctuation. Because we are using the filter DNS, so we can compare the result after filtering compared to the before filterings and find the exact value of RMS of SGS velocity fluctuation. So we have the sigma. The only parameter for this part that we need to specify is tau or time scale, Lagrangian time scale, which is by going through the dimensional analysis, we can get the sense that it would be length scale divided by square root of kinetic energy of subgrid scale fluctuations. So we modify the most common equation in the literature by making the equation of time scale, first of all, a function of velocity, subgrid scale velocity fluctuation in normal direction instead of using a square root of 2/3 of subgrid scale kinetic energy. This comes from the assumption of homogeneous behavior of subgrid scale velocity, subgrid scale fluctuation in each direction, but we show that it's not the behavior is not homogeneous, and we have the different fluctuation in different direction. And as we have the exact value of velocity fluctuation in normal direction, we can just use that one in the equation of the time scale. So after modifying this time scale using the normal velocity fluctuation, subgrid velocity fluctuation, and make it the equation a function of a Stokes number and putting a damping for near wall value to making the time scale going toward the zero when we are getting close to the wall. We saw that the model can provide very good result and improve the filter DNS result. As you can see here, the red line is the deposition velocity coming from the DNS. We are using as a measure to compare our result and improve our result. The blue line is FTNS, as we saw before, with filtering width of 16, and the green line is the FTNS plus the model that I introduced before. As you can see here, the deposition velocity improved a lot, although we have over-prediction of the slightly over-prediction of deposition velocity, but overall we improved the prediction of deposition velocity for the filter DNS dramatically, especially for the particle with lower Stokes number, by using this stochastic model for subgrid scale velocity fluctuation. So for the conclusion, I can say that the concentration of larger particles in the buffer layer increases the particle deposition rate, as we saw. Neglecting the subgrid scale fluctuation effects on particle significantly, the particle affects on the particle statistics significantly, and it can decrease the deposition velocity. Using appropriate subgrid scale model improves the deposition velocity prediction of the LES, as we saw before. For the future work, we're going to go through the testing the model for different resolution of actual LES and improve the accuracy for particles with different Stokes number. Thank you so much for your attention. If you have any question, I'll be with you.
Thank you, Fareed. I'm probably going to have a hold questions. Maybe people can post them in the chat and we can come to your next talk.
Sure.
Which I'll take a minute to get up. If anybody has any questions, don't forget there's the chat function that you can check and post them there, and the presenters will have a chance to come back and maybe look at those.
Sure. Yeah. If you have any question, you can email me. I'm pretty sure that you can find my email address, which is rustaf@stclarkson.edu. And sure, I'll check the chat box after my second presentation, I would say.
Yeah.
Because we are out of time.
If I see any, I'll make sure to give you a note.
Yeah. I'm still struggling to use this application. I don't know how I can come out of this.
So if you shared, just
Oh yeah, stop the sharing thing. I think none of these questions are mine, I guess.
No, there's no questions for your talk yet.
Sure.
I'll let you know at the end of the second one if I saw any go by.
All right.
Chance to look as
So
well.
should I start the second one?
Yes, please.
All right. Thank you.
And thank you for that nice first talk.
Thank you so much. All right, for the second talk, I'm going to go through two-phase liquid-solid flows in rock fractures with a specific application of geothermal energy. So it's completely different from the previous talk. For this talk, we are mainly focused on modeling of two-phase flow, laminar, and with geothermal application. For this, again, I'm going to go through some introduction, geothermal application, introducing the CFD code that we are using, and then I'm going to go through the results. We got the result using two different software of StarCCM Plus and Rocky Fluent. First of all, I'm going to go through the result of a smooth channel fracture, and then going through the fracture with the roughness for the walls through fracture coverage and seeing the characteristic as a function of time and a particle displacement through the time. Then I'm going to go through the conclusion and future work. So for this actually application, the purpose is fracking the rock formation and keep it open for hot water flow. So this process is started with drilling a horizontal well in targeted formation and inserting a steel pipe with holes into the well bore. Then pressurized liquid and propellant are injected into well bore and the targeted formation fractures. Injection after this process, injection is ceased and the fracking liquid is drained. The propellant in the fracking fluid penetrate rock fracture and keep them open and allowing the hot water flow back to the surface. So basically, for this application, we are interested on studying the propellant in the fracture and how we can increase the fracture coverage. When we have the highest number of particle trapped inside the fracture, we can increase the fracture coverage, of course, and that allows the highest water going through the fracture and absorbing the heat from the hot rock formation and flowing back to the surface, which is very important in geothermal energy application. So the motivation of this study was experimental. Because the experimental field studies are so expensive, we need to have a numerical method for studying these propellant movement inside the fracture with a realistic geometry, which most of the time just a simple channel was used for numerical simulation of the fractures. We want to correct that with replacing a fracture with realistic geometry, including the rough walls. And we want to study the effect of propellant's properties on the fracture coverage and heat transfer for different like geometry of the fracture and different type of the fluid flow. So the objectives are to develop a computational model for propant flows in rock fractures and assess the fracture coverage and heat transfer under different conditions. And as I mentioned before, we are using two computational models. First one is StarCCM Plus, and the second one is Rocky Fluent Solver. Both of them are coming with the four-way coupling between the particles and the fluid flow, means that beside the effect of fluid on particles, particle on the fluid, we are considering the particle collision and particle wall collisions as well in these two softwares. So for the like making the geometry and preparing the like the solver, first of all, we started with making the fracture walls with roughness using the SyncFrac application, which is basically create a wall with the roughness through the Brown random method, and we then use these two walls, top and bottom walls of the fracture, to make a channel, as you can see using the MATLAB code, and then this channel was used for like study the propant's movement through the fracture. First of all, we focused on the assumption of a smooth channel, which is very common in the literature. We wanted to see when we are using the smooth channel as the geometry of the fracture, how these particles move through the channel. As you can see, the fracture coverage that we can get with this assumption is not significant, and basically, as we can see in here, all the particles that we are injecting to the domain gonna leave the domain without like getting trapped inside the domain, because we do not have any like roughness for this simple geometry of the channel. So then we switch to the geometry that we made, which has a roughness, and we try to study different sets of particles. As you can see in here, we are focusing on the fracture with a dimension of 0.1 to 0.1 meter, and the mean aperture size, which is the distance mean average, the distance of top and bottom wall of the fracture, is 0.4 millimeter. Gravity is in z direction, as we can see in here, and we are using a slick water as our fluid flow and sands as our propants. We are injecting 1,000 particles per second, and the inlet pressure is 10 meter squared divided by second squared, normalized by the fluid density. As we can see in here, the particles, as I mentioned, we are using 4 sets of particles with diameter of 0.3 millimeter, 0.35 millimeter, 0.37, and 0.4 millimeter. As you can see in here, particles with diameter of 0.37 millimeter gives the highest fracture coverage, which is like the purpose of this study, finding the appropriate propant which provides the highest fracture coverage. So as we can see in here, for when the diameter of particles or propants are much less than the mean aperture size, we do not have that much particle trapped inside the fracture. When it's getting close to the mean aperture size, we can create a blockage at the inlet of the fractures, which is not like our interest in this like type of fracking. Here we can see the number of particles as a function of time. As I mentioned before, the particles with diameter of 0.37 have the highest number of particles trapped inside the fracture, which can be proved by looking at the outlet velocity. As I mentioned on the previous slide, a particle with diameter of 0.4 millimeter can cause a blockage, which is clear by looking at the outlet velocity of the particles. Again, by looking at the velocity contour for a particle with diameter of 0.3 and 0.4 and the pressure contour, we can see the blockage that the particle with diameter of 0.4 can cause at the inlet of the fracture. Here is movies of how these particles are or propants are flowing inside the fracture for two diameter of 0.3 millimeter and 0.35 millimeters. For the case that we have mean aperture size of 0.4 millimeters, which we saw before, that the diameter of 0.35 gives the highest, gives the higher coverage compared to 0.3 millimeters, which can be seen in this excuse me, video as well. Then we try the different mean aperture size. Here we have 0.8 millimeter mean aperture size. We tried the same particle sets that we had before. Here we can see that when the particle size are much less than mean aperture size, the actually coverage is almost negligible for all the particle diameters that we consider in this study, which proves that when the particles diameters are less than mean aperture size, we may go through the assumption of the like a smooth channel that we saw before, because both of them cannot predict the coverage or cannot give that much coverage when we have this propant flow inside the fracture. And this is the contour of the velocity and the number of particles as a function of time. As I mentioned before, for these mean aperture size, for these sets of particles that we are considering in this study, all sets of particles have almost same number of particles or same amount of coverage, which are not that much negligible. Then we focus on the effect of gravity. We try the gravity in other direction, in y direction. In here, as we can see here, the changes are not significant when we are comparing these graphs. We are again using the same sets of particles. When we compare this result with the previous one, that the gravity was in z direction, we cannot see that much significant changes. So we can say that for these actually cases that we considered in here, gravity doesn't play important or significant role in particle displacement inside the fracture. It can be proved by looking at the number of particles as a function of time as well, and compare this one with the previous result that we got for the gravity in z direction. We increase the mean aperture size and we use different sets of particles. Here we have particle diameter of 0.35 millimeter, 0.6 millimeter, and up to 0.9 millimeter. Here we can see that although the particle with diameter of 0.7 may give the highest coverage, but at some point we reach to a blockage at the inlet section of the channel. So basically we can recommend injection with particle with diameter of 0.6 for this mean aperture size. So beside the coverage, we have to look at the blockage that these particles may cause at the inlet section, because when we have the blockage, we cannot get the flow back, and basically injection with this propant size cannot be useful for the application that we are focusing on. This blockage can be seen by looking at the number of particles in here. Although we have the higher number of particles for the particle with the diameter of 0.7, but at some point we'll reach to a constant number of particles, which indicate the blockage that it caused at the inlet section of the fracture. So beside the effect of mean aperture size, gravity, and diameter of propants, we studied the pressure gradient as well for different diameter of the particles. We can say for the range of pressure gradient that we consider in this case, pressure gradient doesn't play a significant role, as you can see in this graph. And overall, we can say that increasing the pressure gradient even can decrease the final coverage that we can get from this fracking. We studied the effect of viscosity as well as effect of shape of propant as well. viscosity, we saw that the lower viscosity may cause higher fracture coverage, and for the shape of propant, we eventually reported that for different diameter of particles, particle with spherical shape may cause higher fracture coverage. Besides this, like focusing on the propant movement inside the fracture, we want to focus on the heat transfer as well. We started with just looking at heat transfer from the wall for the case that we do not have propant coverage inside the wall. So eventually we want to have these propants trapped inside the fracture, and then we want to start like looking at the heat transfer. But for the first step, we just use the water flow and nanofluid to see how using the nanofluid can affect the heat transfer from the wall for the final application of the geothermal energy. So in the left figure, left contour, we have just water flow, and the right contour, we are using the nanofluid, which is water plus aluminum oxide. We can report for the case that we have nanofluid, we can increase the heat transfer compared to the case that we have just water flow flowing inside the fracture. For the conclusion and the future study, I would say a novel procedure to numerically study the propant transport in the fracture with realistic surface roughness was introduced. Sample results on effect of particle diameter, inlet pressure, fluid viscosity, and shape of propant on the coverage of the fracture were reported. A novel procedure to numerically study the propant transport fracture with realistic surface roughness was introduced as well. For the future study, the effect of fracture characteristic, including the mean aperture size and the propant properties on fracture heat transfer, would be investigated as well. Thank you so much for your attention. I'll be with you in the case of any question.
Thank you, Fareed. Again, a great talk.
Thank you so much.
I don't see any questions in the chat, but we do have a few minutes if there's anybody who had any comments or questions for the last presenter.
Hi, Jane. I just wanted to add that I think in the chat, Jana mentioned that I think the recordings of this meeting will be available in the NETL website under the proceedings.
Yes. So if anybody hadn't caught that, there will be a recording of these sessions available. A couple of questions had come up on that note. Well, Fareed, I don't see any questions, but if anybody comes up with any, I believe they could probably get in contact with you, as you mentioned.
Sure, yeah.
And I want to thank you again and thank all our presenters for this afternoon session. Much appreciated. And of course, there is another day tomorrow. I don't know if Murdad here wanted to make any other announcements, but it'll start at the same time.
Yes, that's right, Jenny. Thank you. And yeah, thanks everyone, participants, presenters, session chairs, and moderators. Much appreciated. Tomorrow we'll get together again at 9 a.m. and we have one more day of various presentations. So look forward to seeing all of you tomorrow morning then. If nothing else, you all have a wonderful rest of the day. Thank you.